Hey everyone, today I want to talk to you about superconductivity and the Higgs field. Now you might be thinking, superconductivity? The Higgs field? Huh, what? What do those things possibly have in common? Great question. You've come to the right place. But before we get into it, we've got a bit of housekeeping to do. So first of all, here are the timestamps for this video. Now, I'm very aware that it's kind of unusual to post a 5-hour physics video, but think of it like an audiobook. Now, of course, in physics, you can't just have audio because you got equations and figures and animations, so it's like an audio video book. So even though it's long, there's a lot of good stuff, and it's all in service of this profound vision of the facts that we basically live in a superconductor, as we'll talk about. So I know the length of the video is a bit unconventional, but I really am enamored by the online video format, and I think it has a lot of potential. Ultimately, it's up to you to decide whether this is something that's worthwhile. But I put it to you for your consideration. I recommend watching the video in sequential order because the ideas build on themselves, but it's up to you. You can watch it however you want to watch it. Maybe there's a topic that you already know, so you want to skip ahead. Maybe you're watching this in multiple sittings and you want to pick up where you left off. Well, in any case, do as you wish. In this video, we're going to be drawing ideas and equations from 3 books. First up, we have Introduction to Elementary Particles by David Griffiths. And this is like the sacred text. This is the most amazing introductory text to particle physics that has ever been written. I cannot recommend it highly enough. It covers everything from the basics of quantum mechanics to relativity to gauge theory to all kinds of stuff. So definitely check out that book. In addition to that, we also have Introduction to Superconductivity by Michael Tinkham. Don't let the name fool you, okay? This book is quite intense. It's very rigorous and mathematical, but that's a good thing. Think of it like a cookbook with a bunch of delicious recipes. In this book, you can find a very, very comprehensive overview of superconductivity. And finally, we also have Gauge Theories of the Strong, Weak, and Electromagnetic Interactions by Chris Quigg. This is a fantastic book, and I highly recommend for anyone who's interested in a gauge theoretic perspective, and also a nice comprehensive overview of the Standard Model. In addition to these books, we're also going to be referencing a variety of papers throughout the video, and you can find links to those in the description below. And last but not least, I will also be posting video note PDFs, as well as animation Python codes to my Patreon. And how that works is if you sign up on there for $5 a month, then you're in the club, and then you can access all of my posts, whether it's the video notes or the Python codes or anything else. I don't charge per post. It's just if you're in the club, you're in the club. So thank you to everyone who has signed up on there. And if you're considering signing up, please do. Please support my channel. These videos are a labor of love. I truly enjoy this, and I hope that passion comes through. It is also a ton of work, and if you want to support my channel, that really means a lot. So thank you for your consideration. And with that, let's get into the video. Hey, let me ask you a question. Are you in space right now? Well, no, you're in air. There's air all around you. But there is space between those air molecules. And in fact, that space plays an essential role in allowing air to do what air does. Whether that's creating air resistance, or blowing around in the wind, or just bumping into stuff, you know? Air, as we know it, depends on having some space in which to exist. And I know that's pretty obvious, but hang on to that sense of obviousness, because things are about to get weird. Okay, so the properties of air, like for example air resistance, this is not a fundamental property of the universe. When you think about space, and you think about how most of the universe is just this empty, frictionless vacuum, you realize that air resistance is actually a particular phenomenon that happens down here on Earth with our atmosphere, or I guess on another planet with an atmosphere. But it's not the norm, and it's actually not as fundamental as our everyday experience makes it seem to be. So then, suppose we want to discover the ultimate truths of reality, the bedrock truths at the foundation of physics. So not the things like air resistance that are particular to a particular environment or particular material, but I mean, what are the fundamental truths of nature, you know? And to understand that, we should think about things in the vacuum of space, where everything is really isolated and clean and pure, to get at the most basic, most essential patterns of nature. if we can understand the bare minimum aspects of reality and empty space, then we can better understand what happens when that space is filled with arrangements of stuff. But here's the problem. Empty space itself is not empty. And I don't just mean that space isn't empty because there's light and gravitational waves and all that. No, I'm making a far more provocative claim. I'm saying that the thing that we consider to be the empty vacuum of space is not some empty, platonically ideal notion of mathematical extensivity, but rather that all of that supposedly empty space, including all the tiny space between and within atoms, is filled with a kind of substance. Although substance is not exactly the right word. Material essence might be a better way of describing it, though that's kind of vague and confusing. Sometimes people describe it in terms of jello or molasses, but it's not edible, and besides, it's not viscous either. If we're being technical, we can call it the Higgs field, and that's all fine and good, and that's the proper terminology to which all kinds of formal details have been attached. But Higgs field is not a very inviting term. It doesn't give the intuition anything to grab onto, and that's why so many people, even today, have no idea what the Higgs field is. They've just heard that there's some field or whatever, but they don't really have a picture of what it is and why it matters. So, our goal today is simple: to develop a remarkable, astonishing, awe-inspiring mental image of what the Higgs field is, and how it radically alters the reality that we perceive. And our approach to developing that image is based on a peculiar insight, that in all the English language, the single best word for describing what the Higgs field is superconductor. So that'll be the central theme of the video. We're going to look at the Higgs field through the lens of superconductivity. Now, to be clear, I'm not exactly saying that the Higgs field is a superconductor, in the narrow technical sense of the word. There are some nuances and caveats, and we'll get to those. But I will say that the Higgs field is a superconductor like a goose is a duck. That's about how similar these things are, as we'll see. So on the one hand, I don't want to make a too low resolution of a statement and just say that the Higgs field equals a superconductor, because that could be misleadingly simple. But on the other hand, I really cannot overemphasize the similarities between the Higgs field and superconductivity. And so I think there is actually some utility in just imagining that these two are the same thing, and then carving in the nuances and caveats as you go along. Like, that's actually not a bad strategy for learning about the Higgs field. And don't just take my word for it, okay? This video was heavily inspired by the brilliant paper From Superconductors to Supercolliders by Lance Dixon, which is one of my favorite papers of all time. Link in the description. You should read it, it's great. And it lends credibility to the bizarre ideas we'll be exploring today. Okay, so you know the observable universe? Like, all the things? Imagine as a thought experiment that there's like an atmosphere everywhere throughout all of that, hypothetically, like all of space. You could breathe if you were on the moon or way out in space, there's air, right? So imagine and feel what that would be like. Okay, but now, instead of air, imagine that it's something like a superconducting condensate, which you don't have to know about yet, we'll get into it. But for now, just know that while this condensate doesn't have air resistance, it does have some other properties which pertain to it, rather than to the underlying reality of things. And so this substance-like thing that's spread out all throughout our universe is actually contaminating our laws of physics, even in the vacuum of space where you expect things to be clean and pure. Okay, well, right away, you see an apparent problem here. If there really is something like a superconducting condensate spread all throughout space, here and there and all over the place, then it should be radically modifying the laws of physics. Our universe should be all messed up. But when you look around, it seems like the laws of physics are totally fine. Nature seems completely normal. There's mountains and trees and sunshine and all of that. It's all fine. So what do you mean there's a superconducting condensate everywhere? If we don't see the effects of it, then obviously it's not actually there. And this whole idea is preposterous and absurd. But here's the thing. To understand the Higgs field, we have to peel back a layer of the onion of nature. This requires a kind of radical open-mindedness. Actually, it requires an epiphany. What we consider the normal, natural, regular old world around us actually has a severely messed up laws of physics. So the world as we know it, with all its mountains and trees and sunshine, and all the patterns of nature which are mostly electromagnetic, and all that you touch, and all that you see, and all that you taste, and all you feel, and all of that, is immersed in the Higgs field, this strange superconductor-like field that has somehow been spilled throughout our universe. And the result of the Higgs field is that it turns off the thing we call the weak nuclear force, and also makes it seem like electromagnetism is this simple little U1 symmetry thing, when in reality, that U1 symmetry is just a fragment of the world of weak isospin and hypercharge, which pertains to the SU2 cross U1 symmetry of the electroweak interaction. If not for the Higgs field, if the electroweak interaction were able to manifest without being suppressed by that Higgs field, then the whole fabric of reality would have a completely different character, symbolized here by that exotic rainbow pattern, which of course is not to be taken literally, but is to be taken seriously as a representation of the unimaginable tapestry of cause and effect, which the comfy blanket of the Higgs field protects us from. This seems unusual and surreal, because we're talking about a layer of reality which is deeper than the one that our perceptions are based on. It's a bit like trying to understand the physics of space if you don't have a rocket and so you're stuck here on Earth and you just have to imagine what it would be like if not for all the air molecules. Well, you could do it, but you'd have to mentally immerse yourself in a hypothetical, but it's more than just a hypothetical because it is all around you if not for that other thing that's all around you. You know what I mean? It's like, man, you have to read between the lines of reality. Again, we are in space right now. Space is all around us, but there's air here too. And so we have air resistance and all that. And we are in this deeper, mind-blowing reality of electroweak unification. It's all around us. But there's a Higgs field here too. And so the weak force is turned off, and electromagnetism manifests as a simple phase symmetry. And we have all the patterns of the world in which we grew up, in which our common sense was developed. But common sense is a small subset of truth. And in physics, we go beyond. And although it seems very unusual and crazy at first, eventually it clicks, and then you'll find yourself closer to truth, with a deeper understanding of the world in which we live. Okay, so before we get into the details, here is an overview of what we'll be talking about today. First, we're going to have like a crash course on superconductivity, and we're going to take a historical approach, looking at some of the main discoveries and theoretical developments in chronological order, so that we can see not just the equations, but also where they come from and why. And that'll give us a good conceptual framework for understanding and exploring superconductivity. So then, when we say that the Higgs field is like a superconductor, we'll have a good idea of what it means for something to be like a superconductor. Then, when we get to the early 1960s, the story is going to naturally segue into the Anderson-Higgs mechanism, which is the way in which otherwise massless gauge bosons acquire mass, the photons in the case of superconductors, and the W's and Z bosons in the case of the Higgs field. And we're going to linger on the Anderson-Higgs mechanism for a while, because that's really the core concept at the heart of everything we'll be talking about today. Towards the end of the video, we'll also briefly talk about electroweak unification at the highest level, just the big picture of the basic idea, and how the Higgs field fits into the picture, so that you can start to see and feel the deeper reality underneath electromagnetism and the weak nuclear force. But we're not going to get too technical on electroweak unification today, in the interest of time. That's a topic I would very much like to come back to someday, but it deserves its own video, or maybe a series of videos. Let me know if you'd be interested in that. Well, anyway, that's what this video is all about. So without further ado, let's get into it. Superconductivity came into the world as a total surprise, without explanation. So I'm not going to try to define it as if it's a normal phenomenon with some boring explanation. No, it's a mystery. So I'll tell you the story of the mystery. Okay, so first of all, something that was known way back in the 1800s, and that you can measure at home, is that the electrical resistance of a thing depends on its temperature. So if you take something, and it can be just about anything, and measure its resistance with an ohm meter while heating it and cooling it, you'll find a trend like so. And this trend has a good common sense physical explanation, When you heat up a thing, the atoms start vibrating more aggressively, and so they're going to scatter the electrons that are trying to flow through. So it takes more effort to push electricity through a thing when it's hot. And conversely, if you cool the thing down, then the atoms relax, and the electrons can go through more easily, without being disturbed as much along the way. One way to imagine this is to picture yourself in a crowded room, but the people are all standing around or walking slowly. Well, you can walk through that room without much effort at all, just like, excuse me, coming through. On the other hand, if you're trying to cross a mosh pit at a heavy metal concert, it'll take a lot more effort. People are crazy in there. They'll push you around, you might catch an elbow, maybe fall down. You might not even make it to the other side. You just have to chug a Mountain Dew and hope for the best. Hope that fate is on your side. So that's why resistance goes up with temperature. And we can explain this graph in a way that makes perfect sense. And even though this story about electrons bouncing around is a simplification, because in reality, of course, the details are more detailed, nonetheless, the story is directionally true and in a meaningful way. It is true that electrons scatter more in a hot material, and so the resistance goes up. Well, so anyway, that tells us something about the material essence of electrons, and their behavior in a material. But then, one question that comes up is, what would happen at super cold temperatures where that thermal scattering effect goes away? Would the resistance approach zero at zero temperature? Or would it asymptote to some non-zero value, or what? Well, that's a good question, and it's worth exploring, because that could tell us something about the nature of electrons and matter, and the nature of things, which is what we want to know. So it would be interesting to measure the electrical resistance of materials at super cold temperatures. And that brings us to the story of Heike Kamerlingh Onnes. Onnes was a professor of experimental physics and the director of the cryogenic lab at the University of Leiden in the Netherlands. He was also a pioneer in the field of low-temperature physics, and in 1908 he became the first person to ever liquefy helium at a temperature of just 4.2 Kelvin, in other words 4.2 degrees Celsius above absolute zero. And that was awesome because once you have liquid helium, you have a way of putting that very cold temperature into a material form, into a substance, and this facilitates all kinds of very low-temperature experiments. So Onnes did a lot of experiments on what happens to materials at very cold temperatures, for example, measuring their electrical resistance as a function of temperature. And in 1911, while measuring the resistance of ultra-cold mercury, he inadvertently opened the Pandora's box of superconductivity. Let's take a look at some actual data from one of his 1911 mercury experiments. We'll put temperature in Kelvin on the x-axis, and on the y-axis, we'll put resistance in ohms. Let's look at the data points in order of decreasing temperature. First, at a temperature of 4.37 Kelvin, we have a resistance of 0.13 ohms. Then, a bit colder, at 4.33 Kelvin, we have 0.127 ohms. And then at 4.23 Kelvin, we have 0.114 ohms. And so far it looks like a linear trend, which is not so surprising, But something really weird happens when we go down to 4.2 Kelvin. Now the resistance is only like 0.01 ohms. And even crazier, if we go down just a little bit colder to 4.19 Kelvin, we get 0.00001 ohms, which is within the sensitivity of the experiment. So for all we know, that may as well be precisely 0 ohms. What? And if you go a bit colder, it's the same thing. The electrical resistance has just somehow magically turned off, which does not make any sense whatsoever. It's crazy. By the way, you can find the original 1911 drawing of this plot in Onnes's paper on the sudden change in the rate at which the resistance of mercury disappears. Link in the description below. Now, at the time of Onnes's discovery, nobody had any idea what was going on here. It was a crazy new phenomenon. But it was clear that there was some kind of phase transition. Something new and exciting and mysterious and weird was happening. And because at first all anyone knew about this phenomenon was that electrical resistance disappeared, naturally they called it superconductivity. But the word superconductivity is actually kind of a misnomer, because there's so much more to this phenomenon than just the lack of resistivity, as we'll see in a moment. Well, okay, so after this discovery, one thing you want to know right away is, are there any materials other than mercury that are able to become superconducting? So Onnes kept studying various materials, and in 1913 he found that tin and lead both go superconducting at temperatures of approximately 4 and 7 Kelvin, respectively. And later on, in the 1920s and 30s, superconductivity was observed in thallium, niobium, tantalum, and vanadium, in all cases with a transition temperature of less than 10 Kelvin. So as more superconducting materials were discovered, that started to add some context to superconductivity. It appeared to be a phenomenon that happened at very, very cold temperatures, just single-digit Kelvin above absolute zero. But aside from that, nobody really knew anything about what superconductivity was or why it even existed in the first place, because it seemed to defy all reasoning and common sense, It made no sense whatsoever. And then the plot thickens, because in 1933, the German scientists Walther Meissner and Robert Aschenfeld discovered something new and profound about superconductors. Superconductors expel magnetic fields. And what it means for a superconductor to expel a magnetic field is that, suppose you're looking at it above the critical temperature, so before it goes superconducting, and in that situation, if you put the material in a magnetic field, the magnetic field can just poke through the material. But when you cool it down below its critical temperature so that it becomes superconducting, then a magical thing happens, and the magnetic field just gets expelled from the superconductor. It goes like boing, I don't know, it just gets pushed out of the superconductor, which is super weird. What is going on here? And even though this effect is super mysterious, it's actually pretty easy to imagine. And the way to imagine it is to pretend that the superconductor is a water balloon. With a water balloon, you have the water in the balloon, but then you also have the thin layer of balloon. And so what happens in a superconductor is the balloon layer, the rubber of the balloon, in that layer you have these supercurrents that are whipped up by the magnetic field that swirl around in a way that kind of mirrors and counteracts the magnetic field so that it can't poke into the balloon. And inside the water of the balloon, there is no magnetic field. And so this is really weird. Other materials do not exhibit this behavior because, if you think about it, in a static magnetic field, that is a magnetic field that's not changing in time and just has some constant strength and constant direction, what a superconductor does when it's swirling up these surface currents is counteracting the magnetic field, but the supercurrents are able to persist indefinitely without requiring any kind of external source of power to maintain. So let's say, for example, if you had some ordinary matter and you wanted to make it do this thing, well, it couldn't because the surface currents would get tired. They would dissipate just like electrical current does. It dissipates in the form of heat unless you're constantly putting power into it. And so we find when reflecting on the nature of the Meissner effect that this effect is contingent upon the material having precisely zero resistance. And this is actually a very nicely measurable thing because if there were any resistance at all, even a tiny amount, the current would dissipate pretty quickly, and the Meissner effect would get tired, and the magnetic field would be able to slip into the material. So if you do an experiment where you show that a superconductor is able to expel a static magnetic field, and you check on it some time later and it's still doing that, it's like, okay, well, we can put a very, very, very low upper limit on any resistance that exists in this material. And so, yeah, for all intents and purposes, if you have a true, pure Meissner effect, that material genuinely does have precisely zero electrical resistance. Which is extraordinarily weird. I can't overemphasize. Electrons are matter, right? They bump into things. You see that in the way that resistance goes up with temperature, right? So how can you have a flow of matter in a material that's made of matter with precisely zero resistance? That defies every common sense notion of what matter is. The profundity of this mystery cannot be overstated. Now, I should emphasize that just because a material has zero resistance doesn't necessarily imply that it is going to exhibit the Meissner effect. So, for example, in principle, you could have a material, hypothetically, that didn't have electrical resistance, but that just didn't do this thing about expelling the magnetic field. So at the time that the Meissner effect was discovered, this genuinely was a new aspect of superconductivity. In addition to having zero resistance, superconductors also expel magnetic fields, and so if we want to understand what a superconductor is, we have to take that into account, and we have to be able to explain that. Now, even though the discovery of the Meissner Effect deepened the mystery of superconductivity and made it more puzzling, it also gave us another piece of the puzzle. It added some depth and some nuances to the mystery, but that also gave people more to work with, another handle to grab onto to try to figure out what was going on here. And sure enough, just 2 years after the Meissner Effect was discovered, the famous brother scientists Fritz and Heinz London came up with a pair of equations that modeled superconductors pretty well, and was a significant step forward in terms of our understanding of how to model superconductivity and the flow of supercurrents. These equations relate the supercurrent density to the superelectron number density, as well as the elementary charge, the electron mass, the electric field, and the magnetic field. The supercurrent density is the same as a current density. It's just that it has to do specifically with these superelectrons, which the London equations don't tell us anything about as far as why they exist or how it can be that they have no resistance. That's still very mysterious, but, suppose there are some superelectrons that can slip through a material without any resistance, well then the supercurrent density is going to be the current density of those superelectrons. Oh, one of the great things about the London equations is that it deals with the elementary charge squared. I don't know about you, but whenever I see an equation in electromagnetism where there's the E, I'm always like, wait a minute, is this the positive absolute value of the elementary charge? Is this the electron's charge, which is negative? I make so many sign errors because of that, but fortunately, when it's squared, it's positive. Okay, so if we look at the first London equation, this one tells us that the way the supercurrent density field changes in time is proportional to the electric field in the superconductor, times a proportionality factor that depends on the superelectron number density, the electron's charge squared, and the electron mass. And if we look at the second London equation, this one tells us that the curl of the supercurrent density field is equal to the negative of the magnetic field times the same proportionality constant. And so what that equation tells us is that if you try to put a magnetic field into a superconductor, it's going to swirl up some swirly supercurrents. And the more magnetic field you try to put in, the swirlier those currents are going to be. And that we can use to understand the Meissner Effect. But before we get into the second London equation, first things first, let's take a closer look at the first London equation. So the first London equation tells us that the time derivative of the supercurrent, oh, by the way, now I'm calling it J. We don't have to say J sub S all the time. It's okay. In a superconductor, when you're talking about current, you're talking about supercurrent. Okay, so the time derivative of the supercurrent is directly proportional to the electric field. So the first thing you want to do when you see an equation like this is be like, okay, well, suppose we put some electric field in a superconductor. What happens? Well, if the electric field is constant, then the supercurrent is going to be constantly increasing and increasing and increasing and increasing. And oh my gosh, this is too much supercurrent. What is happening? How could this possibly be? This is crazy. It's just going to go to infinity. So what happened here? Is the London equation wrong? No, we just used it wrong. We made a false assumption that you can have a constant electric field in a superconductor. You can't. What happens if you try to put an electric field in a superconductor is at first the supercurrent is going to increase and increase, but it can't do that forever. Eventually it's going to max out, and actually what's going to happen is the supercurrent is going to reach some steady state situation, at which point it's no longer changing in time. And so by the first London equation, if the supercurrent is no longer changing in time, then the electric field must be zero. And in this way, a supercurrent is able to swoop away the electric field. So the electric field starts off non-zero, it whips up a supercurrent, the supercurrent reaches a steady state, the supercurrent's time derivative then is zero, the electric field therefore is zero, it's been swooped away. So that is a very interesting equation, but it makes sense when you think about it, because if a superconductor can't sustain an electric field, then it can't sustain a voltage drop, and so in a quasi-equilibrium steady-state situation, everywhere in a superconductor is going to be the same voltage. With a superconductor, even when the electric field is zero, that just tells you that the supercurrent isn't changing in time. So you can have a supercurrent that persists and keeps on doing whatever it was doing, even in the absence of an electric field. So in the absence of a driving impetus to keep the current going, it just keeps going all on its own. And so yeah, in the first London equation, we see that a superconductor has zero electrical resistance. All right, well, now let's take a look at the second London equation. This one says that the curl of the supercurrent density is equal to the magnetic field up to a negative proportionality factor. In other words, if you try to put a magnetic field into a superconductor, that's going to swirl up some supercurrents, which is a part of the whole thing about the Meissner Effect, you know, how swirly currents in the water balloon mirror and expel an applied magnetic field. But to really see how the London equations imply the Meissner Effect, we have to pull in another principle from electromagnetism, which is Ampere's law. In the last video, a couple hours in, we derived Ampere's law by relaxing the QED Lagrangian with respect to variations in the photon field and its spacetime derivatives. And we did that using Gaussian units, which is the easiest system of units for seeing how electromagnetism blossoms from local phase symmetry. But anyway, the London equations are often written in SI units, so let's go ahead and convert from Gaussian to SI. And actually, while we're doing that, let's also notice that in a quasi-equilibrium situation where we let the superconductor relax for more than a few nanoseconds, the electric field becomes zero by the first London equation, right? It gets swooped away, and so the electric field term vanishes from our equation. And then we can go ahead and solve for the supercurrent density vector J, while on the right-hand side, what would have been a factor of c over 4 pi in Gaussian units becomes a 1 over mu naught in SI units, where mu naught is the magnetic constant, also known as the permeability of free space. Now, what is this equation telling us? Well, never mind the mu naught factor, that's just a number, and all that number does is it stretches the vectors, but it doesn't change their direction. So the main insight in this equation is that the supercurrent density J gives rise to a curly magnetic field B. And you learn about this in electromagnetism, where if you point your right thumb in the direction of the current density vector, then your fingers curl around like the magnetic field. So let's consider these two equations at the same time. Do you see the beautiful interplay between these equations? Forget about the constants, those are just numbers. The equation on the left says that the curl of J is proportional to B, up to a minus sign, and the equation on the right says that the curl of B is proportional to J. So which field is really the curl of which other field? Yes, they both are. These two equations exist in a seemingly paradoxical tension, and so it's not too surprising that they'll have the effect of turning off the magnetic field within a superconductor. Without doing any math, that's one of the things we might expect to come out of these equations, that the magnetic field should be turned off. But let's convince ourselves of that. Well, first things first, we can plug the equation on the right into the equation on the left by substituting that 1 over mu naught curl of B in for J. And now we see quite a bizarre equation. Again, ignoring the constants, it's basically saying that the curl of B is proportional to negative B. Huh? What? How can the curl of a thing be proportional to the thing? What a strange field. And let's not forget that B is really just a notational or linguistic shorthand for the curl of the magnetic vector potential A. So really, this equation has a triple curlception on the left and a hidden curl on the right. What a dizzying equation. If you feel dizzy right now, good, that's a good thing. That means you are properly appreciating the swirliness of this equation. So where do we go from here? Well, fortunately, we can invoke a very convenient vector calculus identity, which says that the curl of a vector field is equal to the negative Laplacian of the vector field, plus the gradient of the divergence of that field. And that's not physics, that's pure math. It's one of those things that you just have to look up in a table, or maybe memorize if you use it a lot. Or if it's a rainy day and you're looking for a miserable activity, you can prove it by writing everything out in terms of derivatives and doing some pattern matching. Alright, so if we look at this equation, the term on the right involves the divergence of the magnetic field. And, being good electromagneticians, we know that the divergence of the magnetic field is zero, because B is secretly nothing more than the curl of the vector potential A, and the curl of a vector field doesn't diverge. So that's Gauss's law for magnetism, and it lets us delete that divergence term from the equation. So now we can replace the curl of B with simply the negative Laplacian of B. When we do that, we find that the Laplacian of B is proportional to B, up to some constants, and we can clean up those constants by moving everything on over to the right side of the equation. And actually, we can go one step further with our housekeeping by defining this parameter lambda, which is the square root of m over mu naught ns e squared. And then we can interpret this equation as saying that B is the kind of field where, when you take its Laplacian, that has the same effect as simply multiplying the field by 1 over lambda squared. By the way, if you're an eigenperson, you can imagine that B is an eigenfunction of the Laplacian operator with eigenvalue 1 over lambda squared. Well, anyway, the Laplacian operator is the kind of vectorial generalization of the second derivative. So if you just plot things out along one dimension, and imagine the Laplacian as the second derivative of some component of the magnetic field along that dimension, then you find that the magnetic field drops off as e to the negative x over lambda. And you can prove that by taking the second derivative of that exponential. So this lambda parameter is the length scale over which some magnetic field outside the superconductor will drop off within the superconductor. In other words, lambda is the thickness of the water balloon material. Of course, it's not a sharp boundary, even at just half a lambda away from the surface, the field is already noticeably attenuated. And if you go a few lambda into the superconductor, well, you'll still find a little bit of field in there, but not much. Lambda is the order of magnitude length scale in which the magnetic field is being expelled by all of those swirly surface currents. So yeah, the thickness of the water balloon. By the way, I remember this because lambda kind of looks like an upside-down slingshot, and when I was a kid, we used to slingshot water balloons at each other. So this lambda thing is called the penetration depth of the superconductor, and it's a material property that can depend on the conditions of the situation. Typically, lambda is between 50 and 500 nanometers, so pretty small, about 100 to 1,000 times thinner than a human hair. Okay, so the reason we just did this analysis is to see how the London equations give us an analytical handle on the mystery of supercurrents and the Meissner effect. Even though these equations are just phenomenological and they raise as many questions as they answer, at least they're a good starting point, and they give us this concept of penetration depth lambda, which is still a useful concept even today. Okay, so you might be wondering, where do the London equations come from, and why are they what they are? Well, back in 1935, the answer was basically, we don't exactly know, but the equations seem to work, and so they're phenomenological equations. However, they're not completely arbitrary, so they can actually sort of be derived from deeper principles. Although, if we're being technical, this is actually a pseudo-derivation because we have to kind of make some illegitimate moves here and there and put in a little bit of mystery, and so anyway, it's worthwhile to see this pseudo-derivation so we can see what the London equations are really telling us. Okay, so to start off, we can write out the supercurrent density in terms of the number density of superelectrons, the electron's charge, and the superelectron velocity vector. And this is just the idea that the current has to do with how many electrons are there and how fast they're flowing. But then we can write out the velocity vector using the velocity operator, which is basically just the idea that momentum is mass times velocity, solved for velocity, but then also instead of just the kinetic momentum p, which is mass times velocity, we also want to add to it the product of the electron's charge and the magnetic vector potential. And this is the way in which the vector potential augments the momentum of an electron. So this is known as the principle of minimal coupling, and as we saw in the last video, the fact that A augments the momentum of charged matter is really a core part of what A is and why it even exists. Okay, so this quantity P plus EA is known as the canonical momentum. And so far we haven't had to make any weird, sketchy assumptions. But let's go ahead and make a weird, sketchy assumption. We're going to assume that for some reason, the kinetic momentum of the superelectrons is 0. That's very strange, because you would think that the kinetic momentum should be non-zero, but okay, whatever. Suppose that it's 0, and we're just making this up. We'll leave this as an unexplained mystery for now. Now, we have to be careful because when we impose by fiat that p should equal 0, you never know what this might mess up with the other variables in our equations, right? So another thing we're going to do is the vector potential A, we're going to write this now as A tilde. And the tilde is just there to signify that, hey, we have to be careful with this vector potential A, because we don't know exactly why the kinetic momentum should be 0, and we don't know exactly what that's going to do regarding A and the behavior of A and the constraints on A. So imagine that the tilde just represents like a curiously raised eyebrow. It's like, okay, what is with this weird vector potential? Now, if we look at these two equations, we can smush them together and come up with an expression for the supercurrent density in terms of this weird vector potential A tilde times some constants. And this right here is actually the two London equations in one equation. We can see this by writing out the definitions of the electric and magnetic fields in terms of voltage and the vector potential, as we saw in the last video, right? Remember the 6 ways? So when we do that, the first thing we'll do is say, you know what, we're in a superconductor, so in quasi-equilibrium, we're not going to have voltage gradients. That's going to get swooped away. And the expressions shown here for E and B are in Gaussian units, but to convert to SI, we can just delete that factor of 1 over C. So then from this one equation involving J and A tilde, we can recover the first London equation simply by taking a time derivative of both sides. And we can recover the second London equation simply by taking the curl of both sides. So what this really tells us is that the London equations, in essence, are just the statement that in a superconductor, for some reason, the supercurrent is directly proportional to this magnetic vector potential. And that is very, very strange, because usually the magnetic vector potential is not a directly observable quantity. But supercurrent and current in general is an observable quantity. So if these things are directly related up to some proportionality factor, then that means that this weird vector potential A tilde is actually directly observable. So that's kind of strange, and you can imagine that in order to get this math to work consistently, we have to put some guardrails on it. We have to impose some structure to prevent these equations from breaking down and giving us nonsensical results. And as we'll see later, we can derive these guardrails from deeper principles. But for now, just think of them as a result of having to keep the math consistent after imposing this constraint that the kinetic momentum has to be 0. Well, anyway, the first condition is that the divergence of A tilde should be 0. This is the Coulomb gauge condition, but in this context it has extra meaning because it also implies that the divergence of the supercurrent is going to be 0. And that can actually be regarded as a continuity equation on the supercurrent. Now also, we have the constraint that A tilde should equal 0 in the bulk of the superconductor away from the surface. And this constraint is compatible with the Meissner effect. So this has to do with the expulsion of magnetic fields in the interior of a superconductor. And finally, we have the constraint that A tilde should be tangent to the surface of the superconductor. Another way of saying that is that the dot product between A tilde and the surface normal vector should equal 0. So if A tilde is perpendicular to the surface normal, then it's necessarily tangent to the surface. And what that implies is that currents are going to be swirling around the surface, but are not going to be accumulating onto the surface. Now I want to reflect on this for just a moment before we move on. So the London equations are telling us that the supercurrent J is proportional to this mysteriously gauge-invariant vector potential, and that this fact is a direct result of the superelectrons somehow having no kinetic momentum. And that's very strange, and it makes us wonder, how can that be? Are the superelectrons somehow all locked together in a rigid quantum state with no kinetic momentum? I mean, how can this possibly be, So the reason I bring this up is to show you that the mystery at the core of the London equations really all boils down to, why is it that superelectrons seem to have no kinetic momentum? Or at least in my opinion, that is the most intriguing question that we get out of the London equations, given the knowledge known back in 1935. And also, if we think about this from a more modern gauge-theoretic perspective, the London equations are based on the idea of the magnetic vector potential being gauge-invariant, meaning directly observable, meaning there's extra reality to it than we normally expect from a vector potential. And that necessarily means that there's something going on in the superconductor that is modifying the way that we normally think about phase symmetry and electromagnetism. And that's going to be a theme that we're going to explore in depth later on in the video, especially as it pertains to the Anderson-Higgs mechanism. Okay, so where are we now? Well, we have seen how the London equations give us a pretty decent description of superconductivity, but guess what? In 1935, the same year that the London equations were published, there's also another dramatic experimental plot twist. And that is the discovery of a whole new type of superconductors, which exhibit behavior that the London equations do not explain. And that brings us to the story of Lev Shubnikov. Lev Shubnikov was known as the founding father of Soviet low-temperature physics. And he actually worked in Onnes' lab in Leiden back in 1926 to 1930. This was actually just after Onnes' time there. When he was there, Onnes had already retired and unfortunately had passed away. But during that time in Onnes' lab, Shubnikov and another scientist, Wander Johannes de Haas, I hope I'm pronouncing that right, discovered the Shubnikov-de Haas effect, which provided direct evidence for something known as Landau quantization, which we're not going to get into today, but point is it was a pretty cool discovery. But anyway, so after that, in the mid-30s, Shubnikov went on over to Ukraine and started his own low-temperature lab at the Ukrainian Physics and Technology Institute, the UPTI. And there, in 1935, he discovered a whole new type of superconductivity in single-crystal lead thallium. And in 1937, he discovered another example of this new type of superconductivity, this time in lead-indium alloys. So the discovery of type 2 superconductivity is a pretty legendary thing, it's a big deal, and Shubnikov is rightly known as one of the heroes of superconductivity. But Shubnikov was a really accomplished scientist even beyond his work on superconductivity. For example, in 1936, he, along with his wife, Olga Trapeznikova, and the legendary Lev Landau, discovered antiferromagnetism. Oh, and yeah, so we're not going to get into the story today, but, this was just one of the terrible tragedies of history and physics. In 1937, you had Stalin's terror, and if you want to look into something called the UPTI affair, look into the Coherence Landau leaflet. You can read about what happened there. I really don't know what I can say about that today, or, this is not really the right video for telling that story, but we can only imagine what other discoveries Shubnikov might have made. But you know what? To honor his memory, let's go ahead and talk about type 2 superconductivity, okay? Because the people that took away everything from him, they didn't take away his legacy. Okay, so to understand what a type 2 superconductor is, first let's talk about type 1. So a type 1 superconductor is just a regular old superconductor, like the kind of superconductor we've been talking about so far, where it only has two phases, either it's superconducting or it's not. And you can draw a phase diagram if you put temperature on the x-axis and magnetic field on the y-axis. Then there's going to be a curve in that space that separates the superconducting phase and the normal phase, because superconductivity can only occur when the material is sufficiently cold and also in a sufficiently gentle magnetic environment. But if you overwhelm the superconductivity either with temperature or with an extremely strong magnetic field, then the superconductivity is going to break down and the material becomes a normal material. But the problem is, we don't just have type 1, we also have type 2. So what's the deal with the type 2? Well, it's very similar to type 1, except in addition to the superconducting phase and the normal phase, now you also have this mixed phase. And what the mixed phase is the material still has zero electrical resistance. So it's still superconducting in that sense, but it no longer exhibits a complete Meissner effect. Instead, what happens is actually some of the magnetic field is able to poke through the superconductor. And at first glance, you might think, okay, big whoop, what's the big deal? I mean, it doesn't look that surprising or astonishing. But the thing to appreciate about this is it's not just that type 2 superconductors kind of fade in between superconducting and normal like a nice smooth transition. No, it is two transitions. There is a phase that's purely superconducting and purely exhibiting the Meissner effect. But then if you apply a strong enough magnetic field, all of a sudden, some of the magnetic field is able to start to poke through the material. Not all, but some. And the onset of that effect is sharp enough to constitute its own phase transition, okay? So mixed is not just like a combination of superconducting and normal. No, it's really a different kind of thing. And then if you go up to an even higher magnetic field, even the mixed superconductivity breaks down, and you notice that as a sudden onset of electrical resistance. And so when you think about the two transitions, and the material's ability to let some of the magnetic field poke through, and then you think about everything we've talked about so far, about the London equations, and the Meissner effect, and the water balloon, it's like, okay, hold on now. No, this is different. Something weird is going on here. This is like a whole nother chapter in the story of superconductivity. It's like, what the heck? Now we have type 1 and type 2. Like, oh my gosh. As if this phenomenon couldn't get any more mysterious. And just to emphasize, the London equations do not explain the existence of the mixed phase, also known as the Shubnikov phase, in honor of Shubnikov. Because, in the London equations, there's some fancy equations, but they're not that fancy. Really, it's just the idea that the supercurrent is proportional to this mysteriously gauge-invariant vector potential. And that's all fine and good, but it doesn't have the necessary structural richness to it to explain what the heck is going on in the mixed phase. So now we're about to dive into the theory around what's happening there and how we can model it and how we can understand both type 1 but also type 2 superconductivity and the mixed phase and all of that. But before we do that, we have to jump ahead into the future because I want to show you some experimental data, or really just a picture, that'll help us make sense of what a type 2 superconductor is. And then that's just going to make it way easier to get into the theory because we'll have a picture in mind that's going to help us out. Okay, so if we skip ahead to the modern era, we can take a look at a type 2 superconductor in a magnetic field. What the picture shows is a very thin type 2 superconductor that we're looking down on from above. So let's say the plane of your screen right now, let's call that the XY plane, and we're looking at that from the Z direction. And what we're looking at with all those little dots is that each one is actually a quantum vortex of supercurrent. So imagine that, well, you know what? It's like this. Imagine you're in a hot air balloon above Oklahoma, and you look down and you're like, oh no, it's a tornado, like one tornado, right? Well, the thought that's going to cross your mind is, man, I picked the wrong day to go hot air ballooning. But you're not going to have like an existential crisis in terms of like the tornado breaking your sense of reality. No, it's just going to invoke a sense of danger. But now imagine instead if you look down on the beautiful fields of Oklahoma and you see a bunch of little tiny tornadoes, and then you take out your binoculars, and because of course you brought binoculars, and you look at them closely, and you see that each one of these little tornadoes has the same exact amount of swirliness. It's as if they've been copied and pasted all over the beautiful fields of Oklahoma. Now that's a different kind of predicament, because maybe it's not so dangerous to be flying above a field of little tornadoes, I don't know. But one thing I do know for sure is that's going to make you question your sense of reality, because you're going to be thinking, hold on now, how is it that there's a whole bunch of these little tornadoes and they're all swirling by the same amount? Now, obviously, this scenario I'm describing with the beautiful fields of Oklahoma filled with these quantum tornadoes, such a thing is preposterous and absurd, and so you don't have to contend with it in a very serious way. However, this thing with the superconductors is actually real. So yeah, it's smaller and it's less perilous, but like, look at this picture, okay? Like, look at it. These are quantum vortices of supercurrent. Each one contains a single quantum of magnetic flux. And the flux quantum, this quantity has been measured to 10 parts per billion. And for whatever reason, when you look at a type 2 superconductor in a magnetic field, in the mixed state, when the magnetic field is able to start poking through, it does so via these flux vortices. That's how the magnetic field is able to poke through, because each flux vortex carries one flux quantum of magnetic flux, and so it's the number of vortices you have times the flux quantum is the total amount of magnetic flux that's going through the material. But in between that, you still have the superconducting condensate doing its thing, so you can still pass a current along this material. So yeah, that is the mixed state of a type 2 superconductor. And I just bring this up to give us some context, right? So the superconducting state, there's no vortices. The mixed state, you have some vortices. And then the normal state, the superconductivity just breaks down. There's no supercurrent, there's no vortices. And the thing that we now have to explain is, How can we have such a preposterous thing of quantum flux vortices? That's question number one. Question number two is, why do some superconductors have them and some don't? But then also, how can we explain this in a way that builds upon and expands the London equations? Because we know the London equations work pretty well for type 1 superconductors. So whatever our explanation is for type 2, it has to be compatible. It has to be reducible to the London equations in the appropriate scenario, right? So that gives us some sense of what we're trying to do. So let's do it. We're going to travel back in time now, not all the way to 1935, but to 1950. That is when there was a big theoretical breakthrough in superconductivity. So in 1950, the legendary physicist Lev Landau, along with another great physicist, Vitaly Ginzburg, came up with the Ginzburg-Landau model of superconductivity. And to this day, the Ginzburg-Landau model is what you use to understand the flow of supercurrents and their behavior in an electromagnetic field. So the equation shown here is like the heart of their model. This is the free energy density of a Ginzburg-Landau superconducting condensate. I know it looks a little complicated, but we're going to break it down bit by bit in a moment, and you'll see that it's actually not so bad. And actually, the Ginzburg-Landau model is really based on one idea, which is that inside a superconductor, there's going to be a Schrödinger-like wave function, and it's going to obey pretty much the same laws as the Schrödinger equation, but it also kind of wants to repel itself. So we're going to model the state of the superconducting condensate with a complex-valued scalar field. Now, before we go further, we have to think, wait a minute, what are we really saying here? Are we saying that all of the superelectrons are in the same quantum state? Yeah, that's what we're saying. And that should be a deal breaker right from the start. You should hear that and be like, no, you can't do that. You can't do that at all. Because why? Because electrons are fermions. Fermions are half-integer spin particles. According to the spin statistics theorem, if a particle has half-integer spin, then it's antisymmetric under particle exchange, and therefore is going to obey Fermi-Dirac statistics, and therefore you have the Pauli exclusion principle. And that's the principle at the core of the stability of chemistry and matter as we know it. This is not some flimsy principle. You can't just do away with the Pauli exclusion principle. And yet, at first glance, it seems that the Ginzburg-Landau model does exactly that. Alright, so why would we even entertain such an outrageous idea in the first place? Well, because it turns out that the Ginzburg-Landau model and the equations involved are able to derive the London equations from deeper principles and explain type 1 and type 2 superconductivity and explain flux quantization in superconductors, and basically, it's right. Like, it's the right answer, okay? So it works. And it explains experiments. So it is actually a really effective model at explaining superconductivity, but you do have to wonder, how can it be that you have all these electrons in the same quantum state? But we'll come back to that question later. First, let's explore the Ginzburg-Landau model. Alright, so let us derive the laws of physics for our superconducting condensate. Our derivation is going to be based on the idea that the laws which govern the superconductor can be derived from the energy contained in our wave function psi, as well as the electromagnetic field, and also the interaction of our wave function with the electromagnetic field. So the condensate and the electromagnetic field are going to do whatever they have to relax their energy to the minimum possible value. Now, for everything that follows, we're going to assume that the superconductor has just a little bit of time to relax into a quasi-equilibrium situation. And so all we mean by quasi-equilibrium is that we're not going to worry about super high-frequency transient situations. In all of this analysis, we're going to assume that the condensate has a few nanoseconds to relax into its low-energy configuration. Okay, so what we're looking for is an equation that gives us the free energy density of the system, which is the local free energy per unit volume, as a function of something that depends on the wave function psi, as well as some electromagnetic stuff. Okay, but then the question becomes, what should that equation be? Well, first of all, there's going to be some energy associated with the condensate density, that is, the number of superelectrons per unit volume, so that if you have more or less of the condensate, this energy term in the equation is going to be bigger or smaller. And we can write this as alpha times the amplitude of psi squared, where alpha is some material property that by definition gives us the amount of energy contained in the condensate density, And the absolute value of psi squared is, by definition, the condensate density, that is, number of superelectrons per unit volume. And then, of course, there's some other stuff that we're going to include as well, but for now, let's focus on this term. Well, if you make a plot where the absolute value of psi is along the x-axis with 0 on the left, and on the vertical axis, you plot alpha times the absolute value of psi squared, well, if alpha is a positive number, then you're going to end up with the green curve shown here, and as the free energy minimizes, that's going to push the absolute value of psi to 0. And so if alpha is a positive number, psi doesn't want to exist. However, if alpha is negative, then it's a different situation. See, because then you end up with this purple curve, where now psi wants to be as big as it can be. Because a negative alpha means that the more psi you have, the lower and lower the free energy is going to be. Well, of course, there has to be some kind of limiting principle that's going to stop psi from running away to infinity, right? Well, yeah, so as it turns out, there's also going to be an energy due to the condensate's self-interaction, and that is going to provide the limiting principle that prevents the amplitude of psi from running away to infinity when alpha is negative. Now, the way to think about the self-interaction term is that it depends on how much condensate density you have somewhere, so that's psi squared, but then it also depends on how much condensate density you have there for the condensate density there to interact with the condensate density that is there. So you have another psi squared, and you end up with a psi to the fourth. And so what this is an energy that has to do with psi not wanting to exist around itself. So we can put a number on this, beta, and actually we'll go ahead and use beta over 2 so that we end up with a cleaner equation later on. It doesn't really matter. But anyway, this factor is a material property that sets the strength of the self-interaction, that is, the energy per condensate density squared. Now, when alpha is positive, even with this beta term, we're still not going to have any superconductivity. But now, for the case that alpha is negative, this beta term comes in as a limiting principle to prevent psi from running away to infinity. And so therefore, in the case of negative alpha, the free energy density is going to be minimized at some optimal value of the absolute value of psi. And that is what determines the density of a superconducting condensate. And that can be calculated with freshman calculus, because all you have to do is think about this equation in terms of the condensate density rho, where then the free energy is alpha times rho plus beta over 2 rho squared. Well, then the minimum point occurs where the slope is 0, and so all you have to do is take a derivative of the free energy density F with respect to the condensate density rho, set that equal to 0 to find the minimum, and when you do that, you find that rho is going to be the absolute value of alpha over beta. And so therefore, the absolute value of psi is going to be the square root of the absolute value of alpha over beta. Now I use absolute value here because bear in mind, alpha is going to be a negative number for a superconductor, and beta is always going to be positive. So by saying absolute value of alpha over beta, what that really is the ratio of how much the superconductor wants to exist, divided by how much it doesn't want to exist with itself. And so it makes sense that the condensate density would be that ratio. So you see now why we started with beta over 2. It's so that we don't end up with a 2 in this equation. You can think of beta as basically being a constant positive number, but alpha changes as a function of temperature in a really significant way. So if you look at the plot on the left, you can see that alpha becomes a lower and lower number as the temperature decreases. You go to a high temperature, you end up with positive alpha. You go to a low temperature, you end up with negative alpha. Now the curve shown here is something of an idealization. In reality, it's kind of a little messier than this, but this curve applies pretty well near the transition point, where alpha equals 0. And that transition point, where alpha equals 0, that's the critical point where if you go up to a higher temperature, then alpha becomes positive, and now it costs energy to have a superconducting condensate, and so the condensate doesn't form, and you end up with a normal material, not a superconductor. But if you go below the critical point, then alpha becomes a negative number, and so therefore there's negative energy associated with the formation of the condensate, and so the condensate is going to spontaneously form, and so the material will be superconducting. If you subcool the material below its transition temperature, then your alpha value is going to be more of a negative number, and so there's going to be more of an energetic incentive for the condensate to form. So that's why if you subcool a superconductor well below its transition temperature, you'll end up with a denser condensate. And remember, as we saw just a moment ago, the optimal value of psi is going to be a trade-off between psi wanting to exist, right? There's that alpha term that makes psi want to be non-zero. But if psi is too big, then the beta term becomes dominant, and you would have to put in more energy to bring in more psi because it doesn't want to exist with itself. So the actual value of psi that the superconductor is going to take on will be that optimal point that minimizes the free energy density at a value of the square root of the absolute value of alpha over beta. And so in this way, you can see how the condensate density becomes non-zero when alpha goes negative. But remember, psi is a complex valued field. So in addition to its absolute value, it also has a phase. And the question is, what is the phase of psi? Well, if you look at the alpha and beta terms, these only have to do with the absolute value of psi, so they don't care about the phase at all. And as we'll see later on, the rest of the Ginzburg-Landau free energy density equation, it does care about phase gradients, but it doesn't care about the absolute phase. But because psi is going to have a non-zero absolute value, its phase has to be something. And the way to see this is, suppose we put the complex plane horizontal, and on the vertical axis, we'll put the free energy density pertaining to those alpha and beta terms. And you can see that if we bring the superconductor down below its critical temperature, so that the alpha term goes negative, we end up with a kind of sombrero-shaped function in the complex plane. And while we can predict the absolute value of psi by minimizing the energy, the phase is going to be just randomly selected to be just some random phase. And so even though the equations are symmetric with respect to the phase degree of freedom, the fact that psi needs to take on some non-zero amplitude is going to force it to pick out a particular phase. And this is the essence of spontaneous symmetry breaking. And there's a subtlety here, which is that this spontaneous symmetry breaking, one of the things that this relies on is the idea that phase gradients are going to cost energy. And so the phase of the condensate is going to want to align coherently from one place to another. And so in this animation, you see that dot. What that dot represents is the phase angle picked out by the condensate as the material goes superconducting. And the fact that there would be an energy cost associated with phase gradients is what keeps the phase at one place in the condensate the same as at another place. Okay, but now there's a very subtle principle that we have to keep in mind, which is global phase symmetry. So when we're doing quantum physics and we're using complex numbers, we're really just using complex numbers as a kind of number that can roll around. And so the absolute phase doesn't really matter so much as phase gradients, right? Phase gradients are what encode momentum and energy. And so we're always free to define what we mean by a phase angle of zero. And one way to imagine this is if you want to use a complex number to track the phase of the moon, you can use e to the I omega t, where omega is the angular frequency of the moon, and that complex number is going to evolve at the same rate as the phase of the moon evolves, but it's up to you what you want the phase angle of zero to correspond to. You can say, okay, phase angle zero is going to be a new moon or a half moon or whatever it is. And so as part of setting our coordinate system, we're always allowed to say what we mean by a phase angle of zero. And so when you're dealing with a superconductor, it does spontaneously pick out a particular phase. But as a matter of convenience, we can set that phase angle equal to zero. And that doesn't diminish the physical implications of spontaneous symmetry breaking. But it's weird, right? Because it's like, okay, hold on, we got to parse two different things here. Like there's the fact that the material is actually picking out a particular phase, combined with the fact that we have the freedom to decide what we mean by zero phase, okay? So like, what is the interplay between these concepts? And so I was trying to think of a way of explaining this, and I was in the shower, and I was looking at the water, and I'm like, okay, water flows, and supercurrent flows, and soap is clean, and math is clean, and then I'm like, no, it's not working out. The wisdom of the shower has let me down. But then I turned and I looked at the shower wall with the tiles, and I had this epiphany of like, oh yeah, that's the thing right there. That's how it is. Because imagine if you had a bunch of tiles that were superconducting, and you cool them down and you let them all condense, and each one is going to pick out a particular phase. And when you consider multiple different superconductors, that's when you really see the essence of spontaneous symmetry breaking. And when you see this, and then you think about the fact that we have the freedom to choose what we mean by zero phase, you realize it's like, oh, okay, yeah, I mean, we can rotate the definition of zero phase, and that sort of uniformly would rotate all these different phases. But that's kind of not super important. I mean, it's sort of like if you have a crystal with multiple different crystal grains, and you rotate your head, and you're deciding what you want to call your X and Y axis. You know what I mean? It's like, that doesn't actually change the relative orientations of the crystal grains relative to one another. And likewise, a global U1 redefinition of what we mean by the phase is not going to change any of the phase gradients in our superconductors. And so all of these different options for how we want to globally define our phase angle are going to lead to exactly the same physical description of the system. Oh, let me mention a concept in passing, and I'm not going to linger on this, it's a big topic, but while we're here, imagine two tiles that are next to each other, and they have a different phase. Just to give you a feel for what that phase difference means, well, if the two tiles are totally insulated and not connected to each other, and spaced apart a little bit, then each one is just going to have whatever phase it has. But if you bring them together close enough, and maybe you put some material in between, eventually what happens if they're very, very close together is that the wave functions of the condensate are going to overlap a little bit, and you're going to get a kind of quantum tunneling effect where the two different superconductors are going to feel each other, and that's effectively a phase gradient from one place to another, and so that's going to drive a current across that gap, across that junction. And what you find, because you can do this, by the way, you can make superconductors and put them real close. And what you find is that there is a current that goes across from one superconductor to another, which is proportional to the sign of the phase difference across the two superconductors. So if you make a plot of the current versus the phase angle difference, what you find is that if there's no phase angle difference from one superconductor to another, then there's no current, because there's nothing to drive that current. But then if you get a phase angle difference of, say, 90 degrees, then you're going to get current flowing from one superconductor to the other. Now, if you have a phase difference of 180 degrees, the current doesn't know which way to go, so you get zero current again. If you have a 270 degree phase difference, then that's just like 90 degrees, but actually now it goes the other way, so you have current flowing in the opposite direction. And then if you have a 360 degree phase difference, well, that's really not a phase difference at all, so then you have no current. Oh, whoops, I almost forgot to turn on the bubbles. So yeah, you see that there's really an observable effect that has to do with these phase differences. And that tells us that this thing about spontaneous symmetry breaking is actually real and does actually have some physical consequences. By the way, this is known as the DC-Josephson effect. But let's talk about that more some other day. I only bring it up in passing as an example of the reality of superconductors picking out different phases. But for the rest of the video, we can actually imagine dealing with only one superconductor. Okay, so we don't have to worry about the phase difference from one superconductor to another. But one superconductor can have phase gradients within itself. And that brings us to the kinetic part of the Ginzburg-Landau free energy density. Okay, so gradients in the phase of psi, and in fact gradients in psi more generally, have something to do with current and momentum and kinetic energy. And we can understand all of those dynamics by precisely defining how our wave function psi and our vector potential A contain kinetic energy. So we're going to start off with the principle from Newtonian physics that kinetic energy is momentum squared divided by twice the mass. And that's the same principle that we used in Hydrogen Part 1 to construct the Schrödinger equation. Just as in that video, we're going to bring in the momentum operator p hat acting on psi, which by definition is negative I h bar times the gradient of psi. But here we're also going to pull in the vector potential, and we can go ahead and slap that right onto the momentum operator with negative E star over c times the vector potential A times psi. That is known as the principle of minimal coupling. And as we saw in the last video, the vector potential A's ability to affect momentum in this way is central to its definition as the gauge field that offsets the kind of local phase transformations that we can do with our wave function psi. And we'll talk more about that later on in this video. Oh, and in this equation, E star is the effective charge of a superelectron. And as we'll see later on, that's actually going to be twice the electric charge of an electron, because superelectrons are really secretly electron pairs. But we'll talk more about that later. Okay, so then to assemble the kinetic energy density, what we're going to do is we're just going to plug in the definition of the momentum operator into the equation about kinetic energy. And when we do this, we find that the kinetic energy density is 1 over 2m star times the magnitude squared of negative I h bar gradient of psi minus E star over c times the vector potential times psi. And so all that is the combination of those two principles. Notice here we're using m star instead of m, and so m star is the effective mass of a superelectron. And that might take on different values because, bear in mind, we're not dealing with a free electron in empty space, we're dealing with superelectrons inside of a material. But in your mind, you can imagine m star as playing exactly the same role as m from the Schrödinger equation. And so you don't really have to worry about its numerical value today. It's more about the concept and the role that it plays in the equation. Alright, so then if we write out what we have so far for the Ginzburg-Landau free energy density, we have this term with the alpha and the beta, and now we also have this term which encodes the kinetic energy density of the condensate in the magnetic vector potential A. Now then, we have one other kind of energy that we have to account for, and that is the energy contained purely within the magnetic vector potential. So to do this, we're going to borrow an idea from the last video, where we saw that the electromagnetic field strength tensor contributes to the quantum electrodynamics Lagrangian as negative f mu nu over 16 pi. And you find, when you pick out a particular reference frame, that you can write this term as 1 over 8 pi times the difference in the magnitude squared of the electric field and the magnetic field. Now, in a superconductor, the electric field is 0 in quasi-equilibrium, because it gets swooped away. And if we translate from a Lagrangian framework to a free energy framework, we're going to drop the minus sign on the magnetic field term. And then remembering that the magnetic field B is just the curl of A, what we find is that the energy density contained in the vector potential is simply 1 over 8 pi times the magnitude squared of the curl of the vector potential A. And that right there is the Ginzburg-Landau free energy density. So the condensate is going to do whatever it has to do in order to minimize this equation. And so that minimization principle is at the core of the Ginzburg-Landau model. And if we can understand what has to be the case about psi and A in order to minimize the free energy density F, or technically in order to minimize the free energy, which is F integrated over space, then we can derive some governing equations for psi and A. Now that derivation is very long and complicated, and it would take us too far afield for this video, so we're not going to get into the details there. But in essence, this is just like your standard Euler-Lagrange situation, where you have some functional that you're trying to minimize with respect to different field configurations. And when you do that, you can convert an equation involving, in this case, the integral of f over space, into a set of differential equations in psi and A that give you the conditions that psi and A must satisfy in order to minimize the free energy density F. And these differential equations are called the Ginzburg-Landau equations. They come directly out of the definition of the Ginzburg-Landau free energy density. So these are not additional assumptions or additional axioms. No, they're a direct mathematical consequence of the definition of the free energy density F. Now, the first Ginzburg-Landau equation is very, very similar to Schrödinger's equation for a particle with mass m star, charge E star, and energy eigenvalue negative alpha. But in this equation, we also have an additional term, which is nonlinear, and that's that term beta times the amplitude squared of psi times psi. So that's a number that is basically psi cubed, but with the same complex phase as psi. And that nonlinear term causes so many problems because when you're actually dealing with these equations, very often you have to either make an approximation or take a numerical approach. But anyway, in spirit, the first Ginzburg-Landau equation is very much like the Schrödinger equation, and you can interpret it in much the same way. And that beta term, remember, beta is a number that has to do with how much psi doesn't want to exist with itself. And so what that term is going to do in the context of the first Ginzburg-Landau equation is the beta term is going to want psi to spread out away from itself. Okay, now the second Ginzburg-Landau equation is the usual equation that we have for current in quantum mechanics as a function of psi and A. So this equation is all about the way supercurrent flows. And also, within this equation, we find the London equations, if we make the curious assumption that the mysterious A tilde of the London equations is the vector potential A minus h bar c over E star times the gradient of phi, where phi is the phase angle of psi. Now, at this moment, we haven't yet seen why that assumption makes sense. As we get into the Anderson-Higgs mechanism, we'll recognize, hey, that's the vector potential in the unitary gauge, and it contains special physical significance because it has conjoined into itself the Nambu-Goldstone modes in our wave function psi. But let's not get ahead of ourselves. For now, we'll just take it as an assumption that the London equations A tilde is related to the vector potential A in this way. To see that the second Ginzburg-Landau equation gives us the London equations, all we have to do is plug in that definition of A tilde into the second London equation. And when we do that, a bunch of terms cancel, so the phi terms cancel, and we're left with this expression involving E star and M star and psi squared and negative E star over C and A tilde. And if we convert from Gaussian units to SI, so the 1 over C on the vector potential goes away because of the different definitions of vector potential in SI versus Gaussian, and if we also recognize that the amplitude of psi squared is the number density of superelectrons, Ns, which is sort of a core assumption of the Ginzburg-Landau model that psi squared is the superelectron density, then we can rewrite this equation as J equals negative Ns E star squared over M star times the mysterious vector potential A tilde. And as we saw earlier, this equation is the two London equations in one. If you take a time derivative, you get the first London equation, and if you take the curl, then you get the second London equation. So the London equations are nested within the Ginzburg-Landau model, which is super cool. But there's also all this other quantum richness in the equations, which presumably are going to tell us something about the difference between type 1 and type 2 superconductors. And just in general, this gives us a much richer and a much more interesting mathematical landscape to explore. Okay, so let's get a feel for some of this quantum math and what it can tell us about superconductivity. So imagine we have an interface between a normal material and a superconducting material. Well, our wave function psi is not going to be able to transition infinitely sharply between 0 and its bulk value of square root of alpha over beta. But instead, there's going to be a gradual transition that happens over some characteristic length scale, psi. Now that length scale is called the coherence length, and it's defined as approximately the distance that it takes for the condensate psi to return to its bulk value away from a disturbance or from the edge. And this is one of those order of magnitude things, sort of like lambda. It's not exactly a precise edge width, but it's sort of a characteristic length scale. So this is like classic quantum physics. When you have a wave function, there's never a sharp boundary. There's always some blur, because if you had infinite sharpness, that would require an infinite gradient in your wave function. But then you would need infinite kinetic energy density, and that's not a thing. So in the quantum world, things are always a little bit fuzzy. Alright, so how do we model this mathematically? Well, imagine a superconductor in no magnetic field, and we can say that the vector potential is 0, just don't worry about it. This is not a magnetic situation. And without loss of generality, we can also say that our wave function psi is going to be real valued, because we have the freedom to define our phase angle such that the phase angle of psi is 0. Alright, so now let's apply the first Ginzburg-Landau equation. Now the first thing we'll do is, because we're saying the vector potential is 0, don't worry about it, we're going to go ahead and delete that term, and so the equation is going to simplify like so. Next up, to make our lives easier, we're going to define a normalized wave function f, which is just psi divided by its bulk value, square root of alpha over beta. And so f is going to transition from 0 outside the superconductor to 1 inside the superconductor. And to simplify the math a bit more, we're also going to consider the equation along just one dimension, so that the Laplacian term becomes a second derivative in x. And when you make these simplifications and you substitute in f into the equation and you simplify, you end up with the equation shown here. Now, an equation like this has the form of a constant times the second derivative plus the function minus the function cubed equals 0. And if you spend a lot of time with differential equations, then you'll be tempted to identify that constant on the second derivative as the square of a characteristic length scale. And I'll show a brief argument for why that's the case in just a minute, but for now we'll just suppose that's the case. And we can use that then to solve for that length scale by simply taking the square root of the number that appears in front of our second derivative. When we do that, we find that the coherence length is h bar divided by the square root of the absolute value of 2m star times alpha. And bear in mind, alpha is that negative number that gets lower and lower as we cool down the superconductor, and the condensate wants to exist more and more. So we see that there's an inverse relationship between the coherence length, the blurriness of the edge of the superconductor, and the amount that the condensate wants to exist. So if you supercool your superconductor so that the condensate really wants to form and you have a lot of superelectron density, then you're also going to have a sharper edge of the superconductor. Conversely, if you warm up your superconductor and you get it close to that transition temperature, then the coherence length is going to increase and your condensate is going to have a blurrier edge. Now, the coherence length of a superconductor, it varies from one material to another, and also from one temperature to another, but typical values are going to be sort of on the order of like 100 nanometers. Could be more, could be less. Some are 10 nanometers, couple nanometers, and other superconductors are microns of coherence length. This is something that really varies quite a lot from one superconductor to another, but even still, it's very, very small. So it actually is a pretty sharp edge. It's just when you really, really zoom in that technically there is a little bit of quantum blurriness there. But that actually does have physical significance, as we're about to see. Okay, now I know if I don't address this, I'll get comments about, hey, why didn't you address that? So let me take a few minutes to give an argument for why it is that when we saw that differential equation, we interpret psi as a characteristic length scale. So first, let's imagine that we're inside the superconductor, so our normalized wave function f is equal to 1. So if we give f a small disturbance g, so now f as a function of space is going to be 1, plus this little disturbance g is a function of space, where g is a number whose absolute value is much less than 1. And we want to know across what length scale is that disturbance going to vary in space. Well, all you have to do is substitute 1 plus g in for f in our differential equation, and you find the equation like so when you evaluate the cube, and the second derivative of 1 is 0, so you end up with the second derivative of g. Well, anyway, you end up collecting terms, and a couple of things cancel, and you can absorb the g terms together. And we can also use a small g approximation to discard the g squared and g cubed terms. And when we rewrite the equation and divide by xi squared, we see that taking the second derivative of g has the same effect on g as multiplying it by 2 over xi squared. And so therefore, g is going to be something like an exponential whose argument is root 2 x over xi. You can see then that xi appears as a sort of order of magnitude length scale over which our disturbance is going to vary in space. Okay, but that was a bit of a mathematical tangent. Let's get back to something really deep and profound. How about the flux quantum? Let us talk about quantum flux vortices. Man, what a weird concept. It's actually kind of frightening. We're not in Kansas anymore. We have now drifted over the beautiful fields of Oklahoma. Remember from earlier? If you think about a flux quantum, it's like, this is the most surreal, unusual thing ever. How can this ever make sense? How can we possibly understand it? What a bizarre thing. But check this out. What if we had a superconductor and we poked a hole in it so that there was a point where our wave function psi had a value of 0, so no superelectrons at that point, but in the bulk of the superconductor, away from that point, we have the usual bulk value for the condensate psi. Well now, as we know, the condensate is going to rise from 0 at the defect up to the constant value in the bulk over some length scale which is approximately the coherence length psi. And that makes sense based on everything we've talked about. Now check this out. With one move, we're going to make a flux vortex, okay? You ready for this? I guess that's the sound effect for putting a twist in the phase. Okay, so now we have a very similar situation, but you'll notice that the phase angle phi wraps around the defect. And this is a flux quantum. It's a vortex of supercurrent, and the reason it's quantized is because the phase wraps one time around the vortex core. And in this two-dimensional picture, the vortex core is a point defect, but in reality, a superconductor is a three-dimensional thing, and so it's actually a line, like a tornado. So we're looking at a cross-section of that, and in reality, in 3 dimensions, the phase winds around that tornado, and so you end up with the topologically non-trivial, but topologically stabilized field configuration, where you have a phase gradient that's going to persistently swirl around and around and around. And because phase gradients encode currents, when you have a situation like this, you're going to end up with a persistent tornado of supercurrents. Okay, so there's a couple of questions that come up right away when you see something like this. The first is, why does there have to be one phase winding? Why can't we have 2? Well, mathematically, you could imagine the phase winding 2 or 3 or n times around the vortex core, but in practice, it's more energetically favorable for a superconductor to have n vortices, each with 1 phase winding, than to have 1 vortex with n phase windings. So when we have these vortices in a superconductor, the most energetically favorable thing is to have very many of them, each containing 1 phase winding, and that is where the flux quantum comes from. Oh, by the way, the first person to think that superconductors should have quantized flux was Fritz London back in 1948. But it wasn't until 1950 that Ginzburg-Landau came up with the model that really provided a solid mathematical foundation for exploring the nature of flux quantization. And it actually wasn't until the late 1950s that the scientist Alexei Abrikosov studied these vortices in a lot of depth. Abrikosov was really the first person to intensely study these vortices and to look at how they pertain to the phenomenon of type 2 superconductivity. And so in honor of his work, these are often called Abrikosov vortices, but you can also call it a flux vortex or a fluxon. Now, for a vortex like this to be energetically favorable, the supercurrent needs to be able to swirl far enough away from the vortex core that you have a good density of condensate to swirl up. So as you move far away from the vortex core, and the absolute value of psi rises to its bulk value, you want to have currents being able to swirl around out there in order for a vortex like this to form in a superconductor. And remember, what is it that determines how far into a superconductor you can have swirly currents? Well, that's going to be the magnetic penetration depth lambda. Remember, way back towards the beginning of the video, we talked about lambda as being the thickness of the water balloon material, wherein you have these swirly currents. Well, in this context, you can think about lambda as setting the length scale away from the core that you can still have a good amount of swirly currents. And because it is the coherence length psi that determines how fast the superconducting condensate restores its density away from the vortex core, what matters as far as whether or not we're going to have these vortices is whether or not the penetration depth lambda is big compared to the coherence length psi. If the penetration depth lambda is very short compared to psi, like let's say lambda is 1/10 of psi, then you're not going to have these vortices. On the other hand, if the magnetic penetration depth is many times the coherence length, then you will have these vortices, and the material will be type 2. And it turns out that the crossover point between type 1 and type 2 superconductivity occurs when the penetration depth is about 70% of the coherence length. And so 0.7 is the magic number, where if lambda is greater than 0.7 psi, you're dealing with a type 2 superconductor. And we'll talk a little bit more about that in just a moment. But first, I want to say something about flux quantization in general, not just dealing with the case of one supercurrent vortex, but broadening that up to the general situation involving flux quantization in a superconducting material. So magnetic flux quantization is the idea that if you try to poke a magnetic field through a superconductor, the flux is going to have to be quantized, meaning that you're going to end up with an integer multiple of phi naught, the flux quantum, as you poke that magnetic field through the material. And this fact arises directly from the topology of our condensate psi. So if we suppose that we have a condensate with a phase angle of phi, and you imagine a closed loop in this condensate, so a loop where the place you start and the place you end are the same place, then if you walk around that loop and you add up the change in the phase of psi at each tiny step dl, that's going to be the dot product between the gradient of psi and your tiny step dl. Well, okay, so you walk along and you're adding this up like an odometer that can increase and decrease, and you'll find that by the time you complete the loop, because you're going to be back at the place you started at, the total sum of all the phase changes along your journey is going to have to be some integer number of complete rotations, because psi is single-valued. And so if you do a full, complete loop around psi, the phase you end up with is going to be the phase you started out with. And you can write this in terms of an integral around the path, of the tiny change at each step along the path, gradient of phi dot dl, and by the single-valuedness of psi, that has to equal 2 pi n, where n is an integer. Now, if you're no fan of phase gradients, you can gauge them away using the local U1 symmetry of electromagnetism, and that lets you exchange a gradient in the phase of psi for some vector potential A, scaled by this quantity negative E star over h bar c. And so this comes from the principle of local phase symmetry. Now, there are some nuances here that I'm going to gloss over, involving branch cuts and global topological structure as it pertains to phase transformations. Never mind that, okay? It doesn't really matter for now. Just if you focus on each tiny step, and you exchange at each step some gradient in phi for some vector potential, then you can rewrite our integral in terms of an integral of A around the path, and you can pull that E star, H bar, and C onto the right side of the equation. And what this statement means is that one way to think about going around this path and calculating our phase odometer, instead we can think about that as a circulation integral in the vector potential. And we can see that that is going to be quantized by implicit virtue of the topology of psi. And that right there is the principle of flux quantization. But normally this idea is dressed up in terms of a flux integral of a magnetic field. And to get that, all we have to do is apply Stokes' theorem, which tells us that the circulation integral of a vector field around a closed path is going to be the flux integral of the curl of that vector field through the area enclosed by that path. And that's pure math. That's not even physics, that's pure math. And so then if we take our integral and we cast it in terms of a flux integral of the curl of the vector potential A, and remembering that the curl of A is the magnetic field B, then now we end up with an equation that says that the flux integral of the magnetic field through some arbitrary cross-section of a superconductor is going to be quantized, and is going to be some integer multiple of hc over E star. Now here we've absorbed the 2 pi and the h bar into h, because remember h bar is defined as h over 2 pi. So then what is the smallest unit of magnetic flux that can poke through a superconductor? Well, that corresponds to the situation when n is 1, or equivalently -1. The minus sign here just means it winds the other way. But in any case, what that shows us is that the smallest amount of magnetic flux you can poke through a superconductor is going to be Planck's constant h times the speed of light c divided by the effective charge of a superelectron. And remember, we're using Gaussian units here, so this formula is in Gaussian units. And, what's really cool about this is h and c are very well-known quantities. And the flux quantum phi naught, that can be measured. And so we can use this equation to measure the charge of a superelectron. And when you do this, you find that the charge of a superelectron is equal to precisely twice the charge of an electron. So by examining flux quantization in a superconductor, we have direct experimental evidence that superelectrons are actually electron pairs. Simply by examining the topology of our condensate psi, we're able to relate the flux quantum to the effective charge of a superelectron, thereby experimentally determining that a superelectron is actually an electron pair. I think that's just the coolest thing ever. It's like a super wonderful result. Alright, so before moving on from the topic of flux vortices and type 1 and type 2, let me say a few words about flux penetration, which sounds kind of weird, but it is what it is. Okay, so remember earlier in the video we were looking at the Meissner Effect, and we talked about how if you have a normal material, non-superconducting, non-magnetic, then if you put it in a magnetic field, the magnetic field is just going to poke through. It's going to penetrate through the material. So one way to think about that is if you make a plot where along the x-axis, you plot the magnetic field that's being applied to the material, and we can call that h. So by h, we mean the magnetic field that we're trying to poke through the material. Now on the y-axis, we'll put the magnetic field b that actually pokes through the material. And so first of all, if we consider the case of a normal non-superconducting, non-magnetic material, then whatever field we put the material in, whatever h we apply, that's going to be the magnetic field that goes through. And so we're going to have the equation B equals h, and it's just going to be a line that goes straight up and is very boring, and there's nothing exciting about it. But now consider the case of a type 1 superconductor. When you start to apply a magnetic field to a type 1 superconductor, as you know, there's the Meissner Effect. And so you put in a little bit of h, and it just gets expelled from the superconductor. The superconductor does not allow any of that magnetic field to poke through, and so the flux density B is 0. You can try to apply a field h, but the superconductor just doesn't care. It gives absolutely 0 flux. However, what if you keep turning up the strength of h? Well, if you look at this picture, you can kind of get a feel for the fact that it costs energy to pull the magnetic field apart like this. It's almost like stretching a bunch of springs, they want to be straight, they don't want to be curved. And so if h is too high, then eventually that magnetic energy is going to really want to poke through, and the superconductor is just not going to be strong enough to keep it expelled. So there's going to be some critical applied magnetic field, we'll call it h sub c for the critical field, where beyond that point, the field is just too strong, and it overwhelms the condensate's ability to stay condensed into a condensate, you know what I mean? So like thermodynamically, there is going to be this limit to where the low energy configuration is the one that just completely suppresses the superconductivity and allows the magnetic field to poke through. And so if you take a type 1 superconductor and you apply a magnetic field stronger than Hc, well, then you turn off the superconductivity, and from that point onwards, if you apply a stronger and stronger magnetic field, the material is just going to behave like a normal non-superconducting material. Okay, so now what happens if we have a type 2 superconductor? And assume for the sake of argument that we would expect it to have a similar Hc as the type 1, except for the fact that the type 2 superconductor can host flux vortices. Well, what'll happen is, at first, if you apply a relatively weak magnetic field, the type 2 superconductor is just going to exhibit a complete Meissner effect. It's going to be like, hey, okay, a little bit of field, no problem, let's go ahead and expel that. But if you go beyond a certain point, less than Hc, eventually the type 2 superconductor is going to be like, hey, wait a minute, okay, this field is getting a little bit strong, and I'm a type 2 superconductor, so I can have vortices. So rather than completely trying to keep this field pushed apart, why don't I make a couple of vortices and we'll let some of the field poke through? And as the field is able to partially poke through, that's going to relax the magnetic field's energy a little bit. Because now it's not completely expelled. It's not like pulling a bunch of springs apart. No, it's like pulling some of the springs apart and some of them are able to just poke right through, and so it's kind of a more relaxed situation. And because the field is able to partially relax by poking through these flux vortices, what that means is that the material can stay superconducting up to a field that exceeds the thermodynamic critical field Hc, because the vortices take off some of the magnetic pressure that would otherwise want to suppress the superconducting condensate. However, this effect can't last forever. At some point, you're going to end up with so many vortices that you just can't have more vortices, okay? Like everything has its limits, and eventually the material, if you go to a very strong field, is going to break down. And the field at which it breaks down for real, like completely breaks down, we call that Hc2. Now in physics, as in life, that which bends is harder to break. And so for a type 2 superconductor, Hc2 is actually greater than Hc. Oh, by the way, this is why people use type 2 superconductors for very high magnetic field applications. Now, when you do that, you have to be mindful to pin your vortices on some nanoscale defects, but that's a topic for another day. Well, anyway, the point is, if we say that the defining attribute of a type 2 superconductor is that it has this critical field Hc2 that is greater than the critical field Hc that we would expect from thermodynamics, And if we say that that is the defining attribute of what makes a type 2 superconductor, then it can be shown in an analysis that we're not going to do today that Hc2 is equal to the square root of 2 times the magnetic penetration depth lambda divided by the coherence length psi times the critical field Hc. And so if we think about that as the essential characteristic of a type 2 superconductor is that Hc2 has to be greater than Hc, and we analyze this inequality, divide by Hc, move some stuff around, we find that the constraint is, like we saw earlier, that lambda has to be greater than psi over the square root of 2, or about 0.7 psi. So once again, that is the magic number between type 1 and type 2 superconductors. Also, on this topic, there is a dimensionless parameter that we can make simply by dividing lambda by psi. So in other words, what that is the magnetic penetration depth expressed as number of coherence lengths. Now, even though the magnetic penetration depth and the coherence length both vary as a function of temperature, getting smaller as you cool down your superconductor, their ratio, kappa, is actually pretty constant. And so when you think about the Ginzburg-Landau model and these two length scales that naturally emerge, lambda and psi, you can see that their ratio is a very defining aspect of a superconductor. And if you want to know about how a superconductor behaves, one of the most important questions to ask is, what is its Ginzburg-Landau parameter? And is it type 1 or is it type 2? Or if it is type 2, like how much type 2 is it, right? How big is kappa? Anyway, so that's the Ginzburg-Landau parameter. All right, now I want to reflect for a moment on the explanatory power of the Ginzburg-Landau model, because this model is really the gold standard of how physics should be. It's a beautiful thing, because we get so much more out than we put in. Because think about it, what do we put in? Well, all we're really saying is that we're going to be able to model our superconducting condensate with a complex scalar field with the superelectron density proportional to psi squared, so that's kind of, basic quantum mechanics. And we're also going to bring in the magnetic vector potential A, which is very much standard quantum physics. Although, of course, it's weird, why are all these electrons in the same state? But other than that, it's pretty straightforward. And then we also make some reasonable statements about how psi and A contain energy in quasi-equilibrium by defining that free energy equation. And all of this is constructed using very reasonable principles and evaluated using the standard methods of physics. So it's not a crazy model, even though it makes us wonder how can we have so many superelectrons in the same quantum state. Beyond that, it's not actually that bizarre, it's pretty straightforward. Now, what we get out of the Ginzburg-Landau model is we get the Ginzburg-Landau equations when we vary the free energy with respect to psi and A, and as we saw, that's a generalization of the London equations. So that's going to model the way supercurrents flow, and from that we also get the magnetic penetration depth lambda. From the quantum aspect of the Ginzburg-Landau equations, we get the coherence length psi, and we also get the Meissner Effect, and we see that the topologically non-trivial solutions perfectly explain quantum flux vortices and flux quantization. We find also critical magnetic fields, Hc1, Hc, Hc2, and the model naturally splits into type 1 and type 2 superconductivity depending on the ratio of the magnetic penetration depth and the coherence length. And the model also tells us a lot of things about the surface energy of the superconductor, and we can also do all kinds of analysis on vortex matter and flux pinning and a whole lot more, okay? So pretty much all of the salient aspects of superconductivity are encoded in this relatively parsimonious set of assumptions and presuppositions. It's like a beautiful thing. So the math works. But as beautiful as all this math is, we do need an explanation of how it is that a bunch of electrons can be in the same quantum state. All right, you know what? It's time to address the elephant in the room, which is, why is it that the Ginzburg-Landau model is so successful in explaining superconductivity if it's based on an apparent violation of the Pauli exclusion principle? And to find the answer to that question, we have to turn to BCS Theory, which was published in 1957. BCS Theory is named after John Bardeen, Leon Cooper, and Robert Schrieffer. The basic idea of BCS Theory is that some electrons can actually be attracted to each other in a material via their mutual interactions with vibrations in the atomic lattice, also known as phonons. And, this is often pictured as, imagine you have an electron traveling through a material And as it goes along, it kind of draws in the surrounding atoms a little bit, right? Because the nuclei are going to be kind of positively charged, and so as an electron moves through, it kind of pulls them together. But then another electron somewhere else now sees that density and that concentration of positive charge, like a little cloud of positive charge, and is drawn in towards that. And so in this way, these electrons can pair up. That's a gross oversimplification because in reality, the details of this are very, quite complicated. And if you want to see those, you can look at the BCS paper from 1957, link in the description below. But for today, we're not going to go into details on how exactly BCS works. The main thing I just want you to know is that these guys figured out that superconductivity has to do with electron pairs. And the way that they pair has to do with how they interact mutually with the crystal lattice. By the way, you can prove that by making superconductors with varying amounts of different isotopes, because that's going to sort of modify your phonon landscape, modify the acoustic properties of the material. And you can see that that has an effect on the superconductivity. So why does this matter, this thing about pairing? Who cares? Well, see, what happens is when the electrons pair, their spins add up. And so as a pair, they behave as a boson, which has integer spin. Now, in the classic BCS model, a spin-up electron pairs with a spin-down electron, for a net spin of 0 for the pair. But in some more exotic superconductors, it is technically possible that you could have like 2 spin-ups or 2 spin-downs, and then you get a spin of 1, but that's still a boson. And once the pair is collectively a bosonic entity, then by the spin statistics theorem, now that they have integer-valued spin, that pair is going to be symmetric under particle exchange, and so they are liberated from the Pauli exclusion principle. And that allows them to form into a condensate. And so that is the microscopic story of how the macroscopic condensate emerges. Anyway, again, there are a ton of details in BCS theory. It's a very complicated theory, but check out the BCS paper, link in the description. Actually, the first couple pages are really nice and prosaic, and then the math gets pretty intense, but you might be interested in at least reading the first couple pages. Also, if you want to wield supercurrents, if you want to use this for engineering applications, you don't really need to know BCS. You can just use Ginzburg-Landau. BCS is really like, you know what it's like? It's like trying to understand water by using molecular dynamics. It's like, actually, if you're doing something in fluid dynamics, you want to use the Navier-Stokes equations to model the flow and the pressure and all that. But philosophically, if you want to know what water is, you also have to know about H2O. So BCS theory is like understanding water in terms of H2O, and Ginzburg-Landau is like understanding water in terms of the Navier-Stokes equations and the way that it flows. Oh, while we're on this topic, superconducting electron pairs are often called Cooper pairs. And fun fact about that, they're called Cooper pairs not because they make barrels, but because, like Sheldon, they're named after Leon Cooper. And so you often hear Cooper pairs or superelectron pairs, or you can just call them superelectrons. That's okay as well. But just keep in mind that actually the unit of superconductivity is a pair of electrons. So when we talk about superelectrons, we're implicitly talking about electron pairs. Okay, so BCS theory was a fantastic triumph in understanding the nature of superconductivity at a microscopic level, but in 1957, the question still remained. Are we sure that the Ginzburg-Landau model emerges from BCS in the appropriate limit? And, I mean, one would assume so based on the experimental success of Ginzburg-Landau, but technically, if we're being philosophical, we want a mathematical, rigorous derivation of that fact. And that derivation came along in 1959, thanks to the brilliant scientist Lev Gorkov. In 1959, he published a paper which demonstrates that, yes, indeed, BCS theory does logically imply the Ginzburg-Landau model in the appropriate macroscopic limit. And there's a couple of other assumptions in there as well, like Ginzburg-Landau is a good approximation, especially near phase transitions, where the absolute value of psi is relatively low. So, there's some nuances and caveats, and you can see his paper if you want to read about those. But the big picture is now we have a microscopic description of how superconductivity can come to be in terms of electrons interacting and pairing with each other. And we also have our macroscopic Ginzburg-Landau level of description. And now we have a logical bridge connecting the two. So this is a really enlightened, comprehensive picture of superconductivity. And as of 1959, humanity had really kind of started to figure it out in a serious way. But the plot thickens. Because in 1963, the American scientist Philip Anderson taught us another way to think about superconductors by emphasizing the importance of symmetry and symmetry breaking. Anderson realized that much of the behavior of a superconductor can be understood as a result of the phase rigidity of the condensate, and the way in which that phase rigidity alters how we usually think about electromagnetism. To be clear, Anderson didn't modify the Ginzburg-Landau model. He just found within it a tremendously insightful way of looking at things, a mechanism within the model that accounts for much of the bizarre properties of superconductivity in terms of photons acquiring an effective mass inside a superconductor. Okay, so this mechanism should be called the Anderson mechanism, right? Well, actually, Peter Higgs came along in 1964, and in a beautiful Nobel Prize-winning paper of just a page and a half, he took Anderson's idea and ran with it, generalizing it not just to superconductors, but to space itself, which, as it turns out, is apparently a kind of superconductor, as we'll explore at length in the latter half of this video. And so you often hear it called the Anderson-Higgs mechanism, not because they came up with it together, but because Anderson came up with the basic idea, and then Higgs saw in that idea a cosmic epiphany which forever changed our understanding of reality itself. So I think they both deserve a little credit. Alright, to understand the Anderson-Higgs mechanism, we have to bring together a handful of fairly technical concepts. This is graduate-level physics, so don't be demotivated if it takes some time and effort to learn. That's just how it is. So first, let's go ahead and summarize the Anderson-Higgs mechanism, just the big picture, and then we'll go through each of the component concepts one at a time, and then we'll assemble those concepts into the Anderson-Higgs mechanism in a more technical way, but hopefully in a way that provides memorable and visual insight. Okay, so in a superconductor, a condensate forms, and it spontaneously picks out a particular phase. The condensate also has some phase rigidity, in that there is energy associated with phase gradients. So if you try to locally twist the phase of a superconductor, that would take some energy. So our condensate lives in the context of a global phase symmetry, but it picks out a particular phase, and then it enforces that phase via its phase rigidity. Fine, okay. But then we would expect to be able to excite the condensate by creating waves in its phase, and letting those phase waves ripple around, because by global phase symmetry they should be allowed to drift, but by the phase rigidity they're going to be brought back in line. So the phase at one point of the condensate is going to be brought back into alignment by the pure pressure of the phase at neighboring points. And so it's going to be an interplay between a symmetry and the pure pressure that breaks the symmetry. And these kinds of phase waves would be an example of Nambu-Goldstone modes, which are waves that arise when a global symmetry is broken, like phonons or magnons, or apparently, like phase waves in a superconducting condensate. However, the physical nature of a phase wave in psi is a really complicated thing, because the local phase symmetry of electromagnetism means that we can simply gauge away those phase waves by applying a phase transformation which, by definition, takes out the phase angle of the condensate everywhere, and that puts us into something called the unitary gauge. In the unitary gauge, by definition, there can be no phase waves in psi. But everything has a cost, and when we gauge away our phase waves, we end up with an irrotational contribution to the vector potential A. And that energetic contribution to A will give us a term in our free energy equation which depends on the magnitude squared of A. Well, such terms are forbidden for a massless vector field, and so we come to find that in the unitary gauge, it is as if the vector potential A has acquired mass. And that seems like we're violating the laws of electromagnetism, but bear in mind that behind the scenes, it's the phase rigidity of psi that props up the ability for A to have mass. This is often described as the Nambu-Goldstone modes have been eaten by the vector potential, thereby giving the vector potential mass. Okay, so there's a number of technical concepts in the Anderson-Higgs mechanism, so let's take a few minutes to review each of those concepts, and then we'll bring it all together into a beautiful picture of the Anderson-Higgs mechanism. Alright, let's talk about Nambu-Goldstone modes. Nambu-Goldstone modes are waves that are born of a broken symmetry. So in the laws of physics, there are often symmetries, where a symmetry is a variable that doesn't really matter. And a good example of that is spatial translational symmetry, which says that the laws of physics in one place are the same as in another place. And we know this because our planet is hurtling through the void at very high speed, and yet we don't have like seasonal changes in the fine structure constant or that sort of thing. Like no, actually space over here is pretty much the same thing as space over there. And so imagine that you're a free atom just drifting through space. Well, as you drift along, the space that you travel through at one point is going to be the same as the space that you travel through at another point. But when you have a crystal and a bunch of atoms get together and decide to do a periodic arrangement, well, if you're an atom in the crystal, then now all of a sudden it kind of effectively does matter where you are, because if you start to drift away from the location you're supposed to be at, the neighboring atoms are going to be like, hey, get back into that position. We're kind of doing a periodic thing right now, you know? So a crystal effectively breaks spatial translational symmetry. Now, that's kind of a dramatic way of describing what's happening. And even though now, if you're an atom in the crystal, it's as if you don't have spatial translational symmetry. But the principle of spatial translational symmetry is still an aspect of the laws of physics. And so a dynamic interplay emerges between the symmetry and its breaking. Now, similarly, if you have a magnetic material, the magnetism arises from the alignment of the spins of the electrons in the material. And so what happens is, as their spins align, it's going to spontaneously break rotational symmetry, because there's not any cosmically preferred spin axis, but because of the magnetic ordering of the material, the spin in one place is going to want to be aligned with the spin in another place. And so, once again, we have a Nambu-Goldstone situation, where you can get these spin waves going through the material, because rotational symmetry allows the spins to kind of rotate their axis, but the magnetic ordering is going to pull the spins back into alignment, so these waves are called magnons, and much like phonons, they are Nambu-Goldstone modes. And so then likewise, in our condensate, it exists in the context of a global phase symmetry, so that's going to let the phase angle drift, but then there's also some phase rigidity, which is going to apply a restoring force that brings the phase back into alignment, and from that we should expect some wavy waves to emerge. Now, one of these things is not like the others. The phase waves in a superconductor have a particular kind of existence because they're exactly the kind of thing that can be gauged away. And so this reasoning about expecting superconductors to host Nambu-Goldstone modes, it is well motivated and correct, but when you factor in what those waves are made out of, you realize that there's actually a really subtle dynamic going on here, where to understand the Nambu-Goldstone modes, you have to look at it in the context of the vector potential and local phase symmetry. Now, to set our expectations, there's something you should know about Nambu-Goldstone modes, which is that typically we would expect these waves to be massless. So, what is a massless wave? Well, consider the photon. Now, a photon is not a Nambu-Goldstone mode, but it is the quintessential massless wave, and so it'll work just fine for thinking about what a massless wave is. So, when you have a photon, there is a direct relationship between the energy and the momentum. So if you double the photon's momentum, you get twice the energy. Now, as we've seen in quantum physics, energy has to do with how much the wave is flopping around in time, and momentum has to do with how much the wave is scrunchy in space. So when you look at a photon, you see that the more scrunchy it is, the more floppy it is. And so if you imagine a very stretched out wave, like for example a red photon, or even infrared or radio or something longer, then as the wavelength gets longer and longer and longer, the momentum trends towards zero, and so does the energy. And that is the essence of masslessness. So a massless wave, when you imagine stretching it all the way into the long wavelength limit, with wavelength approaching infinity, the energy should approach zero. And even though photons are not Nambu-Goldstone modes, that same principle applies when we talk about Nambu-Goldstone modes being massless. If you imagine, for example, a phonon of very long wavelength, as the wavelength increases and increases, the waves get slower and slower and slower, and the energy trends towards zero. And there's actually a theorem, Goldstone's theorem, which says that Nambu-Goldstone modes are massless. And when you have a system that hosts Nambu-Goldstone modes, you can always put in a very small amount of energy by exciting a very long-range Nambu-Goldstone mode. But there's a very important exception to Goldstone's theorem, and that is, if your Nambu-Goldstone modes are the kind of thing that can be gauged away, well then this thing about masslessness goes away. Because when you factor in the gauge fields, then you see that it's more of a complicated situation, as we're about to see. Okay, so I just bring up photons as an example of a massless wave. But now, in a superconductor, our Nambu-Goldstone modes, these phase waves, they actually do acquire mass. And the way to think about that is they get absorbed into the vector potential A, and then the resulting A, which has been enhanced by the Nambu-Goldstone modes in psi, well, that upgraded vector potential A is going to have mass. And when you try to excite the massive vector potential, you'll find that even for an excitation with zero momentum, that is a super long wavelength, the energy of that excitation is not going to approach zero, but instead will approach the mass energy corresponding to a quantized excitation of the upgraded vector potential. So now we're moving in the direction of seeing how that happens, and we're building up a picture of the Anderson-Higgs mechanism. But as we're doing that, there are a couple of vocabulary words that we're going to be using, and these are solenoidal and irrotational. And in order to see what those words mean and how they're relevant to the Anderson-Higgs mechanism, let's take a moment to talk about the concept of Helmholtz decomposition. So let's say we have some smooth vector field in 3 dimensions, and suppose that it's well behaved. So, for example, if you go out to infinity, the vector field vanishes out there. Well, interestingly, you can decompose that arbitrary vector field into a part that doesn't diverge, plus a part that doesn't curl. So the field that doesn't diverge, that's just going to swirl around, right? That's all swirly. So that's called the solenoidal field. Think of like a solenoid, you know? But on the other hand, the field that doesn't curl, that only diverges. It only pokes out and pokes in. And so that's called the irrotational field. So one way to think about a vector field is the sum of a solenoidal field that swirls, plus an irrotational field that pokes out and pokes in and diverges. And today, we don't have to go into the details of how to do a Helmholtz decomposition, but I just bring it up so that, for example, we can talk about the solenoidal part of the vector potential, or the irrotational part of the vector potential, because as we're about to see, these are useful concepts when thinking about the masslessness or massiveness of photons in the context of the Anderson-Higgs mechanism. Okay, so I have this animation here, and I hope it helps to kind of illustrate the concept. It is a bit cluttered. I don't know. I mean, this was my best attempt at this, but apologies if this looks cluttered. Oh, and by the way, this animation loops, so don't worry, you don't have to pause it. We can just let it go and let it do its thing. So anyway, what this demonstrates is that if you have some arbitrary vector field, so that's the gray arrows, then you can write that as the sum of the solenoidal field, so that's those blue arrows, and you can see how they swirl around, and the solenoidal field is all about curl. And then the green arrows, you can see that this field doesn't curl. It only diverges, it only pokes out and pokes in. And the sum of the blue and the green, that is the sum of the solenoidal and the irrotational field, add up to the vector field, for whatever physically realistic arbitrary vector field that is. Okay, so that's the concept of Helmholtz decomposition, and I only bring it up so that we can use the concept of the solenoidal part of a field and the irrotational part of a field. Okay, so if we want to learn about the Anderson-Higgs mechanism, one of the core concepts is the local U1 transformation, also known as a local phase transformation. Now, as we saw in the last video, the local phase transformation is at the core of electromagnetism, and in fact, this is electromagnetism in one principle. And I'm not going to rehash all of that today, because we'll be here for an extra 3 hours and 12 minutes. But let's just take a look at the definition of the transformation, because this is going to be helpful for us as we explore the Anderson-Higgs mechanism. So the basic idea is that we're doing some quantum physics, and we have a wave function psi, but the phase of psi isn't really a physically observable quantity on its own. And specifically what we mean by that is if we transform our wave function psi into some wave function psi prime by multiplying psi by this e to the I theta term, which is a unit length complex phase field, so you're changing the phase of psi arbitrarily in space and time, then the resulting transformed wave function psi prime should still be just as good of a description of the situation. But with the important caveat, you also have to apply a compensating transformation in the electromagnetic 4 potential A. And that transformation is going to turn A into A prime by subtracting this quantity negative h bar c over q times the 4 gradient of that phase field theta. And if you want a refresher on how that comes to be, just go ahead and watch the last video and you can see where that comes from. But for now, we're just going to take this as a starting point, and we're going to translate it from relativistic language into a particular reference frame, namely the reference frame of the superconductor. Because when you're dealing with a superconductor, you don't actually have to use relativity. You can say, we're going to work within the inertial frame of the material itself. So in order to do this translation, let's go ahead and write out the definitions of the 4 potential and the 4 gradients. In covariant form with the downstairs mu, the 4 potential has voltage for the time-like part, and the negative of the magnetic vector potential as the space-like part. And the covariant 4 gradient has a 1 over c time derivative for the time-like part, and the gradient for the space-like part. So now let's write the rules for a local phase transformation in terms of just the spatial parts, because that's what's relevant in a superconductor. We're dealing with the magnetic vector potential, and we're not so interested in voltage. So looking at the spatial part, we can see that the transformation rule can be written as the transformed wave function psi prime is, once again, psi times the exponential of I theta, where theta is an arbitrary phase field. In this context, it's just a function of space, and doesn't depend on time, because we're in quasi-equilibrium. And then the vector potential transforms by the addition of h bar c over the charge of a superelectron times the spatial gradient of theta. So if you look at these two transformation rules, the spatial part only as well as the relativistic rule, you see they're basically the same thing for A. There's just a difference in sign that has to do with the mostly minus metric. And also, instead of Q for the charge, we might as well write it E star, as we've been using for the Ginzburg-Landau model for the effective charge of a superelectron. And this brings us to a very important idea, which is the concept of choosing a gauge. So when dealing with electromagnetism, we can transform psi and we can transform A in a complementary way, in accordance with the local Yuan transformation rule, and that doesn't change anything observable whatsoever, right? So that is the principle of local phase symmetry, and that principle blossoms into electromagnetism. And this principle also means that we have infinitely many equivalent ways of describing the same physical system in terms of different psi and different A that are all related to each other by local phase transformations. And this is possible because psi and A are not themselves directly observable. The quantities that are observable, that are sort of encoded in psi and A, are encoded in such a way that they're insensitive to this kind of a transformation. So then to choose a gauge is to narrow down that infinite set of options with some convenient gauge conditions. And this reduces the redundancy in psi and A without affecting any observable quantities. Like, for example, we can impose by fiat that the divergence of the vector potential should be 0. This is known as the Coulomb gauge condition. And this condition can be imposed because you can always add the gradient of some phase field that will ensure that A is divergenceless. Or alternatively, we can also say, you know what, let's make psi a real valued field, because we can always apply a local phase transformation that takes away the complex phase at each point in space. And then whatever gradients were in psi, they can just pop up in A as some addition of the gradient of that theta field that we took out. So when psi is a real valued field, that's called the unitary gauge. And that is a very important gauge, as we're about to see. So yeah, that's the concept of choosing a gauge. And it's very similar to setting your coordinate system. Like when you choose where you want to put your XYZ axis and how you want it to be oriented and all that sort of thing, you have the freedom to do that, and you can still describe the same physical situation. And likewise, we have the freedom to apply some gauge conditions that are compatible with these local phase transformations, and that's a part of defining how we're talking about the physical system. So now there's another very important concept that we'll have to know about if we want to understand the Anderson-Higgs mechanism, and that is the Gauge-Covariant Derivative. So the purpose of the Gauge-Covariant Derivative is to give us a way of defining the derivative operator that is essentially unaffected by our choice of gauge. Right? Because, for example, if you just apply a regular derivative or a gradient to psi, and then you transform psi by a local phase transformation, you're going to mess up its gradient. So what the Gauge-Covariant Derivative is a kind of derivative where when you apply a local phase transformation to psi and you apply the corresponding transformation to A, the Gauge-Covariant Derivative, at least the magnitude of the Gauge-Covariant Derivative, is not going to change. So that's going to be a quantity that does not depend on the gauge that we're in. And as you might expect then, that quantity is going to be closely related to physically observable things like momentum. All right, so the Gauge-Covariant Derivative is defined as the gradient of psi minus 1 over E star h bar c times the vector potential times psi. And by looking at it, you can kind of imagine, okay, so we slap on a phase transformation to psi, we transform A in the corresponding way, and this quantity should remain pretty much unchanged. Maybe it picks up a phase factor, but its amplitude should remain unchanged. Let's go through this real quick just to see that that is indeed the case. So if we write out the definition of a local phase transformation, where we slap on a phase factor e to the I theta to psi, and that becomes psi prime. And then likewise, we add a term proportional to the gradient of theta to the vector potential A. And all we have to do to see how the covariant derivative transforms is to plug in psi prime and A prime for psi and A in the definition of the covariant derivative. When we do that, we find the expression the gradient of psi e to the I theta minus I E star over H bar C times A plus H bar C over E star gradient of theta times psi times E to the I theta. So it's kind of an algebraic mess, but we can simplify it. First thing we'll do is we'll apply the product rule to the term psi E to the I theta. And first taking the derivative of psi, we get the gradient of psi times E to the I theta. Then you take the derivative of the E to the I theta term and you end up with I times psi times E to the I theta times the gradient of theta. Okay, now likewise, if we look at that second term, let's go ahead and multiply through by that factor I E star over H bar C. So we pull that in, we distribute it, we cancel a couple of terms on the theta term, and we end up with the expression shown here. Now this equation simplifies quite nicely because you can see that these green terms cancel each other out. And then it gets even better because if you look at this equation with the gradient of psi times e to the I theta minus I E star over H bar C, A psi e to the I theta, man, these equations are a mouthful. Anyway, you recognize the blue terms here as the definition of the covariant derivative d acting on psi, and then you see that there's an e to the I theta term, and so you can go ahead and factor that out. And what we end up with is the conclusion that the covariant derivative acting on the transformed wave function psi prime is equal to the covariant derivative acting on the untransformed wave function times a phase factor e to the I theta. Now e to the I theta has an amplitude of 1, and so therefore the amplitude of the covariant derivative is the same before and after applying a local phase transformation. And so what this demonstrates is that no matter what gauge we're working in, maybe you're working in the Coulomb gauge and I'm working in the unitary gauge, we can both agree on the amplitude of the covariant derivative. And this is a useful concept for simplifying a lot of calculations and also connecting different concepts from one gauge to another, which, as we'll see, is essential for understanding the Anderson-Higgs mechanism. Oh, and you know what? Another cool thing about the gauge covariant derivative is that it makes the Ginzburg-Landau free energy density equation a lot simpler. Because check it out. Okay, so first let's write out the equation for F, as we've seen. Now, if you look at the definition of the gauge covariant derivative, you realize that this middle term in F, the complicated one with all the H bars and I and gradients and E, that whole term, you can see in that the pieces of the gauge covariant derivative, and you can kind of assemble it together and do some pattern matching, and you end up finding out that that whole term can be replaced simply with H bar squared over 2m star times the amplitude squared of the covariant derivative acting on psi. So that is really cool. I mean, look at how much simpler it is. And not just simpler in terms of number of characters, but also simpler in that now we have this quantity which manifestly does not care about which gauge we're in. And that makes the equation a lot easier to parse philosophically. If you want to color code the different parts of this equation, we see that there's the free energy density associated with the condensate's existence, as well as energy density associated with the kinetic energy of the condensate that has to do with that gauge-covariant derivative of psi. And then we also have the energy density of the magnetic field. Now, when you look at this equation and you consider the various things that it has to encode in order to give us the full description of a superconducting condensate, you actually see that it's about as simple as it can be. I mean, I know the first time you see this equation for the Ginzburg-Landau free energy density, it's like, oh my gosh, what is all this quantum stuff? This is crazy. But when you really dive into it, you see like, oh, okay, actually this is a pretty elegant model. You know, it's not very contrived. It actually makes a lot of sense. And while we're here, let me just make one more point about the Ginzburg-Landau free energy density, which is that the whole equation, the whole F equation, does not depend on our choice of gauge, which makes sense because energy is a real observable quantity. So by definition, it cannot depend on our choice of gauge. Whatever gauge we're in, all the observables should be the same. And you can see this by imagining that we apply some arbitrary local phase transformation, and then look at whether or not the individual parts of F are going to be affected by that. Well, first of all, the energy due to the condensate density and density squared, that doesn't change at all, because this phase factor e to the I theta that we slap onto psi does not change the amplitude of psi. And now if we look at the kinetic energy density of the condensate, we find that it's a constant times the amplitude squared of the gauge-covariant derivative, and we know that the gauge-covariant derivative, its amplitude doesn't change when we go from one gauge to another, so that part stays constant as well. And then, last but not least, if we look at the magnetic field's energy density, this also doesn't change because when we transform A, we add to it the gradient of a scalar field, but the gradient of a scalar field does not curl. And so therefore, the amplitude of the curl of A' is the same as the amplitude of the curl of A. And another way to think about this is, remember, what is the curl of A? Well, it's the magnetic field B. And the strength of the magnetic field is an observable quantity, so therefore that also can't depend on our choice of gauge. So the whole Ginzburg-Landau free energy equation is completely independent of whatever gauge we're working in. Alright, so now we're finally ready to look at the Anderson-Higgs mechanism. First, what we want to do is imagine a superconducting condensate with a constant amplitude of psi, but that hosts these Nambu-Goldstone modes in the form of these little phase oscillations. So the phase is going to get kind of wavy, like how we talked about before. And at first, what we can do is suppose, for the sake of argument, that there is no vector potential yet. Okay, so we're just thinking about a superconductor on its own without being influenced by the vector potential. And by the way, everything we're about to talk about, you could also think about in a more general context, but for now we may as well set A equal to 0. Well then, another way to look at this situation with the wavy waves is to say, let's hop into the unitary gauge, where we apply a local phase transformation, e to the negative I phi, where phi is the phase of psi. And so by applying that transformation e to the negative I phi, we're transforming the wave function psi, which is complex valued and has these phase waves, into a real valued scalar field psi prime that has no phase and no phase waves. So we've gauged away the Nambu-Goldstone modes. Oh, that's fantastic. But you know what happens when you apply a phase transformation to psi? We also have to apply the corresponding phase transformation to A. So we're going to add h bar c over e star times the gradient of the angle that we're transforming by. In this case, the angle is going to be negative phi. At each point, we're twisting the phase in psi by an angle of negative phi. And so we actually get negative h bar c over e star times the gradient of phi. And there's actually a sneaky double negative here, because bear in mind, the charge of a superelectron is negative. And so A is actually going to pick up a quantity that is directly proportional to the gradient of the phase of psi before we go into the unitary gauge. So when you look at these two pictures, which by the way are gauge equivalent descriptions of the same situation, you can see that in the bottom picture, what were previously gradients in the phase of the condensate now show up in A as the gradient vector. And so for example, if we pause this real quick, and if you look in the direction of increasing phase somewhere, So that's going to be where the phase angle is turning counterclockwise. Well, the gradient in the phase there is going to be pointing uphill in the direction of the phase increase. But if you look then at the bottom part in the unitary gauge, that's what A is going to be. And so that's all we're saying. We're saying that when we hop into the unitary gauge, what were previously these Nambu-Goldstone modes in the condensate now get absorbed or eaten by the vector potential A. So this is very interesting because earlier we talked about Nambu-Goldstone modes, we talked about symmetry and broken symmetry, and these waves should be able to contain energy because of the phase rigidity. But now we're seeing, okay, yeah, that is true, or that seems to be true, but we have to be careful here because there's an extra level of nuance, which is that in a superconductor, these Nambu-Goldstone modes, these phase waves, have a form which can be completely gauged away and accounted for instead entirely in the vector potential. And so to the extent that the condensate can contain energy because of its phase rigidity, we might as well account for that energy in terms of a modification of the usual behavior of the vector potential A. And it turns out that what that modification is going to do is going to give A mass. And insofar as a photon is a disturbance in A, that means that photons are going to acquire an effective mass in a superconductor. So let's take a look at how this happens. Well, first of all, we have to calculate how much energy is contained in the Nambu-Goldstone modes. And the answer to that can be found in the kinetic term of the Ginzburg-Landau free energy density, which as we've seen is h bar squared over 2m star times the amplitude squared of the covariant derivative acting on psi. And for a simple analysis, let's suppose that the vector potential is 0, so that we're really focusing purely on the energy contained in the phase waves. Well then in that case, when you write out the covariant derivative, you see that the term involving the vector potential goes away, and the kinetic energy contained in these phase waves is simply h bar squared over 2m star times the amplitude squared of the gradient of the wave function. And then when you think about like the amplitude of psi is constant everywhere, you see that the gradient term really just depends on the gradient in phi. And that has to do with this idea of the phase rigidity of the condensate containing energy. You see it in this expression. But now then when we hop into the unitary gauge, we gauge away the Nambu-Goldstone modes, so that the gradient of psi is 0. And then the question is, wait a minute, does the kinetic energy become 0 too? Because we just solved kinetic energy is proportional to the gradient of psi, and so if that's 0, then kinetic energy is 0, right? Well, no, because energy is observable, and so therefore it cannot be affected by our choice of gauge. And so that kinetic energy term involving the gradients of psi is going to have to be replaced with the term involving the vector potential A. And okay, so we can do that by, again, looking at the covariant derivative. This time the gradient of psi is the 0 vector, and so the psi term goes away. We're left with just the term involving the vector potential and psi and those constants. And when you plug that into the kinetic energy equation, we get an expression which is E star squared over 2m star c squared, amplitude of psi squared times the magnitude of A squared. And that is another way of accounting for the energy in those phase waves. And it's totally equivalent to the expression that we derived earlier, but this is the correct expression when we're in the unitary gauge. And so what this all means is that because we have the freedom to choose our gauge, and because we think that a condensate should be able to host these Nambu-Goldstone modes with the phase waves, well, one way to look at that is that in the condensate, there's going to be some energy that arises from this irrotational contribution to the vector potential A. Notice that the contribution to A from the Nambu-Goldstone modes is an irrotational field, because it's based on the gradient of the scalar field phi, and the gradient of a scalar doesn't have any curl. Now, normally, when you're dealing with the vector potential A, the energy of A is contained in its solenoidal part, thinking in terms of Helmholtz decomposition, and the irrotational part of A is usually not exactly real because you can make it go away by hopping into the Coulomb gauge, where your wave function psi takes on whatever phase angle it has to in order to accommodate a divergenceless vector potential. But the situation is more nuanced in a superconductor because the phase rigidity of the condensate means that there are energetic consequences that come in when you try to simply erase the irrotational part of A. Because if you try to gauge away the irrotational aspect of the vector potential A, it's just going to manifest energetically as Nambu-Goldstone modes in psi. To develop an intuition for what's going on here, it's helpful to imagine something that I like to call the Masochist Gauge. This is not a technical thing. You won't find it in a physics textbook, but it is a genuinely legit concept. The idea is just to imagine some Nambu-Goldstone modes, and then hop halfway to the unitary gauge by subtracting out half the phase angle of psi. So it's like half a hop. We have 1 foot in each world, and so we get to deal with the worst of both worlds. Because in the Masochist gauge, the Nambu-Goldstone modes are only half eaten by the vector potential. And so we still have some phase waves in the condensate, but we also have some irrotational contribution to A that contains energy. You'd have to be an enjoyer of suffering and misery in order to ever work in this gauge. But it is useful for helping us think about the Anderson-Higgs mechanism, because all 3 of these pictures are gauge equivalent. And so you can imagine your perspective shifting around between gauges as a continuous thing. So if you put the Nambu-Goldstone modes in the left hand of your mind's eye, you know what I mean, and then if you put the unitary gauge in your right hand, it's not like you have to choose between your left hand or your right hand. You can shift around mentally in the space of gauge-equivalent descriptions of the situation, and you'll find the Masochist gauge as like a halfway point between your left and your right hand. And you don't want to spend any time there, but by noticing that it exists, it kind of gives you a feel for the continuity of the different gauge choices that we're allowed to make. Because one of the questions that comes up with the Anderson-Higgs mechanism is, what's so special about the unitary gauge? And the answer is, it doesn't matter what gauge we're working in. But so therefore, you might as well work in the gauge where everything's the simplest, where all of the shenanigans about phase waves and psi get absorbed on up into the vector potential A. And so you might as well work in the unitary gauge, in which the phase waves are accounted for as part of the upgraded, massive vector potential. Now, if we look again at the equation that we just calculated for the free energy density contained in these waves in A, in the unitary gauge, we see that it's an expression that depends on how much A we have somewhere. If you think back to the last video, we saw that the masslessness of the 4 potential A mu is precisely the statement that the amount of energy in the system does not depend at all on how much or how little A we have. But now the situation is different. In the unitary gauge, there is an energy term which depends on how much A we have, and so therefore A has mass. Something to notice here is that even though we started our analysis with 0 vector potential before hopping into the unitary gauge, and so all of our A is the irrotational contribution from the Nambu-Goldstone modes, had we instead started with a non-zero A, then we could apply the same kind of reasoning, and we would get the same result about energy density being proportional to A squared. But the A in that context would be a more general vector field, not just an irrotational field, but also a field that can have a solenoidal component. And so even though the Nambu-Goldstone modes are eaten specifically by the irrotational component of A, in a more holistic sense, all of A, with all its degrees of freedom, have become upgraded by the consumption of the Nambu-Goldstone modes. Regardless of how exactly A is rippling around, in a superconductor in the unitary gauge, there is energy that depends on A's magnitude squared, and therefore A has mass. Notice also that the strength of this mass term depends on the density of the superconducting condensate, psi squared, and also the charge of a superelectron. And that makes sense because imagine you're a photon and you're interacting with a condensate. Well, how much your existence interacts with the condensate depends on the density of the condensate and also how strongly you're coupled to its constituent particles. And so the thicker the superconducting condensate is, the more massive the photon becomes. So how should we calculate the mass of a photon in a superconductor in the unitary gauge? We'll invoke a principle from quantum field theory, which is that if you have a term like this, where the energy density depends on the magnitude squared of a real-valued vector field, then that's going to be a mass term, and it'll have the form 1/8 pi times mc over h bar squared times the magnitude squared of the vector potential A. Now we're not going to be deriving that principle today in the interest of time. Today we'll just take it as a given. And later on, we're going to use essentially the same principle again when calculating the W and Z masses. Okay, so to calculate the mass of a photon in a superconductor, we just have to match terms and solve for the mass. So first, if we multiply by 8 pi times h bar squared divided by c squared, we end up with an expression for the mass of the photon squared. And then all we have to do is take a square root, and we solve that the mass of the photon is twice the square root of pi over the effective mass of a superelectron, times the effective charge of a superelectron, times h bar divided by c squared, times the absolute value of psi. And notice how the mass of the photon is directly proportional to the amplitude of psi. Later on, we'll see that the masses of the W and Z bosons are directly proportional to the Higgs vev, and for precisely the same reason. But we'll get to that later. For now, let's focus on the vector potential A. Now, as you can imagine, an A that has mass behaves differently than an A that has no mass. Alright, well there's a way of looking at this math that you'll often hear people talk about, which is that when A becomes massive in a superconductor, it gains the ability to be longitudinally polarized. And this gives the vector potential A in a superconductor an extra degree of freedom, or an extra way that it can be excited that is physically meaningful. So the blue arrows on the left show an example of a vector potential in the Coulomb gauge. So the Coulomb gauge condition is that the divergence of A is 0, so then we end up with an A that is purely solenoidal. Now remember, the magnetic field B is the curl of A. So when you think about the way that the magnetic vector potential encodes magnetic energy, you realize that really it's only the solenoidal part of the field that you have to worry about. And the irrotational part is not physically significant. However, in a superconductor, when you're dealing with the unitary gauge, as we've seen in the unitary gauge, the Nambu-Goldstone modes in psi are going to manifest as an irrotational contribution to A. And so on the right, what we're seeing is the vector potential in the unitary gauge. And so you can see that this vector potential is no longer purely solenoidal, but also has a non-zero irrotational part, corresponding to those Nambu-Goldstone modes. So in addition to solenoidal and irrotational, there's also the terminology transverse and longitudinal. And a transverse wave is something where whatever direction the wave is propagating, the thing that's actually oscillating is oscillating in a perpendicular direction to that. So for example, here you have this wave that's kind of going upwards at a 45-degree angle, but the thing that it's comprised of, the vector oscillations that make the wave wavy, are going 90 degrees relative to that, 45 degrees. You see what I mean? They're kind of going up and to the left and down and to the right. So that's a transverse wave. Now the connection between a transverse wave and a solenoidal field is that if you take an arbitrary solenoidal field and say, I'd like to look at this from the perspective of Fourier analysis, where we decompose the vector field into a sum of plane waves, well, the fact that your vector field is purely solenoidal means that those constituent plane waves themselves have to be solenoidal, meaning that they don't diverge or converge. And in order for a plane wave to be divergenceless, it has to be transverse, so that whatever way it's moving, it's oscillating perpendicularly to that, and you'll notice that that wave does not contain any divergence or convergence. And so when you stack a bunch of arbitrary transverse waves to construct some general vector field, that field is always going to be solenoidal because none of those transverse plane waves are going to add any divergence or convergence to the field. And the divergence is a linear operator, so, you add a bunch of divergenceless plane waves and you end up with a divergenceless, aka a solenoidal, aka a swirly, vector field. Okay, now on the other hand, a longitudinal mode is a wave where the direction of propagation is in the same direction as the thing that's sloshing around and comprising the wave. So here we have a longitudinal wave going up and to the right, and we see that the vectors themselves are sloshing around up and to the right and down and to the left, and so that is a longitudinal mode. And this mode doesn't have any curl, so when you stack a bunch of longitudinal modes, you're going to end up with an irrotational field. And the reasoning here is very similar to what we just saw, but instead of adding up a bunch of transverse waves, which are divergenceless, now we're adding up a bunch of longitudinal waves, which don't have any curl, because for a longitudinal wave, the amplitude vector and the wave vector are parallel. So you can stack up as many longitudinal waves as you want. Each one has no curl, and because curl is a linear operator, the resulting sum is going to have no curl. And so that's why, from a Fourier analysis perspective, if you're dealing with an irrotational field, you can write that as the sum of longitudinal waves. Now what I'm showing here is an example of two waves superimposed on each plot. And in fact, they have the same wave vectors, but the waves on the left are purely transverse, and the waves on the right are purely longitudinal. And you can see just by stacking two waves that we end up with the swirly situation on the left and a diverging and converging but not rotational situation on the right. So when you generalize that to a more general situation, you can see the connection between transverse waves and solenoidal field, and longitudinal waves and an irrotational field. So now if we return to the picture we were just looking at, where on the left we have a solenoidal A in the Coulomb gauge, and on the right we have a more general A in the unitary gauge, just to emphasize, that A in the unitary gauge is not purely irrotational. No, it can contain a solenoidal component as well. It contains both. And so if you wanted to decompose it into a sum of plane waves, you'd have both transverse and longitudinal modes in that sum. So this is what people mean when they say that because of the Anderson-Higgs mechanism, the vector potential A is able to be longitudinally polarized, in addition to the transverse polarizations that it can usually host. And so A gains these extra degrees of freedom that are physically meaningful. But of course, as you now know, those extra degrees of freedom don't just come out of nowhere. Those are secretly just the Nambu-Goldstone modes in psi. But, you know, a mode by any other name is still, I don't know, I thought that was going somewhere, but it's not. So, all right, hey, let's move on. Something else that's cool about the Anderson-Higgs mechanism is that it gives us a fresh perspective on the Meissner effect. So let's say we're looking at the surface of a superconductor with the vector potential shown here in orange, and we're going to try to excite the vector potential from outside the superconductor by applying a magnetic field to it. Well, in the unitary gauge, because the vector potential A has mass, that means that there's going to be some energy density which is proportional to the magnitude squared of A. And so therefore, A is going to want to minimize its energy by relaxing itself out of existence to the zero vector in the bulk. And you can personally relate to how A feels in a superconductor, because it's sort of like Monday morning when you have to wake up and you're like, oh man, I'd rather just be the zero vector right now, I don't want to do anything. But of course, in a superconductor, there are other kinds of energy pertaining to gradients and all that sort of thing. And so if you try to excite the superconductor by applying a magnetic field to it, well, A is going to be aroused a little bit near the surface of the superconductor, up to some distance lambda, the penetration depth, which by the way is inversely proportional to the effective mass of a photon in a superconductor. Beyond the length scale of the penetration depth lambda, A is just too lazy to play along, and so out there it would rather be zero. Now, because A wants to be the zero vector, and the curl of A is the magnetic field B, well, the curl of the zero vector is also the zero vector, and so there you go, that's the Meissner effect. Inside a superconductor, the vector potential ate the Nambu-Goldstone modes in psi, that gave it mass, and now it's all massive and lazy. Isn't this a beautiful way of looking at the Meissner effect? I love it. I think this is awesome. It's great. It's fantastic. Now, of course, you might be thinking, hey, well, hold on now. This is only in the unitary gauge. But suppose we chose another gauge and we wanted to look at it in that situation. And we're always free to do that. You can always hop into a different gauge if you want. But bear in mind that the vector potential in any other gauge is only going to differ from the vector potential in the unitary gauge by the addition of the irrotational component that comes from the gradient of the phase angle of our phase transformation. And so the vector potential we're looking at in the unitary gauge, which wants to be the zero vector, in some other gauge, it's going to want to be a purely irrotational field. And what do we know about purely irrotational fields? They don't curl. And so, in any other gauge, it's still true that the magnetic field goes to zero inside a superconductor. Okay, so we've been talking about Nambu-Goldstone modes and the vector potential and Nambu-Goldstone modes getting absorbed into the vector potential and the Anderson-Higgs mechanism, but we can also imagine amplitude modes in psi. So as the name suggests, these are waves in the amplitude of psi. Now these waves are going to be inherently massive. It's going to cost energy to make the condensate's magnitude deviate from where it wants to be. So if you think about the amplitude of the condensate at some point, increasing and decreasing, and you think about the sombrero part of the Ginzburg-Landau potential, you know, the alpha and the beta, well, the amplitude of psi is inherently not going to want to deviate from the value that minimizes that part of the potential, And so therefore, any excitation in this mode requires energy regardless of the wavelength, and that gives rise to a mass energy in these excitations. Now, when you factor in the quantum nature of the condensate, it turns out that you can only excite this mode in discrete energy packets, and so therefore, there is going to be a mass gap in the system where if you want to excite an amplitude mode, you have to put in at least the mass energy required to excite that mode. Now, it's very difficult to excite an amplitude mode, and it's a very unstable form of energy. So, right after you excite an amplitude mode, its energy is going to scatter away into some more stable form. But still, there are ways to experimentally confirm that superconductors can host amplitude modes. Also, the amplitude mode of a superconductor is often called the Higgs boson of a superconductor. Not to be confused with the Higgs boson of the superconductor of the universe, but it is exactly the same idea. And that's why the discovery of the Higgs boson was such a big deal, because it showed that the superconductor thing is more than just an analogy, because it can be directly jiggled. If you've followed along with everything so far, then you're now in a great position to learn about the Higgs field, and to understand it in a genuinely deep and meaningful way that goes beyond the molasses analogy. Now that you know what a superconductor is, we can use the superconductor analogy. Okay, so when upgrading our mental image from a superconductor to the Higgs field, there is one extra bit of algebra that it's worth talking about for a moment, and that is SU2. Now, some of you are already familiar with SU2, and we talked about it in the spinner video, but let's just reflect on it for a moment. And also, there's a way of framing SU2 that segues nicely into the Electroweak model. So even though it'll seem like we're just talking about SU2 right now, we're actually setting the stage for Electroweak unification. Alright, so the easiest way to imagine SU2 is to start off by imagining U1, which we talked about at length in the last video. U1 is all the ways of changing a complex number without changing its magnitude. So it's all the ways you can swing around a complex number in the complex plane. Algebraically, we can encode these transformations as e to the I theta, which is a unit-length complex number with a phase angle of theta counterclockwise from the real axis. And because complex multiplication involves adding the phase angles of the numbers being multiplied, multiplying a complex number by the unit-length e to the I theta simply changes the number's phase angle by theta. We've used this idea a lot in previous videos, so that shouldn't really come as a surprise. But here's a cool observation. We can get from U1 to SU2 just by changing one word. SU2 is all the ways of changing a complex doublet without changing its magnitude. A doublet is a fancy way of saying pair. If you've ever seen two peas in a pod, then you're familiar with the concept of a doublet. It's just two of a thing that are to be regarded collectively as the same thing. I like to draw a doublet as 2 points in the complex plane, representing the two peas, with a little line connecting them representing the pod. So you see, a doublet is a cute thing, it's not a scary thing. There's no need to fear doublets. Doublets are our friends. And if you want to, you can think of a complex doublet as a vector in C2, but we don't even need to overthink it like that. A doublet is just two peas in a pod. And for understanding SU2, it's helpful to think with that level of structureless generality. You can, of course, use doublets to encode different things. For example, a spinor field can be written as a doublet-valued field, but the spinorial essence of a spinor comes not from it being writable as a doublet, but also the space-time transformation properties of the field that are governed by, for example, the Dirac equation. But anyway, all that's to say, a spinor field can be written as a doublet field, but a doublet field is not necessarily a spinor field. It could just be like a scalar field, in terms of how it transforms under Lorentz boosts. But the scalars have a form of a doublet. That's okay. And in fact, as we'll see, the Higgs field is a complex doublet scalar field. Anyway, I find that at first it's helpful not to get too hung up on the ontological meaning of a doublet. Just think of it as a kind of number. And usually we write a doublet as a column of complex numbers. So if we have a doublet named phi, we can write that as a stack of the complex numbers phi1 and phi2. So, what is the size of a doublet? Well, let's use the same idea as for a complex number. One of the fundamental rules of complex numbers is that the magnitude squared of a complex number phi is given by phi conjugate phi, right? Phi star phi. So then the magnitude of phi is the square root of phi star phi. We can apply exactly the same idea to a doublet, but instead of just conjugating phi, we also have to turn it over on its side so that it becomes a row vector, because then we can take the dot product and have the dimensionality work out correctly. And so actually the magnitude squared of a doublet is given by phi dagger phi, where the dagger symbolizes the transpose conjugate, which just means that we flip phi on its side and conjugate it. Why we use a dagger to symbolize flipping a thing on its side and conjugating it, I don't know. Maybe I don't want to know, but it is what it is. So the magnitude of phi is the square root of phi dagger phi. Okay, so let's return to our definition of SU2, all the ways of changing a complex doublet without changing its magnitude. Well, by inspection, a complex doublet has 4 degrees of freedom, 2 for each complex number. So then if we want to change a doublet while holding its magnitude constant, how many degrees of freedom do we have? 4 degrees of freedom, minus 1 because the magnitude is fixed, leaves us with 3 phase-like degrees of freedom. And so this SU2 group is going to have 3 generators, that is, 3 fundamentally distinct ways of rolling around in SU2. Now, when dealing with U1, we use e to the I theta to rotate a complex number by the angle theta. Similarly, when dealing with SU2, we can use 3 expressions to rotate a doublet around by 3 different angles in 3 different ways. And you can combine this into a big exponential of e to the I theta 1 tau 1 plus theta 2 tau 2 plus theta 3 tau 3, where the thetas you can think of as like phase angles, and tau 1, tau 2, and tau 3 are the Pauli spin matrices. You often see these matrices written as sigma, but in the Electroweak model, it's actually more common to write them as tau. Okay, so just by looking at these matrices, it's not obvious why they are what they are, or what exactly they do. And if this is your first time with matrix exponentiation, you might also be like, hold on, how do you exponentiate a matrix? But that's all just algebraic stuff that you learn along the way. The important thing is to see what SU2 transformations actually look like. So the animation here shows some example doublets being transformed. On the left we have tau 1, in the middle we have tau 2, and on the right we have tau 3. And you can see by looking at this that these are all like different ways of kind of rotating the peas in the pod, but it's not obvious how to make sense of this. And so it would be nice if we had a better way of visualizing doublets. A way that makes these SU2 transformations more easily digestible by the imagination. Because the complex plane peas in a pod picture is nice because we can directly see each part of the doublet. So it's a very direct and transparent window into the algebra, at least in terms of what the doublet is at each moment. But the problem is, when we look at SU2 transformations in this picture, the transformations are confusing and hard to describe. I mean, you can kind of get a sense that there are these 3 independent ways of swirling the doublets, but the motion doesn't quite click into the imagination in the way that we might like it to. Fortunately, there is a way of visualizing SU2, which makes the transformations themselves much, much easier to understand, but the cost is that the objects they transform become a little more abstract. And this is the flag picture that we saw in the spinner video and in the last video. Here's how the flag picture works. Any doublet can be drawn as a flag, in accordance with some equation. So there's some equation which you put in the doublet and it gives you the coordinates of the flag and how it's oriented. Now the details of that equation are actually not so important for now. All you really need to know for today's video is that a doublet can be depicted as a flag, and the how is not so important. Okay, of course, if you're really getting into this topic, then you should also learn the how. And you can find that in the paper An Introduction to Spinners by Andrew M. Steen, link in the description. The flag picture applies equally well whether you're dealing with spinners or doublets more generally, so spend some time with that paper if you're interested in the details, but we don't need to linger on those details today. Okay, so the reason I bring up the flag picture is that in this picture, the generators of SU2, that is the Pauli matrices tau, are very easy to visualize. Tau 1 rotates the flags around the x-axis, Tau 2 rotates the flags around the y-axis, and Tau 3 rotates the flags around the z-axis. So it's as simple as that. By representing the doublets as flags, we can imagine the Pauli matrices in terms of our natural intuition about three-dimensional rotations. That makes the math way easier. Also, a cool thing to know is that in this flag picture, a U1 transformation rotates each flag around its own axis. So you see that U1 doesn't go beyond what SU2 can do, in the sense that for any given U1 transformation on any given flag, we could also write that in terms of the appropriate SU2 transformation that gets you from the first flag to the second flag. And so U1 is just kind of a different way of transforming a flag. It's more narrow. SU2 goes beyond U1 because SU2 can, and usually does, change the flag pole orientation, whereas U1 only changes the flag orientation around its flagpole. And by the way, what is the deal with the flag? It's kind of a weird mathematical object, right? Well, it's just a thing that represents an orientation in 3 dimensions. If we instead used a line segment, well then there's the question of, what is the role of the line, So a flag is the kind of minimal object that lets us visualize a 3D orientation. It doesn't come as too much of a surprise that the 3 phase-like degrees of freedom of a complex doublet can be related somehow to the orientational degrees of freedom in 3 dimensions. What is surprising is that the phase-like degrees of freedom of the doublet actually double cover the 3D rotations, so that when a doublet does a full SU2 rotation and gets back to where it started in the complex plane, peas in a pod picture, it will have rotated twice in the flag picture. That's what people are talking about when they say that SU2 double covers SO3, where SO3, the group of 3x3 rotation matrices, is the group that's typically associated with rotations in 3 dimensions. But we already covered that in the spinner video, so let's not double cover it here. Haha. Oh, I'm the worst. Hey, while we're here, let's notice that SU2 transformations generally don't commute, meaning that if you apply 2 consecutive SU2 transformations to a doublet, it matters which transformation we do first. Starting with the same doublet, doing transformation A, then transformation B, will in general yield a different final doublet than doing transformation B, then transformation A. This is different than U1, where the order doesn't matter, because the phase angles just add, and order doesn't matter when you add 2 numbers. But because of the connection between SU2 and 3-dimensional rotations, we can see that SU2 matrices do not commute, that the order does matter, because that's a natural property of 3D rotations. In math, there are different kinds of proofs. Proof by deduction, proof by induction, proof by contradiction, proof by exercise for the reader, proof by it came to me in a dream, proof by pudding, so many kinds of proof. But what we're looking at now is my favorite kind of proof. The most zen flavor of proof. Proof by just look at it and see how it is. Suppose you have some object and you rotate it about the x-axis, then the y-axis. If instead you had rotated it first about the y-axis, then the x-axis, it would end up at a different final orientation. And so right there you can see an example of how 3D rotations do not commute. And we just picked the x and y axes as an example, but you can imagine any other axis of rotation, and you'll find that the only time 2 3D rotations commute is if the rotation axes are the same. Or 180 degrees opposite, that's okay too, because then you're just rotating in the same plane, and that's spiritually a 2D rotation, which does commute. Anyway, the reason I bring this up is just to show that it is totally natural and intuitive that SU2 matrices do not commute. This is not a bizarre thing. No, having seen that SU2 is related to rotations in 3 dimensions, we would expect these transformations not to commute. And on the topic of commutation, for what it's worth, SU2 and U1 do commute with each other. If you do an SU2 transformation followed by a U1 transformation, that's the same as first doing the U1 transformation and then the SU2 transformation. And the reason this works is that an SU2 transformation rotates a flag by a particular axis, X, Y, or Z, or some combination thereof, whereas a U1 transformation always rotates a flag by its own axis. So when you combine an SU2 transformation with a U1 transformation, you're just swinging the flag and then twirling the flag. And whether you do the swinging then the twirling or the twirling then the swinging, you end up at the same place. So SU2 and U1 commute with each other. So as you see, the flag picture teaches us a lot about the group theory of SU2 as well as U1. And very importantly, as we'll see in a moment, about the interplay of SU2 and U1. You can just think of it all in terms of how the flags rotate. And again, for now, you don't even have to be an expert on how to draw the doublet as a flag. Just know that it can be done, so that we have these two different windows into the algebra. On the one hand, we have the peas in a pod picture, where the complex components are readily visible, but the transformations are confusing. And we also have the flag picture, where the transformations are easy to understand, but the complex components are obscured and confusing. So you want to think in terms of both, because each has their advantages. Also, the fastest way to truly digest SU2 into your imagination is to get your hands dirty with some actual code. Math is a contact sport, and when you're actively wrestling with the equations, rendering animations with various parameters, and seeing how it all plays out, that is when the essence of the math really soaks into your soul and becomes a part of you. So, to that end, on my Patreon, you can download the animation codes that make these animations with the transforming doublets, with the SU2 and the U1 and the peas in the pod and the flags, and you can put in your own doublet or list of doublets and see what happens. And that'll turbo boost your learning experience. Now, these codes are primo content, exclusively available to those who have joined the club on Patreon. I hope you'll consider signing up, and hopefully this can be a mutually beneficial way to fund the channel. Sort of like selling books, if I write a book that you want to read, you can buy the book. Well, here's some codes that'll install in your mind a familiarity with SU2 and U1 acting on doublets. That's a great thing, right? Well, if that's something of value to you, then please consider joining the club and getting in on this mathematical adventure. Okay, so why have we been spending so much time talking about SU2 and U1 and doublets? Great question. It's because the gauge group of the Electroweak model is SU2 cross U1. And the Higgs field is a complex doublet scalar field that breaks down SU2 cross U1 into the U1 of electromagnetism that we know and love. So these insights about transforming doublets are exactly what we'll need in just a moment as we dive into electroweak unification. But first, let's take a step back from all this math and zoom way out and get philosophical and meditate on the nature of reality. The universe is a complicated thing. There's a lot of stuff going on, and there's also a lot of different kinds of stuff going on. But amazingly, when you really zoom in on this wild economy of cause and effect, you find that the dynamics of nature are governed only by 4 forces. Every push or pull that's ever been observed falls into one of these 4 categories. First off, we have gravity. That's when space-time gets curvy and time is no longer purely perpendicular to space. Fate picks out a preferred direction, stuff just goes in that direction as if enchanted by destiny. We call that falling, and on a cosmic scale you have stuff falling all around itself and swirling around and all that. So that's gravity. It's the way space-time gets weird and curvy under the influence of matter and energy. Then we have electromagnetism, good old local phase symmetry. And this comprises most of what we know and love. Not only electricity and magnets, but also things like chemistry and friction and contact forces and basketball and even your own DNA, and the way molecules behave, is an electromagnetic phenomenon. Common sense can be summed up as a pragmatic understanding of electromagnetism and gravity. For all intents and purposes, those are the only 2 forces that we interact with in a meaningful way. The other 2 forces, the nuclear forces, are not nearly as familiar to the imagination. So first up, we have the weak force. Based on the name, you might think that this force is weak. But it's not exactly weak. It's more like a turned-off force. If 2 particles are very, very close together, like within 10 to the minus 18 meters, which is about 1,000 times smaller than the nucleus of an atom, then the weak force is active. Actually, at that very close range, the strength of the weak force is suspiciously similar to the strength of electromagnetism. But then if the particles are even slightly farther apart, say just 1/10 of an atomic nucleus away from each other, then the weak force is completely turned off. It's as if there's something in the vacuum of space itself which swoops away the weak force, so that its effect can't penetrate more than some distance lambda away from a particle. And that's a little something called foreshadowing. Okay, but hold on. How do we even know that the weak force exists, if it only acts over such a short length scale? Well, nowadays we have particle accelerators that can directly probe that length scale, by smashing particles together with extreme energy, smushing them right up next to each other. But even without those fancy accelerators, we see traces of the weak force in nature. So the weak force is mediated by the W+, W-, and Z bosons. And we'll talk more about those later on, but for now, just think about those as sort of like photons, except they're really massive, so they're not often created, and they don't like to exist for very long. And as the name suggests, the W+ boson carries a positive electric charge, W- carries a negative charge, and the Z boson carries no charge. And one of the ways that we see the weak force in nature is when an atom undergoes beta decay. So what'll happen during beta decay is that a neutron in an atom converts into a proton and emits an electron and an electron antineutrino. But behind the scenes, what's really happening there is that within that neutron, you have a down quark that is turning into an up quark and a W- boson, and then that W- boson is decaying right away into an electron and an electron antineutrino. And, atoms, sometimes they undergo beta decay. That's just a way that elements be transmutant sometimes, and it's an indication that the weak force is a thing. And you can also have beta plus decay, which is a very similar process, but involving a W+ boson. So this has been observed in nature, it's a known effect, and so that's how we know that the weak force is a thing. But also, while we're here, this is kind of a tangent, but it's really cool. You should look up the Super Kamiokande detector. This is a neutrino detector in Japan, and it's really cool. It's like a kilometer underground, and the way that it works is that it has 50,000 tons of ultra-pure water, and it's way underground, so there's no light or anything. It's super, relaxed. And you've got these neutrinos, and a neutrino you can think of as like an electron that has basically no mass and no electric charge. And you have a bajillion neutrinos flying through all the time, like flying through you right now. So in this cave underground with all the water, there's a bunch of neutrinos going through. Neutrinos don't interact electromagnetically, so they normally just pass right through ordinary matter. But they do interact via the weak force. And so every once in a while, a neutrino comes through and it interacts with the water molecule via the weak force, and then it emits some light, and the light goes into the detectors. And based on the pattern, you can figure out where the neutrino came from. And so in that way, this cave full of water serves as a kind of camera that sees with neutrinos instead of light. And this is really cool. So here's a picture of the sun that was taken with neutrinos at the Super Kamiokande detector. And the crazy thing is, these neutrinos came through the Earth, because the Earth is almost entirely transparent to neutrinos. Oh, you know what? There's one more thing about neutrinos you have to know. And this is going to blow your mind. It makes no sense, but it's true. Every neutrino that's ever been observed has been left-handed. Meaning that if you take your left hand and you point your thumb in the direction of motion of the neutrino, then your fingers are going to curl around like the spin angular momentum of the neutrino. Now this is super weird, and it should keep you up at night, and it should give you kind of an existential crisis, because we would expect for neutrinos to be half of the time left-handed and half of the time right-handed, right? Like photons. But that's not the case. They're all left-handed. I don't know. It makes no sense. It's literally a glitch in reality that does not have an explanation. As we'll see later in the video, we can model this. We can bake this mysterious chirality into our description of nature. But that doesn't explain where the chirality comes from. Oh, by the way, the W bosons only interact with left-handed particles. The Z bosons interact with both left-handed and right-handed. Well, anyway, there's some very weird, very strange chiral stuff going on in the electroweak sector, as we'll talk about later. So anyway, that's a little bit about the weak force. And last but not least, we have the strong force. This is the force that binds quarks into protons and neutrons. A proton is two up quarks and a down quark, bound into a trio of quarks by the strong force. Likewise, a neutron is two down quarks and an up quark. And when you have multiple protons and neutrons together, as in the nucleus of an atom, the strong force from within each proton and neutron sort of leaks out. And the residue of that force is what binds the protons and neutrons together into the nucleus. And that is what makes the nucleus stable. Because if it were just electromagnetism, the protons would all repel themselves and the nucleus would go flying apart. but it's the residual strong force that holds the nucleus together. Now, that effect starts to weaken if the nucleus gets too big and things get too far apart. Then electromagnetism takes over, and then the nuclei go flying apart, and so that's why the heavier elements are unstable. Well, anyway, there's a lot to be said about the strong force. Much like electromagnetism blossoms from U1 symmetry, the strong force blossoms from local SU3 symmetry. SU3 has 8 generators, and so you end up with 8 gauge fields, the gluon fields. But let's not get into that today, okay? In fact, for today, let's not worry about gravity or the strong force. Don't float away and don't explode, but let's just focus on electromagnetism and the weak force so we can see what's going on with them and what secret relationship they have, and what that can tell us about the Higgs field and the nature of things. Actually, we'll get back to electromagnetism and the weak force in just a moment, but first, there's a thought experiment that we should perform in the laboratory of the mind, and that is, what would it look like if space itself were superconducting? Well, suppose we have a bunch of particles floating around and bumping into each other and interacting electromagnetically, and we'll use this blue glow as a kind of way of visualizing the electromagnetic interaction. So maybe that represents the electric and magnetic field strength, and we're being a little bit vague on what exactly it means, just, it's poetic license, okay? But the point is, now, if we make space superconducting, then the electric field is going to get swooped away, the magnetic field is going to get Meissner Effected away, and all of a sudden, now this blue glow of electromagnetic field, it goes away. Because photons are massive now, they can't propagate very far, and so the electromagnetic influence of a particle on its environment, it just doesn't extend anymore. I mean, okay, maybe it extends some distance lambda and then it gets attenuated, and so maybe two particles that happen to be very close range with one another could still interact electromagnetically, if they're within a lambda or so. But aside from that, the long-range electromagnetic interaction of the particles would have been turned off, because the medium in which the particles exist, the space in which the particle exists, is now superconducting, and so it does not allow for a photon from one particle to travel over to the other particle, right? It's a whole different kind of medium. So the reason I bring this up is to say that if our universe were superconducting, then electromagnetism would be turned off. And by turned off, what I mean is that it would acquire some very close-range length scale, beyond which the force effectively wouldn't occur. But if you're within that length scale, then the force still exists, and at that close range, asymptotically, it's still as strong as it ever was. It's just that, you go out a little ways and the superconductor turns it off. Now, given this thought experiment, and given the fact that electromagnetism in our universe is a long-range force, we know that we are not living in a superconductor. But what do you make of the fact that the weak nuclear force has been turned off in precisely this way? Oh, ho 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 ho. You picking up what I'm putting down? You see what I mean? We are living in a superconductor. It's just not exactly the same superconductor as a superconductor that is a superconductor. It's the superconductor that is the universe in which we live. Do you see it? Isn't it incredible? It just gives you like a moment of whoa. And it changes your life forever. It's a subtle thing, but just to sense that there is a water in which we swim, it's remarkable. So what do you make of that, huh? I'll tell you what I made of it. As soon as I had that realization, I'm like, oh, I gotta make a video on this right away. I read Lance's paper and I'm like, oh yeah, no, this is the next video right here. Hydrogen 3 can wait. I gotta tell the world about superconductivity in the Higgs field. Okay, so are electromagnetism and the weak nuclear force secretly related somehow? Well, let's do a little compare and contrast. So with electromagnetism, the force carrier is the photon. The photon is a vector boson. It's an excitation in the 4 potential A mu. Photons are massless, and so they have infinite range. So that lets us see galaxies that are like super far away because the photons are able to travel all the way from there to here. Also, the photon itself carries no electrical charge. Charged matter has charge, but the photon itself does not have charge. And the principle of local phase symmetry blossoms into electromagnetism. On the other hand, if we look at the weak force, we find 3 force carriers. We have the W+, W-, and Z bosons. And these are all vector bosons, and they have spin 1, just like a photon. But unlike a photon, they are massive, like really massive. And because these particles are so massive, they're really unstable, and so they just don't propagate very far before they decay. And how massive are they? Well, we're talking for the W's, 80.4 GeVs. The Z's are like 91.2 GeVs. And just for context, this is like over 100,000 times the mass of the electron. So that's quite different than a photon. There's a big difference between zero mass and a lot of mass. And to make matters even more confusing, the W bosons have electric charge. W plus has positive charge and W minus has negative charge. So that's confusing because photons don't have charge, so ostensibly that's a difference between the weak force and electromagnetism. But then also it's like, wait a minute, they have electric charge. And that seems like an electromagnetic thing, so maybe there is some kind of underlying unity between electromagnetism and the weak nuclear force. And then you look at the Z boson, and it's electrically neutral. It doesn't have any charge at all. One way to remember that is think of Z means zero charge. I don't know if that's actually why they named it that, but hey, it works. And then what about the gauge group of the weak force? Because when you look at electromagnetism and you see that the whole thing is reducible to this local U1 symmetry, naturally the question arises of maybe we can account for the weak force using similar principles. But in that case, then what kind of symmetry group would we need in order to generate the three bosons of the weak force? It'd have to be something involving 3 degrees of freedom, right? Because you would have like these 3 different ways of messing up your wave function, and then you'd have to have 3 fields that can come in and clean that up. So maybe there's something where like there's some 3 degree of freedom symmetry group that might give rise to the weak force. Well, actually, the answer is a little bit more complicated than that. But it's complicated, but it's also simple. So it is what it is. It's elegant and interesting. So let's take a look at how electromagnetism and the weak nuclear force are indeed 2 sides of the same coin. So in our observed reality, we see electromagnetism and the weak force as like 2 totally different things. Electromagnetism is the manifestation of local phase symmetry. It involves a massless gauge field, and that enables infinite range. On the other hand, with the weak force, we have the W's and the Z, very short range, cutoff length scale of 10 to the minus 18 meters. Seems like it's totally different. But the key to understanding how these things are related is to understand the Higgs mechanism. Very similar to the Anderson-Higgs mechanism. But underneath the Higgs mechanism, the source of both electromagnetism and the weak nuclear force is the electroweak interaction. And this is based on the symmetry group SU2L cross U1Y, that we'll go into in more depth in just a moment, but that symmetry group gives rise to 4 massless gauge fields, W1, W2, W3, and B. The W's are the gauge fields of weak isospin, and B is the gauge field of hypercharge. And if not for the Higgs field, all 4 of those gauge fields would be massless. But because of the Higgs field, which happens to have 3 phase-like degrees of freedom, you're actually going to end up with 3 massive gauge fields, and 1 gauge field that remains massless. And it's not as simple as the B just getting split off from the W's, but it's actually more complicated because the Higgs mechanism actually mixes together W3 and B, as we'll see in a moment. But this is the big picture of how the electroweak interaction gives rise to electromagnetism and the weak force. It's all about the Higgs mechanism. And that's why we're talking about electroweak unification, because if you want to understand the Higgs field, you have to understand it in the context of electroweak unification. The Higgs field is really the star of the show when it comes to seeing how electromagnetism and the weak nuclear force are actually 2 sides of the same coin. Or 2 peas in a pod. Or actually, I guess 4 peas in a pod. 1 pea from the electromagnetism and 3... Okay, I'm overdoing this. Moving on. Alright, let's take a look at the gauge group of the electroweak interaction. This is SU2L cross U1Y. First of all, starting with the U1, as we've seen, this is just all the ways of rotating around a complex number in the complex plane. And SU2 is all the ways of swinging around a complex doublet without changing its amplitude. So what's the deal with the subscript L and the subscript Y? Well, in the electroweak model, this U1 is actually not the same U1 as electromagnetism. This is actually the U1 of something called hypercharge. And so we use Y to symbolize hypercharge, I think because Y rhymes with hyper. It's a mid-rhyme, according to the haters. Anyway, what this does is when we put a U1 gauge symmetry into the model, this is going to give rise to the hypercharge gauge field, And in your mind, you can imagine this as exactly the same as the electromagnetic 4 potential A mu, except we're not in our observed reality yet. We're in the, let's call it a hyper reality before we put in the Higgs field, okay? So if you followed along with the last video, then you'll be well aware of what happens when you give your model a local U1 symmetry. You end up with a 4-vector field that can augment the energy and momentum of particles within your model. And so the idea of the Electroweak model is that part of it is a kind of local U1 symmetry like we saw for electromagnetism, but that's actually not the full story, and that's actually not the U1 of electromagnetism. As we'll see in a moment, the U1 of electromagnetism is kind of like a slice through the space of SU2L across U1Y. We'll articulate that more precisely in just a minute. But I think the more interesting part of the Electroweak gauge group is SU2L. So the L means left-handed. And one of the most unusual things about the Electroweak model is that it treats left-handed particles and right-handed particles differently at a fundamental level. So a particle is left-handed if, imagine it's moving away from you and it's turning counterclockwise, and it's right-handed if, as it moves away from you, it turns clockwise. One way to remember this is it's sort of like a football. If you throw a football with your right hand, it's going to spiral like a right-handed particle, and if you throw it with your left hand, well, then it'll be like a left-handed particle. Now, in the Electroweak model, at first, none of the particles have mass. So there's no mass involved, and so we don't have to worry about the difference between helicity and chirality. Everything's massless, everything's moving at the speed of light, and so each particle has a well-defined left-handedness or right-handedness. And so we take it as a first principle in the Electroweak model that this SU2 symmetry only applies to left-handed particles. And how does it apply? Well, the way it applies is that if the particle is left-handed, it's going to be able to transform as a doublet under SU2. So for example, consider this doublet on the left. We have an electron neutrino up top and an electron on the bottom. And even though the neutrino's wave function and the electron's wave functions are themselves spinor fields, you can imagine this doublet as sort of encoding a complex superposition of those wave functions. And then the idea of local SU2 symmetry is that you can transform that superposition of the neutrino and the electron arbitrarily under an SU2 transformation. And that's not going to change the size of the doublet, that's not going to change, the overall amplitude of the superposition or anything like that. It's just going to mix around or kind of spin around the neutrino and the electron in the doublet. And the same goes for the up quark and the down quark. So if you have a left-handed up quark and down quark, those also are going to be able to transform under SU2 as a complex doublet. So what is the consequence of putting an SU2 symmetry into the model? Well, what's going to happen is it's very similar to local U1 symmetry giving rise to a 4-vector field. And in fact, it is actually quite similar. Instead of 1 degree of freedom giving rise to 1 gauge field, we have 3 degrees of freedom, giving rise to 3 gauge fields. These are the so-called weak isospin gauge fields, W1, W2, W3. And as a good starting point, you can imagine that these are very much like the gauge field B or A, but with the important caveat that because SU2 does not commute, the weak isospin gauge fields, W1, W2, W3, are also going to be able to interact with each other. So when you're looking at a Lagrangian that involves the weak isospin fields, in addition to the usual contributions from the field strength tensors, which we saw in the last video, we're also going to have a self-interaction term. But now, today, we don't have to go into too much detail on that. And by the way, let me just say this. The Electroweak model is a very complicated thing, and there's a lot to it. And I know I'm probably not going to do it justice today in terms of giving you a comprehensive overview of the Electroweak model. It's like a big thing. What I'm hoping to do here is to show you enough of it that you really get a good sense of what the Higgs field is and what it does. And then also, to the extent that this part of the video is going to raise more questions than it answers, I hope that those questions are going to lead you in a productive direction as far as what to study next. If you're interested in the Electroweak model and you want to learn more about it, definitely check out that book by Chris Quigg. It's a fantastic book. Okay, so back to the Electroweak model. In the Electroweak model, and actually in the Standard Model more generally, we have 3 generations of matter. So all the matter that we're familiar with is from the first generation. Our atoms are made up of electrons and up quarks and down quarks. But in addition to all of these particles, you also have the second generation and the third generation, which is just a copy and paste of the first generation, but the second generation is more massive, and the third generation is even more massive. But other than that, it all seems like a copy and paste. And we still don't know who ordered that. We still don't know why that is or whatever. But, anyway, it's just we have to factor that into our description of nature. So that is what it is. So in the second generation, we have the muon neutrino and the muon. We have the charm quark and the strange quark. And in the third generation, we have the tau neutrino and the tau, as well as the top quark and the bottom quark. Back in the groovy days, they used to call that the truth quark and the beauty quark. But then it became hip to be square, so now we have to be serious, and we have to call it the top quark and the bottom quark. You'll notice in this model, there is no such thing as a right-handed neutrino. And that matches what has been observed in nature. All of the neutrinos observed so far have all been left-handed, and it's an open question as to whether right-handed neutrinos exist or not. If they do, maybe they're sterile and they don't interact for some reason. For now, I just want to point out that based on the fact that no one's ever observed a right-handed neutrino, in the Electroweak model, they simply do not exist. And similarly, the other right-handed particles, the electrons and quarks and muons and tau, if it's right-handed, it does not transform under SU2. And so it doesn't couple to the W gauge fields. It only couples to the hypercharge gauge field if it's right-handed. So you can see that we build in the mind-blowing chirality of the weak interaction into the first principles of the Electroweak model. So it's not an explanation of where the chirality comes from, but it is a description of the situation. It remains a big mystery, even to this day, what the deal is with the chirality and the weak interaction. This is like a super deep mystery. And when you think about it, it's hard to even imagine what an explanation for that would look like. It's one of those mysteries that seems to defy not only explanation, but imagination. So we'll save that for future generations to figure out. But in the meantime, let's just work with what we know. Oh, and one more thing while we're here is notice that when you have these doublets that transform under SU2, what we're saying there when we're putting in an SU2 symmetry is that we should be able to arbitrarily apply an SU2 transformation to our left-handed particles, and that's going to mix the components of the doublets around. So suppose we have just an electron. Well, we can transform that into an electron neutrino, and that doesn't change the description of the situation, so long as we also transform these W fields in the corresponding way. So that's a very, very mysterious thing because it tells us that, in some sense, the neutrino and the electron are sort of the same particle. I mean, it's super weird. It's like, what do we even make of that? It's hard to say. But it is what it is, so we'll take that as a starting point for today. So the Electroweak model, it's very mysterious and it's very like, whoa, what is this? How can this be? And in particular, there are actually two problems with the model, or two apparent problems that are like really problematic. The first is that the Electroweak gauge fields, the isospin fields W and the hypercharge field B, these are massless. And we know that they have to be massless because it's the nature of a local symmetry that you can mess up your wave function by an arbitrary amount here versus there, now versus later. And so when you apply this arbitrary SU2L cross U1Y transformation and you're messing up your wave functions, you can do it in a very scrunchy, very floppy way, or you can do it in a less scrunchy and more relaxed way. And depending on the intensity of your transformation, you're going to have to pull in more or less W and B. And so therefore, there cannot be an energy cost or benefit that depends on how much of the isospin fields or how much of the hypercharge field you bring in. This is the exact same reasoning we saw in the last video when we demonstrated that the photon has to be massless. And so if we want our Electroweak model to be able to give us the massless photon field, but massive W and Z fields, this is like a major problem. Because in reality, the weak gauge fields have mass, but in the Electroweak model, very clearly they don't have mass. And to make matters even worse, we have another major problem with the Electroweak model, which is that only the left-handed particles transform under SU2L, and so only the left-handed particles feel the isospin gauge fields. So why is that a problem? Well, aside from being weird, it's okay that it's weird, but the problem is one observer's left-handed particle might be another observer's right-handed particle, depending on their velocity, if the particles had mass. Because if the particle has mass, you can always Lorentz boost into a reference frame where the particle is going the other way but still spinning the same way. And so one observer's right-handed particle could be another observer's left-handed particle if the particles have mass. And then the question becomes, well, okay, the two different observers are going to disagree on whether or not that particle transforms under SU2L and whether or not the particle feels the weak isospin gauge fields. And so if our matter particles have mass, then there's this inherent incompatibility with the idea of an SU2L gauge field in the context of special relativity and different inertial frames. It just doesn't work. And the only way to solve that is to say, okay, all of our matter particles are massless, so therefore there is no reference frame where you can boost it the other way and have it going the other way. No, a massless particle is going to be left-handed or right-handed, and all observers are going to agree on that. And so if we want the Electroweak model to be logically coherent, all of the matter content has to be massless, but of course, in reality, matter has mass. So what's up with that? Now, these two problems are very severe. I mean, you would think just throw away the model, like this doesn't work at all, like not even remotely, right? But instead of just throwing it away, we're going to do something even crazier. We're going to spill a superconductor into it. And this is going to be a special kind of a superconductor, okay? This is the Higgs field we're talking about. So we're going to use the symbol phi instead of psi. So notationally, it's a little different, but it's kind of similar. Also, the Higgs field phi is going to be a complex doublet field, so that it can transform under both SU2L and U1Y. It has to be a doublet, because if it were just a single complex-valued field, it wouldn't be able to transform under SU2. So the Higgs field is going to be a complex-valued doublet field, and it's going to transform under Lorentz boosts as a scalar. So it's not going to be a spinor field, it's just going to be like a relativistic Lorentz invariant scalar field. Now when we do this, when we put our superconductor into the Electroweak model, a miracle happens. The Higgs field phi is going to transform the massless isospin and hypercharge fields into three massive gauge fields, the W+, the W-, and the Z of the weak force, and one massless gauge field, A mu, the photon field. And that breaking down, we can understand entirely in terms of superconductivity. All you do is you imagine some Nambu-Goldstone modes in the Higgs field, and then you hop into the unitary gauge, and you calculate the amount of energy in the fields, and that gives you the mass term, and you get the mass, and you can show that it's massive, and then you can show the photon has no mass. We'll get into that in just a second. It's really an amazing thing, the Higgs mechanism. And this is so cool, but okay, so we bring in the Higgs field to fix the Electroweak model, to give the W's and Z mass, to leave the photon massless, and while we're doing that, we bring in a prediction. Because if the Higgs field is like a superconductor, then it should have an amplitude mode. And that's the Higgs boson. That's what the Higgs boson is. It's the amplitude mode of the superconductor that is the Higgs field. So that is a really fantastic prediction, because it's highly non-obvious that space-time itself should be excitable like a superconductor is excitable. But if that turns out to be true, and okay, spoiler, the Higgs boson was discovered in 2012, so it is true, then it's like, whoa, this thing about unifying electromagnetism in the weak force led to this prediction about space-time itself having a superconducting kind of essence, and then the amplitude mode was discovered. It's like, wow, that's really cool. Oh, and one more thing while we're here is the Higgs field phi is also going to give mass to the matter particles in the Electroweak model via their Yukawa couplings. Now, how exactly the Yukawa couplings work is still deeply mysterious. There's actually not a good answer, and so it kind of goes beyond the superconductor analogy. But long story short, the Yukawa couplings provide a way for the gauge group of the Electroweak interaction to be compatible with special relativity. So we'll briefly look into that in a little more depth towards the end of the video. All right, let's get existential. So imagine some space with nothing in it whatsoever, where all that's there is that it's there. No dust, no atoms, not a thing at all. The darkest silence. A perfect vacuum. How dreadful! A sane person thinks nothing of it. A physicist stares into the void and writes a Lagrangian. Because, as you now know, empty space is not empty. It's a superconductor in hyperreality. We can no longer take comfort in the naive innocence of youth. Now we have seen too much. So, let us write a Lagrangian about nothing. We'll start with the idea that the vacuum of space is not empty, and that we're living in a superconductor that we'll call phi. Now, if phi is a superconductor, then it should have the kinetic and potential energy of a superconductor. The kinetic energy term in the Lagrangian is going to be the magnitude squared of the Gauge-Covariant Derivative acting on phi. In essence, this is exactly the same as just writing out the amplitude squared of the Gauge-Covariant Derivative acting on phi, but to be technical, because phi is a doublet, we have to do the thing with the transpose conjugate with the dagger. And also, because phi is relativistic, we have to take our derivatives in a way that makes Einstein happy. So we have the product of a Lorentz covariant gauge-covariant derivative and a Lorentz contravariant gauge-covariant derivative, so every inertial observer can agree on this. Now, the gauge-covariant derivative for the Higgs field is not the simple gauge-covariant derivative that involved the magnetic vector potential, because remember, the Higgs field lives in the electroweak hyperreality. Now, hyperreality is not a technical term, but it's a term that fits really well, so I'm going to keep using it. Anyway, the gauge-covariant derivative is the same basic idea as what we saw before, where you have a foregradient, and then you're adding in some gauge fields. So in the case of the electroweak model, we have the weak isospin fields W, corresponding to the Pauli spin matrices tau, and we also have the hypercharge field B, corresponding to the hypercharge assignments Y. The hypercharge Y is just a scalar quantity. And we'll get into what the hypercharge means later on, but for now, capital Y, just know that for the Higgs field, that's just the number 1. So for now, you can really just ignore that capital Y, and then you can see that the essence of this hypercharge term is very much similar to the electromagnetic four-potential term in electromagnetism. By the way, everything we're doing from now on in this video is going to use natural units. When you're dealing with the standard model and stuff, you get a lot of terms and a lot of characters, and we don't want to be carrying around h-bars and c's all over the place. So h-bar equals c equals 1 from now on. Also, you'll notice G and G prime. These are the SU2L coupling constant and the U1Y coupling constant, respectively. And those coupling constants set the strength of the weak isospin and hypercharge gauge fields, respectively. So G and G prime are very analogous to the electric charge E, and in fact, they're deeply related as well. Okay, so that's the gauge-covariant derivative. And the cool thing about what we'll be doing today is when we're looking at how the Higgs field gives mass to the W and Z bosons, all we have to do is evaluate the magnitude squared of the gauge-covariant derivative acting on phi as we hop into the unitary gauge. So we don't even have to go into that much detail on how exactly the electroweak gauge transformations work. As we'll see in a moment, the Higgs mechanism and the W and Z mass calculations are actually a really nice introductory exercise in sort of dipping a toe into the electroweak model without getting too technical. Alright, so the Lagrangian is kinetic minus potential energy. Lagrangian density and energy density if we're being technical. And so in our expression, we're also going to have some kind of potential energy, which is a function of phi. And because phi is like a superconductor, we would expect that to be the Ginzburg-Landau potential energy. So, Ginzburg-Landau is alpha times magnitude psi squared plus beta over 2 times magnitude of psi to the fourth. Well, when you translate that into Higgs language, the same exact idea is written as negative mu squared phi dagger phi plus lambda times phi dagger phi squared. And although it looks different, it's actually exactly the same thing as what we saw before with the alpha and the beta. Because if you look at the green term that I put up there for reference, the potential of a superconductor, you can see that alpha is negative mu squared, beta over 2 is lambda, and the magnitude squared of psi is the magnitude squared of the Higgs doublet, which is phi dagger phi. So therefore, the magnitude to the fourth of psi is phi dagger phi squared. And so even though the Ginzburg-Landau potential is dressed up differently here, it's still exactly the same idea. And it's still going to give us a sombrero potential in the magnitude of the Higgs field. Though, of course, now that phi is a doublet, it has 3 phase-like degrees of freedom. But never mind that for now. First, thinking purely in terms of the magnitude, we can see that the Higgs field is going to take on a non-zero vacuum expectation value. Oh, by the way, when people talk about vacuum expectation value, they call it VEV. That's what everyone says. VEV. Okay, so let's calculate the VEV. If we take the mass parameter of the Higgs field, that's that mu factor, experimentally, we know that mu is about 88.4 GeVs. And there's also the self-coupling constant lambda, and experimentally, that's going to be about 0.129. And then, as we talked about before, you want to think about negative mu squared as being alpha, think about lambda as being beta over 2, and think about phi dagger phi as being the magnitude of psi squared. And then remember before, way back, when we calculated the density of a superconducting condensate, and we found that it was the square root of the absolute value of alpha over beta? Well, if you apply the same reasoning here, then you find that the magnitude of phi is going to be the square root of mu squared over 2 lambda, and you can take the mu squared out of the square root, so you can write that as mu over the square root of 2 times lambda. So yeah, that's how the magnitude of the Higgs field in the vacuum state relates to the mass parameter and the self-coupling constant. Conventionally, we write the Higgs doublet as 0 v over root 2, where the square root of 2 is just a conventional normalization factor, and v is the Higgs VEV, the vacuum expectation value, but we call it a VEV because we're cool, and cool people say VEV. So the VEV is going to be mu over the square root of lambda, which you can see by looking at the equation we just found for the magnitude of phi. And so if you plug in the value of 88.4 GeVs for mu and 0.129 for lambda, you'll find that the Higgs VEV is 246 GeVs. Let's take a graphical look at what the Higgs doublet looks like, in both the peas in a pod picture as well as the flag picture. So the Higgs vacuum state is a doublet that we write as phi. Phi plus is an electrically charged scalar field, and phi 0 is electrically neutral. But never mind that for now, we'll come back to that later. For now, the thing to know is that this doublet is 0 v over root 2, so if we plot this doublet in the complex plane peas in a pod picture, you see that the top component is going to be at the origin, and the bottom component is going to stick out along the real axis by an amount v over root 2. Now, as we've seen, the magnitude of phi, and so the value of v, is determined by the Ginzburg-Landau potential part of the Higgs. You know, that sombrero potential. But then there's still the question of what are the phase-like degrees of freedom, because a doublet has 3 phase-like degrees of freedom. Well, by convention, we set the top component of the Higgs doublet to 0, and we make the bottom component of the Higgs doublet real. And so of all the possible doublets that have the same magnitude, that conventional choice is why we're dealing with 0 v over root 2 in particular. And as we'll see later on in the video, the fact that we're defining the top component to be 0 is intimately related to the fact that the top component represents a charged scalar field, and the bottom component represents a neutral scalar field. And so you don't have to wonder, why is it that the Higgs field spontaneously broke with a phase that just so happens to have a 0 top component? No, that's just a matter of convention. We could reformulate the entire Electroweak model with an arbitrary Higgs doublet, but then everything just gets more messy, and there's no point in doing that. Alright, well, because our doublet has 0 in the top component, when we look at it in the flag picture, it's going to be pointing straight down. And so when you imagine SU2 and U1y transformations acting on the Higgs field, one of the ways we want to imagine that is rotating this downwards flag. Okay, and so the Higgs vacuum state is this doublet all throughout spacetime. So it's a nice constant doublet field. Imagine a field of these doublets, the same exact thing everywhere, all over the place. That's the Higgs field. But now the question is, hold on. Can we have Nambu-Goldstone modes in the Higgs field? Like the phase waves we saw in the superconductor, can we have those kinds of oscillations in the Higgs field? I mean, we're going to have 3 degrees of freedom instead of 1, but other than that, it's the same basic question, right? We kind of would expect to have Nambu-Goldstone modes here. And that is a very interesting line of reasoning. And as we're about to see, that line of reasoning is going to let us calculate the masses of the W and Z bosons. So, before, when we looked at a superconductor that was just chilling with no magnetic field, we realized, wait a minute, there could be phase waves potentially, but then we thought like, well, okay, yeah, but those phase waves can be gauged away, and then you'll end up with an irrotational part of the vector potential, and that gives you longitudinal modes, and so then the photons become massive in the superconductor. Okay, now we're going to take exactly the same idea, but apply it to the Higgs field. Now, it's a little bit different, because the Higgs field is like an upgraded superconductor. You know, it has the two complex numbers. And so instead of one phase-like degree of freedom, it has three. And okay, so that's a little extra complexity, and maybe we can symbolize that with like an RGB color space or something. You know, you can imagine having Nambu-Goldstone modes in the Higgs field, and it's just sort of more complicated, more degrees of freedom. But still, if we hop into the unitary gauge, well then we can erase those Nambu-Goldstone modes by definition, but their energy still has to exist somewhere, and if we let the Nambu-Goldstone modes drag us around in the space of gauge-equivalent descriptions of the situation, in other words, we say, okay, we're going to go into the unitary gauge, so we're going to demand that the Higgs field phase is locked to a certain value, fine, but the energy contained in those Nambu-Goldstone modes is now going to pop out as irrotational additions to the three gauge fields that we need in order to put the Higgs field into the unitary gauge. So in essence, this is exactly the same idea that we looked at earlier when we were looking at the Anderson-Higgs mechanism in a superconductor. The long and the short of it is, the Nambu-Goldstone modes in the superconductor get eaten by the gauge fields and give them an irrotational component that manifests as longitudinal polarizations. And once your vector field is able to be longitudinally polarized, then it's no longer massless. Now it has that third degree of freedom and it corresponds to a massive vector field. Okay, so you start with the assumption that the Higgs field is like a superconductor. And then you follow exactly the same thought process of, all right, it's going to have Nambu-Goldstone modes. But wait, those waves are exactly the kind of thing that can be gauged away. So you hop into the unitary gauge, the Nambu-Goldstone modes go away, but then your gauge fields pick up a kind of energy that gives them mass. And we're going to dissect this in more mathematical detail in just a moment. But first, I just want to emphasize that these two pictures on the left and right, these are gauge equivalent. They both describe exactly the same physical situation by the SU2L cross U1Y gauge symmetry of the Electroweak model. We're allowed to hop into the unitary gauge, that's totally fine. And so when you think about it, if you have a complex doublet superconductor filling all throughout space, and you equip that field with the gauge symmetry of the Electroweak model, well, that's going to be indistinguishable from an empty vacuum with three of those gauge fields having acquired mass, corresponding to the Higgs field's three phase-like degrees of freedom. And there's some nuances about the mixing of the third component of the SU2 group with the U1Y, and we'll get to that in just a moment. But the thing I want to emphasize is that when you see the masses of the W and Z fields, one of the ways you can read that, one of the ways you can interpret and imagine that, is as space being filled with a superconductor, and this is like a gauge-equivalent way of thinking about the nature of things. But it gets even better, because actually these two pictures are only mostly indistinguishable. Because the thing about the Higgs field is, yeah, it has three phase-like degrees of freedom, and yeah, those can give mass to the three vector fields that they correspond to, but the Higgs field is a complex doublet. It has 4 degrees of freedom total, 3 that are like a phase and 1 amplitude. And so if this Higgs field really exists, and is not just some kind of accounting trick or mathematical construct, then it has to exist all the way, and so it should also be able to host amplitude modes. And so you don't see it in this picture of the Nambu-Goldstone modes and the unitary gauge and the gauge bosons acquiring mass, but when you think about the consequences of what has to happen if we're really to take this seriously, you realize, okay, well, this model seems to very clearly predict that empty space itself should be excitable like a superconductor is excitable in terms of the amplitude mode. And that brings us to a little something called the Higgs boson. But let's not get ahead of ourselves. I believe we have to calculate some W and Z mass, okay? Okay, so to do these W and Z mass calculations, we're going to split up the problem into 2 parts. So rather than considering the Higgs field with its full 3 phase-like degrees of freedom, and the W and Z fields together, first we're going to look at the Higgs field with just the 2 degrees of freedom corresponding to tau 1 and tau 2, which corresponds to the W gauge fields. And that'll let us calculate the W mass by hopping into the unitary gauge and calculating how much energy is associated with how much W we have. And then, after we do that, we're going to consider a Higgs field with Nambu-Goldstone modes corresponding to just tau 3, which corresponds to the Z field. And the Z field is going to emerge as a combination of W3 and B as we're doing the mass calculation. And then once we see the combination of W3 and B that becomes the Z field, we can take the orthogonal combination and we can associate that with the photon field, which is going to remain massless. So I just bring this up to say that we're going to treat the W's and Z's separately, although it should be pointed out we don't have to do this. If we wanted to, we could keep everything together, and we could do the W's and Z's all at once. It would just be a bit algebraically messier if we do it that way. So let's go ahead and split it up into W's and Z's. Oh, there's something I have to say about the W plus and W minus bosons. So these are fundamentally the same kind of thing, the same degrees of freedom as W1 and W2, but actually W plus and W minus are the definite charge states that emerge from W1 and W2. So this is very much like how you can have circularly polarized light by adding up some out-of-phase combinations of linear polarizations. So if you've worked with circularly polarized light, then you'll recognize this formula. But if you haven't, for today it's really not that important. In your mind, if you want to imagine W plus and W minus as being synonymous with W1 and W2, but only as it pertains to mass, then I think that is okay for today's video. When it comes to calculating the W masses, this nuance about definite charge states isn't super important. So I do bring it up in passing, and I have the equation here, and I have some information, but as far as the Higgs mechanism is concerned, in your mind you can think of the W plus and W minus mass as basically being the same as the W1 and W2 mass. Then, once you learn about the Higgs mechanism, and you see the Gell-Mann Nishijima relation, that's when you'll want to go back and think about W plus and W minus and diagonalizing T3, and you'll be like, oh yeah, okay, the isospin projections are +1 and -1, and so you're going to have a positively charged W plus and negatively charged W minus. So if this is your first time seeing the definition of the W plus and W minus bosons, I know it seems kind of arbitrary at first, but if you spend some time with the Electroweak model, eventually it's all going to click. Okay, but for today, we're just going to take this W plus W minus definition for granted. All right, let's calculate the mass of the W bosons. First, we write out the magnitude squared of the Gauge-Covariant Derivative acting on the Higgs field. And we get this expression involving the foregradient of the Higgs field, as well as the isospin fields and the hypercharge field. And for notational elegance, we'll go ahead and use the indices A and B so that we can write the isospin terms a little bit more concisely, using the Einstein summation convention. Okay, so remember, what we're imagining now is that the Higgs field is hosting some Nambu-Goldstone modes in the degrees of freedom generated by tau 1 and tau 2, so rotations of the flag about the x and y axis. And when the Higgs field is vibing in this way, then when we hop into the unitary gauge, that energy is going to be transferred from those Nambu-Goldstone modes into the W1 and W2 terms in the covariant derivative. So in the unitary gauge, the gradients that were in the Higgs field from the Nambu-Goldstone modes go away, and likewise, we can ignore the hypercharge for now because we're just dealing with W1 and W2. And so we can go ahead and unpack the W terms, writing out just W1 and W2, and ignoring W3 for now. We'll come back to W3 later when we calculate the Z mass. Okay, so now we have this expression that is going to give us energy as a function of how much W we have. And so this is going to be the W mass term in the Lagrangian. And to evaluate this, all we have to do is crunch the algebra. So first, we can go ahead and pull out a couple factors of g over 2, so we end up with g squared over 4 in front of the equation. And then we can go ahead and take the transpose conjugate of the left side of the expression. When we do this, we'll end up with the transpose conjugate of phi, and we move that over to the left because, bear in mind, it becomes a row vector now. And then the W tau terms, what those are going to be is a scalar times a Pauli matrix. And if you look at the definitions of tau 1 and tau 2, you can see that they're equal to their own transpose conjugate. So therefore, when we take the transpose conjugate of the W tau expressions, It's just the same W tau expression as before. All right, and so now what we're going to do is we're going to go ahead and FOIL through the expressions involving the W's and the taus. And when you FOIL this out, you end up with expressions involving tau 1 times tau 1, and tau 1 times tau 2, and tau 2 times tau 2. And we can simplify this by looking at the properties of the polymatrices. What we find is that tau 1 times tau 1, as well as tau 2 times tau 2, these are both the identity matrix. And likewise, if we look at tau 1 times tau 2, or negative tau 2 times tau 1, we see that those are also both equal to the same thing. And so therefore, the tau 1s and the tau 1s we can ignore because those are just the identity. And the tau 1 tau 2 plus tau 2 tau 1 cancels out to 0. So that middle term gets deleted from the expression. Now then, to clean up the phi dagger and phi terms, we can go ahead and write out the Higgs doublet phi, which is 0 v over root 2. And when you take phi dagger phi, you end up with 1/2 v squared. So, substituting that into the equation, we end up with g squared v squared over 8. Now what about this expression involving W1 and W2? Well, here, let's go ahead and invoke the definitions of W plus and W minus that we saw earlier. You'll find that if you multiply together W plus and W minus and multiply by 2, you end up with W1 times W1 plus W2 times W2, which is exactly the expression that we find multiplied by g squared v squared over 8. And so therefore, if we substitute in 2W plus W minus, we end up simplifying our expression to simply g squared v squared over 4 times W plus W minus. Now, W plus and W minus are conjugates of each other, and so we can interpret this expression as being of the form m squared times the magnitude squared of the W field. And by symmetry, you can think of this as W plus or W minus. There's no difference for the mass term in the Lagrangian. W plus and W minus have the same mass. Now, this term m squared magnitude of W squared, we recognize this as a mass term, and you can see Quigg equation 2.2.4 for justification of why that is. This is the form of the mass term in the Lagrangian for a complex-valued 4-vector field. And then simply by identifying the constant in front of the expression, we can see that the mass of the W boson is going to be GV over 2. So the mass of a W boson depends on the SU2 coupling constant G, as well as the Higgs vacuum expectation value. And that kind of makes sense. I mean, what else would it depend on? So that's really cool. That's a nice, satisfying expression, because all we really did was the same thing we did when calculating the effective mass of a photon in a superconductor. But instead of using a complex scalar field psi and the vector potential A, we used the Lorentz invariant complex doublet field phi and the isospin gauge fields W1 and W2. And you know what? If we want to calculate the mass of the Z boson, it's exactly the same idea. The only difference is now, instead of imagining Nambu-Goldstone modes in the Higgs field in terms of the degrees of freedom generated by tau 1 and tau 2, we're going to think about it in terms of the degrees of freedom generated by tau 3 and the hypercharge U1 transformation. So again, we follow the same procedure. We write out the magnitude squared of the Gauge-Covariant Derivative acting on the Higgs field. We hop into the unitary gauge, where the 4 gradient of the Higgs field goes away. And we look at the terms involving W3 and B. Now this time we have both the isospin coupling constant G, as well as the hypercharge coupling constant G prime. So we're not going to pull out a factor of G over 2. Instead, we're going to pull out a couple factors of 1/2, and we end up with a 1/4 on the outside of the expression. So now let's go ahead and take the transpose conjugate of the left half of this expression, while foiling it too in one fell swoop. We can do this by recognizing that the W tau term is not affected by the transpose conjugate, because tau 3 is its own transpose conjugate, and the hypercharge term is not affected by the transpose conjugate because it's a scalar quantity. So all we have to do when we FOIL this out is move over the phi dagger onto the left side, and then just go ahead and FOIL out the other terms. Alright, and now, in order to simplify this expression, let's make the following observations. First of all, just like we saw before, if we write out the Higgs doublet phi, we find that phi dagger phi is 1/2 v squared. And that's good to know. But inside this expression, we also have tau 3 and tau 3 times tau 3 and y squared and b. So we have to evaluate some other things too. And one of the things we have to evaluate is the expression phi dagger tau 3 phi. To evaluate this, all you have to do is put the tau 3 matrix between the phi dagger and the phi, and you end up picking up a -1 from the tau 3, so that expression evaluates to -1/2 v squared. We also make the observation that the Higgs field has a hypercharge of 1, so the y and the y squared go away, and so we can rewrite the expression like so. And next, what we want to do is, looking at this expression with the W3s and the Bs, we recognize that it has the form of a square, and so we can factor it out like so. But now if we look at this equation, we recognize, hey, wait a minute, this is like some constant times the magnitude squared of some 4-vector field. Now what exactly is this 4-vector field? Well, it's the combination of W3 and B that has mass. Like, by definition, right? I mean, we're not just saying that arbitrarily. We find, while doing this calculation, that there is this field, this particular combination of W3 and B, that has energy associated with how much of it we have. And so by following the same reasoning as the superconductor and the W fields, we can see that this field right here is the massive combination of W3 and B. But you know what? If we look at this field, we can see that it has the coupling constants G and G prime multiplied onto W3 and B, and it would be nice if we could divide those out somehow, so that this combination of fields were more similar to W3 and B. But then what do we divide by? Do we divide by G? Do we divide by G prime? Well, how about this? Imagine a right triangle where we have G and G prime as the two legs of the triangle, so that the hypotenuse has a length of square root of G squared plus G prime squared. So let's go ahead and divide out our field by the square root of G squared plus G prime squared. The Z field is the massive combination of W3 and B, where the ratio of how much W3 and how much B comes right out of the covariant derivative that we're analyzing to look at how much energy is in the W3 and B fields, in the situation with the Higgs field and the Nambu-Goldstone modes and all that, and we get this expression involving G W3 and G prime B, and then we divide out by this factor square root of G squared plus G prime squared that lets us sort of normalize those coupling constants. Now then, we can rewrite our expression in terms of the Z field by pulling the denominator out front and factoring it out, and we get the expression shown here, V squared over 8 times G squared plus G prime squared times the magnitude of Z squared. And we can recognize this as the mass term in the Lagrangian for a real-valued 4-vector field. You can see Quigg equation 2.2.1 to see where that comes from. And now all we have to do is simply match the terms and solve for the mass of the Z field. And we end up solving that the mass of the Z field is V over 2 times the square root of G squared plus G prime squared. And so if you look at this, you can see that it's actually very similar to the mass of the W, but with an additional contribution from the hypercharge coupling constant G prime. In fact, imagine setting G prime equal to 0. So if hypercharge weren't a thing, then the mass of the Z and the mass of the W would be the same. But because hypercharge is a thing, it adds an additional contribution to the mass of the Z. You know, there's another way of looking at this in terms of something called the Weinberg angle, or the electroweak mixing angle. And what this is, as shown in the triangle with the purple text, this is the angle in the right triangle involving G and G prime. So by definition, the tangent of theta W is G prime over G. And if we want to reframe everything we've been talking about in terms of theta W, then we can easily define not only the Z field, but also the photon field A mu as a rotation matrix acting on the W and B fields. So a rotation matrix has the form of cosine of theta, negative sine theta, cosine theta, and if you analyze this matrix acting on the W3 and B vector, you find that Z is exactly like what we just solved for, And then A mu is the orthogonal combination of W3 and B that doesn't contribute at all to the mass term. And again, the Z field is the combination that has mass, and the A field is the combination that has zero mass. So these are both mass eigenstates of the combinations of W3 and B. Okay, so we've calculated the W mass and the Z mass, and we've seen how those get their mass from the Anderson-Higgs mechanism. And when we calculated the Z mass, we saw this thing about the mixing of W3 and B and the mass eigenstates and Z and A. But here's the thing. All of this should make us wonder, how is it that the photon escapes mass-free? Because, electromagnetism is based on local phase symmetry. So what we need to find in this picture of this Higgs field and the SU2 and the U1 and the whole Electroweak model, what we need to find is a circular degree of freedom that doesn't affect and is not affected by the Higgs field. And in the vacuum state, we can imagine that simply as the complex doublet, 0 v over root 2, which in the flag picture is the downward pointing flag. So the question is, we know that the Higgs field can transform as a doublet under SU2L, and can also transform under U1Y. So is there any of those transformations, or any combination of those transformations, that doesn't do anything to the downward flag that is the Higgs field? If so, it's not obvious. Because if you think about it, any SU2 transformation is going to rotate the Higgs flag. By definition, right? That's what an SU2 transformation does in the flag picture. But at the same time, any U1 transformation is going to rotate the flag about its own axis. So you can't leave the Higgs field alone with purely an SU2 or a U1 transformation. What we need to do instead is to combine a transformation from SU2 with a U1 transformation in such a way that they cancel out for the doublet that is the Higgs field, but at the same time, they allow a circular degree of freedom, a circular group of transformations, a U1 group of transformations on every other doublet. And in order to see what that might look like, imagine we have a dandelion of flags. And all this dandelion is a way of getting a feel for the transformation. So this arrangement of flags is not important. This is just designed to be like a good sampling of the space, a good representative sample of doublets. And that kind of fills in the space so we can see what this transformation looks like and how it transforms doublets. Now, if we look at this transformation and we look at the bottom flag, we can see that it's not moving. So, what kind of a transformation is this anyway? Well, what it is we're rotating every flag about the z-axis using tau 3, right? Using an SU2 transformation, we're rotating all of those flags around the z-axis in the flag picture. But at the same time, we're using a U1 transformation to rotate each individual flag about its own axis, because that's what a U1 transformation does. And it just so happens that when you do this, and you look at the flag that's pointing straight down, that's the flag of the Higgs field, you see that it's not moving. So this transformation does not bother the Higgs field in any way. You end up with this circular degree of freedom where you can go around and around in circles, and it has a different effect on each kind of doublet, but at the same time it has the same effect. For every doublet, it rotates the flag around the z-axis, and it also rotates the flag around itself. It's just that it's only for the flag of the Higgs field where those changes cancel out, so that the Higgs field is totally immune or totally insensitive to this kind of transformation, whereas every other doublet sees this transformation as a kind of circular transformation. And so that's the flag picture, but now if you look at the complex plane in the doublet picture, you try to figure that out and what's going on there? Well, it's a little confusing at first, but then it's oh, wait a minute. The first component of each doublet, that is those circular dots, is spinning around like a U1 phase transformation in the complex plane. And the second component, those squares, are not changing at all. So that's how to look at it in the complex plane picture. It's just that this transformation does a U1 transformation on the first component, and it leaves the second component invariant. And then because of the fact that the Higgs field is defined to have a first component of 0, you can see then in that picture that the Higgs field is insensitive to this transformation. And of course, both pictures represent the same set of doublets. It's just that in one we're looking at the flag picture, and the other one we're looking at the complex plane picture. Now let's take a closer look at exactly what's going on with this transformation. Well, that was a bit much, but here we are. So in the left column here, we have the transformation that we were just looking at, which rotates every flag around the z-axis, while also rotating it around its own axis, which in general is going to rotate and twirl some arbitrary flag. But because the motion cancels out for the downward flag of the Higgs vacuum state, this transformation does not affect the vacuum state, and therefore this transformation will remain a symmetry of the Electroweak model even after we've spilled our superconductor into hyperreality. So this transformation is the U1 transformation of electromagnetism. The middle and the right columns show a tau3 and a U1 transformation, respectively. And for all these transformations, we can think in terms of the peas in a pod picture or the flag picture, because those are two different windows into the same algebraic structure. Now, as I mentioned earlier, we use the letter Y to symbolize hypercharge, and that's effectively a multiplier on how much or how fast the flags are going to rotate around themselves for the same U1 transformation. So for example, all the doublets shown here have a hypercharge of 1, like the Higgs field. So for all intents and purposes, we don't really have to worry about hypercharge for today. But suppose we wanted to understand how a doublet behaves if it has a hypercharge of -1. Well, in that case, the transformation on the right would just go around the other way, with the flags twirling around backwards, and then when you combine that with the tau3 transformation, you would find that the top flag doesn't rotate. And we see this with the lepton doublets, where those doublets have a hypercharge of -1, and so you end up with an electrically neutral top component, the neutrino, and then you end up with an electrically charged electron, muon, and tau, having a charge of -1, where the negative sign arises from the negative hypercharge. And in fact, in general, the electric charges of particles are determined by how they transform under both tau3 as well as their hypercharge. And this is the essence of the Gell-Mann Nishijima relation, which we'll get into in just a moment. But first, let's take a closer look at this transformation, which is the U1 symmetry group of electromagnetism, as it's the only subgroup of SU2 cross U1 which is independent of the Higgs vacuum state. Well, actually, there is one thing we should adjust. If you look at the peas in the pod picture, you can see that tau3 rotates the top components, those circles, counterclockwise, and it rotates the bottom components, the squares, clockwise. On the other hand, the U1 transformation rotates both components counterclockwise in the complex plane, since we're multiplying the whole doublet by e to the I theta. So when we combine these two transformations, the motion of the bottom components cancels out, and so those don't move in the combined transformation, but then the motion of the top components adds, and so those end up moving around twice as fast. So now let's go ahead and adjust our definition of the transformation by dividing the phase angle by 2, just to slow down the motion so that the combined transformation turns around at the same rate as the tau3 and the hypercharge transformations. Now this is a more properly adjusted transformation, which is still fundamentally the same degree of freedom, but now it goes around at the same rate as the weak isospin and the hypercharge transformations. Okay, so let's look at the specific formulas for these transformations, like the actual equations that are making things go. Well, in the middle column, the tau3 transformation, the transformed doublet phi prime is calculated by multiplying the untransformed doublet phi by e to the I theta tau 3, which swings the doublet around in the tau 3 degree of freedom. In the right column, we have a U1 transformation, and so that's just e to the I theta times the doublet. And you can imagine that either as e to the I theta, where theta is a scalar quantity, or if you want, you can imagine theta as theta times I2, with I2 being the identity matrix. Either way, it's the same. Also, bear in mind, for now, we're assuming that the hypercharge is 1 because we're dealing with the Higgs field, but in general, that equation would actually be e to the I times y times theta, where y is the hypercharge, a scalar quantity. Okay, so to arrive at the equation for the combined transformations, in the left column we can just multiply those two equations together, noticing that the order doesn't matter, because an SU2 transformation commutes with a U1 transformation. And remember, we're also going to divide the phase angle theta by 2 to slow down the transformation to the appropriate rate. So we end up with the equation shown here. But we can simplify that equation by absorbing things together into one exponential. To do this, we just have to add the tau3 and the U1 terms. And we can slip a 2x2 identity matrix onto the U1 term so that the matrix dimensionality works out. And that's a legit move because scalar multiplication does the same thing as multiplication by a scaled identity matrix. Now, if we add these two matrices, we find that the top terms add up to 1 and the bottom terms cancel out. So we end up with the simple matrix 1, 0, 0, 0. And it turns out when we exponentiate e to the I theta times that matrix, we end up with the matrix e to the I theta 0, 0, 1. And that matrix is kind of like a mermaid, but instead of a woman and a fish, it's a U1 transformation up top and an identity matrix down below. So now we see that our combined transformation, acting on a doublet of hypercharge 1, is nothing more than a U1 transformation e to the I theta on the top component of the doublet, and it does nothing to the bottom component. And so no wonder this doesn't affect the Higgs vacuum state, because by definition, the top component of the Higgs is 0, and 0 doesn't change under a U1 transformation. You can see now why we associate the top component of the Higgs with a charged field, and the bottom component with a neutral field. Hey, you know what, there's one other thing we should know here. So in the Electroweak model, we often use T3 instead of tau3, where T3 is defined as 1/2 tau3. The generators of SU2 are often normalized with this 1/2 factor, so that the transformation has eigenvalues of plus or minus 1/2. And we see the same normalization convention in a different context, when thinking about the spinor wave function of an electron, which also transforms under SU2 but in a different context, and it also has the eigenvalues of plus or minus 1/2, since electrons are spin 1/2 particles. Now, the SU2 of the electroweak gauge group pertains to weak isospin, not spin, but these two ideas share the same underlying group theoretic structure. And so we often use T3 instead of tau3 because it has that baked-in normalization factor of 1/2. So anyway, with that little nuance in mind, we can write our transformation as the combination of T3 and y/2. Now, this equation looks more complicated than it really is, because bear in mind that this is just the idea that the unbroken U1 subgroup of the electroweak gauge group is generated by rotating all the flags about the Higgs flagpole axis, and then rotating all the flags about their own particular axis by the same angle, and then slowing it down by a factor of 2 so it has the right speed. People often wonder, why is T3 singled out in particular instead of T1 or T2 or some combination of the T's? But that's just because of our choice that the Higgs vacuum state has 0 for the top component. If instead we started with the convention that orients the Higgs vacuum state differently, we would arrive at basically the same equation, but dressed up with different T terms. And so you see there's nothing really cosmically fundamental about T3 in particular. That's just a reflection of the fact that the Higgs flag is conventionally vertical. People also often wonder why the hypercharge transformation is divided by 2. It's like, does hypercharge only matter half as much as isospin? Well, remember, there's a hidden 1/2 built into the definition of T3, and so really we're just averaging the SU2 and the U1 transformations. It's not like hypercharge is half as important as isospin. No, these hypercharge and isospin transformations balance each other equally when applied to the Higgs vacuum state. Okay, so we have now unlocked a very deep and a very important equation. Are you ready for this? Wait for it. Haha. Q, the generator of the U1 transformation that gives rise to electric charge and electromagnetism, is a combination of weak isospin and hypercharge. This equation is the Gell-Mann Nishijima relation. You know, this is often taught as like one of those rules that you just have to believe and you just have to take as an axiom. But actually, it's not arbitrary. It exists for a reason. And you can see that reason if you just think in terms of a dandelion of flags. Okay, so if we look at the particles of the Standard Model, their properties are encoded with a lot of numbers, and it's not clear where all of those numbers come from. Or, in other words, it's not obvious why we have the particles we have in our universe. But there are patterns in some of the numbers, and so it's not a total mystery. For example, as we now know, the electric charge of a particle is the sum of its T3 eigenvalue and half its hypercharge. So for the SU2 doublets, circled here in pink, the T3 eigenvalues are just 1/2 for the top component and -1/2 for the bottom component. And this mirrors the structure of spin 1/2 systems in quantum mechanics, where, for example, an electron can have a spin of plus or minus 1/2, and that is encoded in the top and bottom components, respectively, of the electron's spinor wave function. Now, for the particles that don't transform under SU2, their T3 eigenvalues are 0, sort of like a particle that doesn't have any spin, metaphorically speaking. Physically, weak isospin and spin are different things, but they share a lot of the same mathematical structure. And then for the W bosons, which are not matter particles but are gauge bosons, those T3 values are a little weird. Those aren't exactly eigenvalues, but are rather a reflection of the fact that W plus and W minus can flip a doublet over in the flag picture. Because bear in mind, W plus and W minus are comprised of rotations of the flag about the X and Y axis, as well as a little twirling action that comes from their complex definitions, but we're not going to get into that for now. And so anyway, what a W boson can do is it can transform an electron into a neutrino, or vice versa. And so when you're flipping around a doublet, you're going to change the particle's T3 eigenvalue by plus or minus 1, depending on whether it goes from plus 1/2 to minus 1/2, or minus 1/2 to plus 1/2. Okay, now if we look at the hypercharge column, the hypercharge assignments are more mysterious than the isospins. Let's not worry today about where the hypercharge numbers come from. That is a long story and a topic for another day. There is an easy but unsatisfying explanation for where the hypercharges come from, which is just that they're whatever they have to be in order for the charges of the particles of the Standard Model to align with experimental observations. But of course, we want a deeper, more fundamental explanation of why those hypercharge numbers are what they are. And for that, we would have to get into anomaly cancellation, and that's a whole thing, but hopefully we'll come back to it someday. Oh, speaking of hypercharge, I want to give a shout out to Martin Bauer. Martin, thank you for taking the time to talk to me about hypercharge and anomaly cancellation. Our conversations have given me a lot to think about, and I look forward to discussing the topic further, and maybe even collaborating on a video one of these days. You've been very generous with your time, and I just want to let you know I really appreciate it. So thank you. All right, let me make a couple more comments on this table before moving on. So in addition to the matter particles shown here, we also have the second and third generation particles, the muon and the tau and the charm and the strange and the top and the bottom, and those have identical properties to the first generation. They're just much more massive and very unstable. But they do exist for some strange reason. Oh, and if we look at our gauge bosons, we have the W's and the Z and the photon, and we now know that those are born of the electroweak gauge group, after it's been broken down by the Higgs field. So the ideas we've talked about today give us a really profound insight into where most of the gauge bosons of our universe come from. But then we also have the gluons. The gluons arise from the SU3C gauge group of the strong force, which we haven't talked about today because it would have taken us too far afield. Gluons do not transform under SU2L or U1Y, and so they have no weak isospin or hypercharge, and therefore no electric charge. But they do have color charge, which pertains to the strong force and SU3C, but that's a topic for another day. Today we're just looking at the electroweak sector of the Standard Model. Okay, well, I have to mention the Yukawa couplings, at least briefly, but this is a complicated topic that goes beyond the scope of today's video, so we're not going to go into it in detail. I just want to mention it in passing. Okay, so before we put the Higgs field into the electroweak model, we saw that all the matter particles had to be massless, because otherwise different observers might disagree on which particle is left-handed and which particle is right-handed, and whether or not it transforms as a doublet or a singlet under SU2, and whether or not it feels the W fields. So we made everything massless. But now that the Higgs field is here and has a non-zero value, technically we could have these Yukawa coupling terms in the Lagrangian, which allow us to mix together the right-handed and left-handed components of our matter particles in a way that's compatible with relativity, as well as the gauge group of the electroweak interaction. The way to think about this is now different observers can disagree on whether a particle is left-handed or right-handed, and in reality, when you look at the wave function of a particle, you actually have a left-handed and a right-handed component, and different inertial observers can disagree on how much a particle is right-handed versus left-handed, but all inertial observers are going to agree on the value of the Lagrangian term shown here, because you can see how it kind of mixes the right-handed and left-handed components together. In this equation, L is the left-handed component and R is the right-handed component. And this zeta factor is a coupling constant. So, for example, if we think about the electron in the Higgs field, its Yukawa term is going to have the form shown here, with zeta sub E being the Yukawa coupling of the electron, and V over root 2 coming in from the Higgs vacuum state. And the net result of what this term does, when you think about like the dynamics of the physics and what happens when you have a term like this, is it ends up giving the electron mass. And the mass of the electron is the product of the electron's Yukawa coupling constant times the Higgs vev divided by the square root of 2. When you learn about the Yukawa couplings, the first thing everyone wants to know is, what is the nature of this? What is going on here? What is like the microscopic description of this interaction? And the answer is, there is not yet a good answer. So the way to think about the Yukawa couplings is it's more like the lifting or the resolution of a paradox, rather than a good explanation. So if not for the Higgs field, we really would have to have massless particles. But with the Higgs field there, acting as this scalar field that fermions can interact with, well, then it's possible to have these Yukawa coupling terms in the Lagrangian. But it is a deep mystery. And also, it's possible that the true story is more complicated than what we're showing here. So what I'm showing here is kind of like the vanilla standard model, but there are extensions to the standard model involving multiple Higgs fields or other kinds of fields in which the Yukawa couplings have a more nuanced nature. But again, we're not going to go down that rabbit hole for today. I just wanted to mention it in passing so that we can see that this apparent contradiction between special relativity and the chiral electroweak gauge group can actually be resolved by the presence of a scalar field that the fermions can interact with. Okay, well, based on everything we've seen so far, you can start to appreciate that there really is something to this electroweak model. Even though it starts off kind of weird, once you see it, it's like, hold on, wait, this actually kind of works. You start off with the SU2L cross U1Y symmetry group, you break it with the complex doublet, and you end up with the correct masses for the W and Z bosons, and you get a massless photon, and you get Yukawa couplings giving mass to the fermions, and it's like, okay, cool. I think we might be onto something here. But of course, these ideas rely on the fact that we live inside of something that's very much like a superconductor, which is very difficult to accept, and something that we should be very skeptical of, but also something that if it turns out to be true, would validate everything else we're talking about. Like, if we had a way of directly probing the superconductor, the Higgs field, then we would know that we're on the right track, and this is it, and this is what's going on in our universe, and that would be amazing. And so when you think about what are the different ways of directly probing the Higgs field, this complex doublet field, well, you think about the phase-like degrees of freedom, the Nambu-Goldstone modes, and you have to recognize that that's equivalent to looking at the W and Z fields, right? As we've seen, I mean, based on the Higgs mechanism, the W and Z fields get their mass from the Nambu-Goldstone modes in the Higgs field. So you can interpret measurements of the W and Z field as telling us something about the Higgs field, but if we're being skeptical about this concept of a Higgs field, you could always imagine interpreting those measurements as something else, right? So if we want to really directly probe the Higgs field, what we would have to do is actually excite an amplitude mode in the doublet. Because that can't just be gauged away, that's a real thing. That's the Higgs field really being itself. And if we can observe such an amplitude mode, also known as a Higgs boson, then we know that this superconductor thing is not just theory, it's real. Like, it's really for real, it's like actually real. And so that's why, there was all this hype about like, let's discover the Higgs boson. That would be like the best thing ever. So let's talk about what the Higgs boson would look like, and in particular, how much mass we would expect it to have. So the Higgs boson is an excitation in the amplitude of the Higgs field phi, so that instead of a constant VeV, we have V plus H, where H is a scalar field that's rippling around in spacetime. So imagine V, the VeV, which is like 246 GeVs, and then a small h on top of that can go up and down, and so a Higgs boson is like a quantized jiggle in H. Okay, so writing out the Higgs field in terms of 1 over root 2 V plus H, we can calculate the amplitude squared of the field as 1/2 V plus H quantity squared. And now the basic idea is that the mass of the Higgs boson arises from that Ginzburg-Landau sombrero part of the Higgs Lagrangian that we saw earlier. So let's write that out with the mu and the lambda and the phi dagger phi. And when we substitute into phi dagger phi, 1/2 V plus H quantity squared, we get an equation which tells us the energy that corresponds to having these ripples in the amplitude of the Higgs field. Now, what follows is a bit of algebra, and it's a little bit tedious, but it's not so bad, so let's just work through it real quick. The first thing we're going to do is we're going to multiply out the quadratic and the quartic terms in V and H. So just multiply everything out there, and you see the expression shown here. Next up, we're going to collect some terms into this V0 parameter, and that's just going to be negative mu squared over 2 V squared plus lambda over 4 V to the fourth. So that corresponds to the potential of the Higgs field with just the VeV. So that's like a reference point of a constant Higgs field without any H rippling on top of it. And what we can also do is we'll use a small h approximation to neglect the h cubed and h to the fourth terms. The idea here is that because h is going to be small, especially relative to v, we can get away with just expanding it to second order. So when we do that, we get a slightly simpler expression, shown here. And next up, what we want to do is we want to substitute in v equals mu over the square root of lambda. And remember, that equation comes from calculating the VeV of the Higgs field. It's very much the same as calculating the density of a superconducting condensate. And when we do that, we end up with the expression shown here. You'll notice that two of these terms cancel each other out, and then we can absorb the other two together. Minus 1/2 plus 3/2 is 1, so we end up with V0 plus mu squared H squared. And now at this point, we may as well use V equals mu over the square root of lambda again, so that we can write the expression as V0 plus lambda V squared H squared. And now what we can do is we can interpret that term as a mass term in the Lagrangian of a real-valued scalar field. In this case, the field is H, which is a field of amplitude ripples on the Higgs field. And so a term like that in the Lagrangian is going to have the form 1/2 m squared H squared. And so if we just match the terms and we solve for the mass of the Higgs boson, we end up getting that the mass of the Higgs boson is the Higgs VeV V times the square root of 2 times the self-coupling constant lambda. Before the Higgs boson was discovered, people had done a bunch of measurements which constrained the values of what V and lambda could be. So lambda was something between 0.1 and 0.3, and V, the Higgs VeV, that was known with more accuracy, that it's about 246 GeVs. So based on that, if you look at this equation, you can estimate that the mass of the Higgs boson should be somewhere between about 110 and 190 GeVs, depending on the value of lambda, which wasn't known with a ton of precision until after the discovery of the Higgs boson, but there was a pretty decent estimate, so the Higgs boson should have a mass of like about 100 and something GeVs. Now a particle of that mass would be very unstable, but if you could create it, you could detect it through its decay products. And so when you think about like what do you have to build in order to actually make Higgs bosons, you need extraordinarily intense particle collisions, but in order to make that happen, you would have to build the largest machine ever built with the largest and most powerful superconducting magnets. This would be insane. You would need to collide protons at like 99.999 lot of nines the speed of light, which is very difficult, but in theory, it can be done. And so people did it. And, if you look at all the things in history that people have done, a lot of bad things, a lot of stuff that wasn't great. But on this one, people did a great job. Building the Large Hadron Collider, that was really quite something. And, I think it's worth pointing out, this video is called Superconductivity and the Higgs Field. And so far, we've been very theoretical, and it's all been like theoretical physics. But superconductivity in the Higgs field is also the story of the greatest experimental physics achievement in recent memory, because this involved more superconducting material than anything that had ever been built, and it was built to discover the Higgs boson. So anyway, I think it's just beautifully poetic how the story of superconductivity in the Higgs field isn't just a theoretical thing, but also spills out dramatically into the real world. It's really amazing. Well, anyway, when you're smashing protons together, you're creating all kinds of particles, and it's really a mess. But you have these detectors, and these detectors tell you what comes out of the collisions. And in order to do good science, you want to have a couple of detectors, not just one, so that you can compare their results. So what we're about to look at are ATLAS and CMS. These are two of the detectors on the Large Hadron Collider. And their job is to measure, what is it that's coming out of these insanely intense collisions. Alright, so the first way in which the Higgs boson was observed was in terms of its decay into two photons. So the Higgs boson is very unstable. If you create it, it'll decay almost right away. But one of the ways it can decay is into two photons. And what's nice about the two-photon decay mode is that it's very clean. So what I'm showing here in these plots are data from the two different detectors, ATLAS and CMS, and in both cases, on the x-axis, we have the combined energy of the two photons that are produced in these collisions. And the top of each plot shows the background as well as the signal for the Higgs boson. That's that little bump. And the reason there's a background is that when you're smashing particles together with crazy intensity, this is giving off all kinds of light. You're going to have photons coming out of that all over the place. But statistically, you're going to have a nice, clean curve for those photons. If it were just random photons coming out, flying out, you can calculate what that distribution is going to look like in terms of how often you get a low-energy photon versus a high-energy photon. And that's going to give you a nice, smooth background curve. But then you see that there's a bump at a particular energy scale of about 125 GeVs. And so what the bottom of each plot shows is the bump with the background curve subtracted out. And in both ATLAS and the CMS, you find that there's a bump at the same energy scale of about 125 GeVs. And so you think about, what is the kind of thing that can create a bump? Well, if you create a particle that has mass energy of 125 GeVs, and it doesn't have to exist for very long, just the shortest little blip of time, but then it decays. Well, when it decays into two photons, that'll add a little blip onto your chart, and you'll say, hey, yeah, we got a new particle at about 125 GeVs. This was extremely exciting, because bear in mind, based on the theory, we're expecting the Higgs boson to be a new particle, somewhere between maybe 110 and 190 GeVs. So here's a new particle at 125 GeVs. That's it, right? That totally seems like this is the Higgs boson. And of course, this detection got people very excited because it seemed like they had found what they were looking for. But technically, how do you know that this is the Higgs boson as opposed to just some other new particle with a mass of 125 GeVs? Well, that would be pretty unlikely, but technically, if you're doing science, you have to have a lot of confidence and you have to have a really sound set of experimental data. But fortunately, there's a way to do even better than just the two-photon measurement. Because the mass of the Higgs boson is not the only prediction that the standard model gives us. We can also predict all the possible ways that the Higgs boson can decay, and how probable each decay mode is. And so if you look at the chart here, I'm showing the 9 most common decay modes for a Higgs boson. So a Higgs boson is most likely to decay into a matter-antimatter pair of bottom quarks. The second most likely decay mode is into a couple of W bosons, except, well, technically the second W has an asterisk, and what that means is that only one of the W bosons is real, The other one's virtual off-shell, and it decays into something else before it really has a chance to exist. But that's like a nuance that we're not going to get into now. The third most likely thing is to decay into a couple of gluons. The fourth most likely is to decay into a couple of tau particles, tau and an anti-tau. Fifth most likely is a couple of charm quarks. Sixth most likely is a couple of Z bosons. Again, one real and one off-shell, one virtual. The seventh most likely is into a couple of photons, as we just looked at with the background curve and the bump. So that is actually not a very common decay mode, but it is a very clean signal. And so the cleanliness of that signal is very nice from an experimental perspective, even though that decay mode is pretty unlikely. And then the eighth most common decay mode is into a Z boson and a photon. And the ninth most likely is into a couple of muons, a matter-antimatter pair. And beyond that, there are other possibilities, but they're extremely unlikely. Like, for example, technically a Higgs boson could decay into 4 photons, but that only happens like 1 in a bajillion times. And then some decay modes are completely ruled out, completely impossible. Like, for example, a Higgs boson cannot decay into 3 photons, because that's just not allowed by the conservation laws of the Standard Model. Well, anyway, when you take all of this into consideration, you see that the Standard Model actually gives us a very specific fingerprint for what the Higgs boson should look like in terms of what it decays into. We should expect to see that particle, that mysterious particle of 125 GeVs, in all of these different decay modes, and we shouldn't see it in the decay modes for which we shouldn't see it, you know? So you're not just measuring the prediction, you're also measuring that it's not the thing that the prediction doesn't predict. It's like you have to think about the dogs that aren't barking, if you know what I mean. And on top of all of that, the decay probabilities, that is the branching ratios, the relative percentage likelihood of each of these decay modes, should also match the Standard Model. And if that's the case, if you can observe this mysterious 125 GeV particles across even just a few of these different decay modes, and it matches, then that's the Higgs boson. So I looked on the internet and I found a paper from 2015 that showed ATLAS and CMS measurements of 5 of these decay modes. And as you can see, it's a match. Within some error bars, because given the state of the art of present technology, these numbers can only be calculated so precisely at the present time, but hopefully in the future we'll have better precision on this. In fact, hey, maybe since 2015 there's already better precision. I don't know, I found a paper that kind of worked, so I might be a little bit out of date on this already. But anyway, yeah, as you can see, the Higgs boson has been observed in a number of different decay modes. The branching ratios match the prediction, and so we can say with a very high degree of confidence that the Higgs boson does actually exist. That is to say, we are actually living in basically a superconductor. And we know this not just because it's conceptually very nice and very pragmatic and it works and it lets us unify electromagnetism and the weak nuclear force. No, but now we know that it also exists in its own right, like it's been directly observed. So that is just an incredible thing. It's amazing and astonishing, and it's just wonderful. I mean, it's like, wow. So let me comment a little bit on how the Higgs field might not be like a superconductor. Like, what are some of the ways in which the metaphor breaks down? Well, first of all, everything we've been talking about so far is at the level of Ginzburg-Landau. So with superconductors, we also have the BCS theory that tells us the microscopic story of how electron pairs form into the condensate that we can then analyze with Ginzburg-Landau. With the Higgs field, we don't yet have that BCS level of description. So we only have the phenomenological math of the Ginzburg-Landau potential. And that means that there is a deep mystery as to what the Higgs field is and where it comes from and what even is it and why are we living in a superconductor? That's very strange, right? And when you think about possible answers to that mystery, there's a very beautiful line of reasoning which involves extending the superconductor analogy one step further and saying, okay, here's what we're going to do. Let's assume that the Higgs field is a condensate. And better yet, let's assume that there's something about the Standard Model, maybe SU3 in the strong force, that naturally forms into a condensate. Because, one of the things with the strong force is you have color confinement, where if you try to pull quarks apart, you're just going to end up creating more quarks. And so you have this really cool situation where quarks are always bound with other quarks. And so maybe there's another property of the strong force, which is like universal condensation or something, And so then if you could show, based on looking at the dynamics of the strong force, that a condensate naturally arises, maybe if we explore the properties of that condensate, we'll find that that is the Higgs field. And then we no longer have to invoke the Higgs field as this like arbitrary complex doublet scalar field, but rather at that point we would have a microscopic explanation for what the Higgs field is and also why it exists. So this is a very beautiful idea, but it doesn't work. And the reason it doesn't work is it predicts a mass for the Higgs boson, which is a few thousand times smaller than the measured value. And, that's kind of a big deal, so there goes that theory. But it's such a beautiful idea that maybe we want to try to preserve it anyway. Maybe we just have to kind of warp it and make it work some other way. But to do that, we would have to postulate the existence of as yet undiscovered fermions, interacting in accordance with some as yet undiscovered force, and so the model becomes a lot more speculative. Now, if you're interested in this idea, you can look up Technicolor models, and that's the name for this general category of models in which the Higgs field is actually secretly a condensate. Now, Technicolor, it is a very beautiful idea, and it was popular back in the day when we didn't have as much experimental data as we have today. But nowadays, it's not really as fashionable as it used to be, because the experimental data seems to be indicating that Technicolor is probably not true. There's probably something else going on with the Higgs field. So then, what even is the Higgs field? We don't know. It's a beautiful thing, in this time period in which we're living, in the long arc of history, we're not at the end. So we still, as of today, we do not know the fundamental nature of the Higgs field. We just know that there's this phenomenological model for it that can be interpreted pretty much in terms of superconductivity. Though, of course, that analogy, it shouldn't be constrictive, it should be constructive. So an analogy is just a thing that gets you from point A to point B, where point A is what you know and point B is what you don't know yet. And so you can kind of discard the analogy once you see the thing. So having used superconductivity as a kind of gateway to the Higgs field, of course, we don't want to think that all the Higgs field could potentially be is strictly a superconductor. No, it might surprise us, and there's still a lot of open questions we have. Speaking of open questions, here's a question. How many Higgs fields are there? Well, before the Higgs field was discovered, as far as we knew, there were 0 Higgs fields. But now we know there's at least one. And, I'll say this kind of loosely, so don't take this too literally, but a superconductor, in a way, is a place where there are at least 2 Higgs fields. See, here I'm reversing the analogy. I'm saying the superconductor is like a Higgs field. Because if you were a sentient being that lived in a superconducting thing, and you were a scientist, you'd be like, aha, I know that photons have mass. I'm so smart. But then someone outside the superconductor would be like, hey, superconductor being, actually, photons don't really have mass. That's just a property of the material in which you live. So then the superconductor being can break out of their paradigm and be like, oh yeah, wow, actually it is a circumstantial thing and that photons don't really have mass. But then, of course, you can go another level up because you can think well, the W's and Z's have mass, but it's not really. Not if you factor in the Higgs field and kind of zoom out a level and be like, whoa, actually, the W's and Z's don't really want to have mass. It's the Higgs field that gives them mass. And so now we're finally at this exalted level where we can see the standard model in its full glory. And we're like, okay, SU3 cross SU2 cross U1 is the gauge group of the standard model, and that is the fundamental thing. But it's wait a minute, how do we know that is the farthest out meta level of analysis? What if, even when you account for the Higgs field, what if there's another Higgs field that we just haven't observed yet? And this could totally be the case. Because if you think about it, imagine another Higgs field, but with a way more massive Higgs boson. Well, that would give a lot more mass to whatever gauge bosons it's interacting with, so it would suppress them a lot better. And there could potentially be other forces out there, other super massive gauge bosons, other Higgs fields that we just haven't been able to observe yet because they exist at this super high energy scale. Now, on one hand, Occam's razor says, well, okay, let's not assume there's a whole bunch of Higgs fields. But on the other hand, if you do allow for the possibility that maybe there's another Higgs field or even multiple more Higgs fields, then it's possible that the gauge group of the standard model might actually be a broken down remnant of a more elegant, more fundamental gauge group. For example, SU5 or SO10. SO10 is the way of rotating things in 10 dimensions. And that one is a suspiciously good fit for the standard model in a variety of ways that we won't get into now. But anyway, that's the idea of grand unification. So all that's to say, there's a lot about the Higgs field that we don't yet know. And so even though the Higgs field is very, very much like a superconductor, think of it as potentially something that really goes beyond a superconductor in an as yet unappreciated way. All right, before wrapping things up here, I just want to make one final comment, which is technically we don't yet know whether the Higgs field is stable or just metastable. So the Higgs field originally condensed, I think, like a picosecond after the Big Bang. And ever since then, our universe has been in this superconducting state, right? This Higgs vacuum state. But in theory, it might be possible for the Higgs field somewhere to fluctuate into a different vacuum state, and then for that vacuum state to propagate out in a bubble at the speed of light, and as it goes along, it's changing all the physics in its path. It's like a bubble of annihilation that goes along, dissolving atoms like sandcastles in a tsunami, just completely changing the nature of reality and everything. And you end up with a cosmic amnesia and a whole new operating system for nature, and it would be a terrible catastrophe. At least for anyone who dreams of leaving behind an enduring legacy in this universe. It would just wipe out all of our attempts to have any connection to the eternal. Like, it would just be the worst thing ever. So it's possible. We don't know. So far, so good. I mean, it's been 13 point whatever billion years, and we're still okay. But you never know. The vacuum state of the Higgs field could change one of these days. Now, there's a silver lining, which is that because this bubble of annihilation would expand at the speed of light, you wouldn't see it coming. Although that silver lining has a touch of gray, because if you can't see it coming, then for all we know, it's already on the way. Oh man, well, let's hope that's not the case. Oh geez. I need to go for a walk. Hey, thanks for watching, and I'll see you in the next one. Assuming the Higgs field doesn't decay.